It's hard to write defensive and secure code in any programming language if your code does not live up to certain quality standards. This includes writing clean code, readable code, writing code that follows the principles of software development. And these principles are what we'll discuss here in this video. Before you actually execute on any project, whether it's a software project or some other kind of project, it's important that you think, design, and prepare for the project beforehand. That's when you make the most of your time executing on the project. And the same is true for defensive design. Defensive design is the practice of planning for contingencies in the design stage of a project or an undertaking. With defensive design, not only do you think about how you'll execute on a project, you'll also think about all the ways in which things can go wrong once your project is up and running. And then you code into your project ways to defend against these failures, whether these failures are due to user input, hardware failures, anything. Defensive design can be adopted for any kind of project, an engineering project, a mechanical project, anything. When you adopt defensive design in a software project, what you get is defensive programming, which is a form of defensive design intended to ensure the continuing function of a piece of software under unforeseen circumstances. Any software will accept inputs from the user from a third party library or other external components. And that piece of software has to make sure that it continues functioning properly, even if the inputs are not correct. Ensuring this is defensive programming. The idea is your software should function correctly no matter what. It should not behave unpredictably, even in the presence of unpredictable circumstances. Now, defensive programming is not all about defense or security. It encompasses many tenets. For example, part of defensive programming is improving code quality and reducing the number of software bugs and problems via maintenance of your software and extensive testing. Eliminating subtle bugs will lead to better programs, more predictable programs, so code quality becomes all important. It's also important that you make your source code comprehensible. Source code should be readable and follow sound principles of software development. If your code is so arcane that it cannot be maintained by a team of developers, well, essentially that means you are the only one who can take care of that code, and that's not scalable nor sustainable. It's important that your code can be read by anybody on your team and understood by anybody on your team. This makes maintenance of the code and removal of bugs easy. And finally, you should make sure that your software behaves in a predictable manner, in spite of any unexpected inputs that might be fed to your software. Unpredictable behavior of software in production is very hard to track down and debug, in spite of the presence of logs and all of the monitoring tools. Even if your software fails, make sure it does so gracefully and in a predictable manner. And there are ways that you can recover from this failure well. Now that we've understood the big picture behind defensive programming, let's talk about the principles of software development. These principles are a list of styles, approaches, philosophies, learnings, and software practices that software engineers have understood and learned over the years. These are not guidelines that were set up in a day. All of these guidelines come because of years of hard earned experience. Having made millions of mistakes, software engineers have thought long and hard about the best design principles in order to fix those mistakes and avoid committing such mistakes in the future. These principles help us write clean, comprehensible, maintainable, and scalable code. Let's start with the first principle. This is the simplest of all, but also the hardest to implement. The acronym for this is KISS. Keep it simple, Simon. And this is an exhortation to all developers that every component that you write code for should be as simple and clear as possible. Anyone looking at that component should know what exactly it does and why the implementation is set up in the current manner. Things should be clear and well understood by everyone. You should not create new entities in your system, whether they are classes, new functions, or other components, without having a clear reason for these entities to live or exist. Don't create a new class or a component unless you absolutely have to. Think long and hard before you introduce something new into the system. Whatever code changes you're making, you need to think about keeping things simple. Keep your components focused on solving exactly one thing and doing it correctly. If you're solving an entirely different thing, create a new component. That's a good use case. Make sure you reuse your existing components wherever possible. Let's move on to another best practice or software engineering principle. It has a cool little acronym as well. YAGNI. You aren't going to need it again. Now, software developers love writing lots of complex code. So once they have a component, they want to write all of the code for the component for all of the possible use cases of the component. But that's not the right thing. Do not implement all the functionality of a component at the very beginning. You may never end up using this functionality in the future if your requirements change or your design changes. Write code for only what you need at this point in time. So start with the very basic functionality first, only what you need to keep your project moving forward, and then add in more functionality as needed down the road. Everything does not need to be implemented up front. You need to let your classes evolve. Add new functionality as needed, refactor existing functionality as and when it's required to do so. Don't shy away from going back and changing and adding things. Change is good, evolution is good. The next important software engineering principle that we'll discuss can be expressed using this pithy saying: measure twice, cut once. So, before you dive into implementing anything, think about whether the problem itself that you're solving exists and is the right problem. Is this method of solving the problem correct? Are the requirements all met? Have you thought through the design? Now, it's important that you think of this over and over again, and only after you're convinced, you move on to choosing the tools to implement the solution, choose your team, choose the metrics to measure the outcome once the solution is complete. So it always saves you time to measure twice and cut once. Here is another software engineering principle, once again with an acronym: try or don't repeat yourself. Now, when you're writing code, often the same bit of logic is needed in multiple places. Avoid copy pasting your code into different components. Do not have the same logic in more than one place. Have all of your multiple components use a utility, a common utility that can be shared. Repeated code is a scourge and you'll pay for it over and over again. This means anytime you have to make any changes or fix that code that has been copy pasted into different places, you'll have to do it as many times as you've copy pasted that code. It's better to pay the upfront cost of refactoring common logic into a single method or component. So you pay now, but that payment is limited. You're not paying down the line. Here is a software engineering principle named for a philosopher, Occam's razor. This principle states that in a group of hypotheses, always select the one that has the fewest assumptions. So, the hypothesis that makes the fewest assumptions is the right one. What does this mean in code? Keep your code straightforward, satisfying very few use cases. You add your complexity only when you absolutely need it. Another software engineering principle states big design should always be upfront. So, when you're looking to write code for a component, make sure you design the general architecture and the basic interactions upfront. You should have a big picture understanding of what this component is going to look like and how it's going to interact with other components. But at the same time, be prepared for your code to change and evolve during the implementation phase. This could be because of changing requirements or flaws that you've identified in your design. Money may be the root of all evil in the real world, but in software, it's premature optimization. And since Donald Knuth agrees with me, I'm going to believe this is correct. Now, when you're writing code, focus on program correctness first. Optimize later. Make sure that your code handles all of the conditions it needs to and performs the right operations. Once you're reasonably satisfied that your code is correct and you've written tests for your code, you can focus on improving the performance and resource utilization of the code. Correctness comes first, optimization later. So avoid premature optimization. So if you write optimal code very early in the life cycle of your program, it may not be used at all. You might throw away that code altogether and have wasted time. Let's look at the next software engineering principle, the principle of least astonishment. So, code that you write should be intuitive and what it does should be obvious. It should not surprise other developers or users who look at your code. It should have a low astonishment factor. Basically, it means your system should behave in an obvious and predictable and consistent manner and should not cause unexpected side effects. It's your responsibility as a developer to design user friendly and clear components matching what the users expect, their mental models, experience, and expectations. Here is another principle that has served me well in the past, the law of Demeter. This talks about how components interact. You should ensure that you keep your software components independent of each other, they should be loosely coupled. So, the functioning of one component should not depend on another component unnecessarily. Strongly coupled components are hard to maintain, hard to version, hard to improve. So, reduce the communication and interactions between components. And whatever interactions there are, make sure they are well defined, well documented. At the same time, you need to maintain cohesion by putting related classes, methods, and other components in the same module or namespace. So, if you know two classes are going to be talking to each other all the time, they should be part of the same component. Once we've wrapped our head around the basic software engineering principles, let's look at some other principles that you ought to keep in mind. When you're building your component, make sure that the responsibilities of the client using your component are minimized. So, design your API to minimize the client's burden. The client should find the API straightforward, simple, and easy to use, and the API should not perform unexpected operations. The actual implementation of the API can be as complex as you need it to be, but this complexity should be isolated within the API. It should be abstracted away and hidden from all users of the API. So keep your API simple, keep your implementation complex if you need to. Maximizing encapsulation goes hand in hand with minimizing client responsibilities. Whatever a component is, it should have a well defined purpose, and the complexity of the implementation should be encapsulated into that component. Any user of that component should be able to use it without knowing any of the underlying implementation details. This is what comes from making the API easy. So, without worrying about the actual implementation, users should be able to use that component correctly. Here is another engineering principle, prefer compile time errors to runtime errors. You should write your code in such a manner that you're able to detect and fix errors early. Maybe have assertions in your code to look for errors proactively. The later an error is detected, the more expensive it is to fix. Now, every programming language has its own set of features, its own constraints, and also tools to help you determine the source of the error. Make sure you take advantage of all of these in trying to track down your errors. Fix your errors early at development, during testing. Once your product has shipped, it becomes very expensive to fix errors, as this graph will show you. At the bottom here on the x-axis, we have the various phases for a particular product: design, development, testing, pre-release, and production. Along the y-axis, we will plot the cost of a change that you make to your product at these different phases. Note that the y-axis goes from 10x all the way to 1 million x. This is not on a linear scale, it's on an exponential scale. Now, here is how this graph looks. for the different stages where you find and fix bugs. In the design and development stage, you pay a very small price. If you find your bugs here, they are relatively easy to fix. The cost is not very high. But in the testing phase, you can see that we pay a higher cost. And once your product has been shipped and it's in the hands of your clients, it becomes very, very expensive to fix those bugs. A methodology used in the design and development of software that helps find bugs early is design by contract. This is a metaphor for how components of a software system collaborate with each other on the basis of mutual obligations and benefits. Every component that is a participant in an interaction has obligations towards the other components that it interacts with, and it receives benefits from those other components. There are three basic parts to designing by contract, and we'll revisit this later on in this learning path. Design by contract essentially states that inputs to your programs need to meet certain obligations. These are referred to as preconditions. Your preconditions check need to all pass. Once your program executes, there are certain properties that will not change during the course of execution. So, certain properties will be assumed on entry and guaranteed on exit. And these properties are referred to as invariant. They do not change during execution. And finally, once execution is complete, that execution would have updated other properties. Guaranteeing the updated state of a property on exit is referred to as a post condition. Preconditions, invariants, and post conditions together make up the three components of design by contract. And finally, code readability and comprehension is all important while writing good defensive code. Make sure you have meaningful names for your variables and functions. Variable names should represent what that variable holds. Function names should represent what exactly that function does, what action the function performs. Make use of whitespace to separate out the logical portions in your code. Don't squish all of your code together into one block. Make sure the expressions that you use are simplified and use parentheses extensively to specify what computation needs to be performed first. If you have very complex expressions in your code, split them up and store intermediate results. This makes the code readable and easy for others to follow. Make sure that you use comments extensively, especially in the very complex portions of your code. Your comments should not ramble on about irrelevant details. Comments should clarify, not obfuscate. Let's say you want to specify the space time complexity of the algorithm, that should be in a comment. If you want to specify that a function has certain side effects that may not be obvious, please use comments. Let's say for performance reasons, you're using certain hacks in your function. Make sure you comment that. Otherwise, another developer might come in and change the code, and the performance of your code will suffer. Every code base that you work with will have its own code formatting conventions. Make sure your code also fits in and follows those conventions. If you're starting off a new project, remember that C++, Java, Python, all of the high level languages have their own different conventions. Be consistent with the existing code base or make sure you follow the right conventions for a new code base. When you write your comments should not be all about the implementation. Comment at a higher level of abstraction. Comment about what the code does, not how it does it. Assume that the reader is competent and will be able to understand your comments and avoid unnecessary noise words and phrases. Don't obfuscate, clarify. When you're working in C++, it's very important for you to have a good high level understanding of how compiling and linking works in C++. There are certain types of errors that are compiler errors, other errors are linker errors. Understanding these errors will help you track down the error and debug your programs faster. The code that you write in C++ is source code. Before it can become an executable, there are three phases. The first is the pre processing phase, The preprocessor is a very ancient bit of technology in C++. With preprocessing, operations are carried out on the source code, and the source code is updated with all of the information in the header files before the code is sent to compilation. The compilation phase essentially involves converting the source code in the CPP files to machine code. So, the high level source code that you've been writing will be converted to a language that your machine will understand. And finally, we have linking. Linking brings different bits of machine code together to build an executable. All the source code files generated in the compilation phase will be brought together in the linking phase. Here is a visualization of these three phases. We have the source code that we have written, which includes a number of hash directives. Hash includes are part of these preprocessor directives. These hash directives are understood by the preprocessor. The preprocessor will then replace those directives with actual C++ code, and what we get will be preprocessed code. The preprocessed code will not include any hash directives because the compiler does not understand them. Once those hash directives have been removed and we have preprocessed code, that code is still high level code. It's sent through the compilation process, and the compilation process will generate object files, an object file for each of the source files. Now, you might have used a number of different libraries in your code. Your object files will reference those libraries. Those libraries will need to be linked in, and this is done as a part of the linking process. The linking process will bring together all of the libraries referenced by your source code and also the references from one source file to another will be linked together. The output of the linking process is the executable that you will then run. If you've not chosen to build an executable and you want to build a C++ library instead, that will be the final output of the linking process. So either an executable or a library. Let's look at each of these phases in detail because it's very important that we understand what exactly they do. Now, pre-processing are behaviors that are carried out on code before the compilation process. The preprocessor essentially goes through your entire source code looking for preprocessor directives. Any source code that you write which contains the hash prefix is essentially a preprocessor directive. The compiler does not understand those directives, the preprocessor does. The preprocessor will then perform the action based on the directive that you specified. For example, the hash include directive is used to include header files. This specifies code that should be part of the current file, and this code usually contains functions and class definitions. The preprocessor will look at this hash include directive and include the contents of the header files into the current file that it's processing. So the entire contents of the header file will become part of your file. Once the pre-processing phase is complete, all of the preprocessor directives in your source code will have been replaced by actual C++ code. There'll be no more hashes in your code. The output of the preprocessor is then sent along to the compiler, and the compiler is responsible for converting your source code in C++, which is a high level language, to assembly language. Assembly language is what our machine understands. Assembly language is then further converted to actual machine code using a component known as an assembler. The assembler is part of the compiler. At the end of the compilation process, every source file will have a corresponding .o file. So this is the object file with the .o extension, and this contains the machine instructions corresponding to your source code. The machine instructions are now split up in different files, but these different files make up a single executable. And this is taken care of by the linking process. Linking is responsible for bringing together the machine code for different files into a single executable or a single library. If you reference external libraries, such as the standard library or other libraries offered by third parties, linking is where your executable will be linked with the external libraries and frameworks that you've used. The compiler can throw errors, the linker can also throw errors. Linking is where we resolve the dependencies in our code, and if certain dependencies are not able to be resolved, the linker will throw an error and stop linking. The linker will complain if it's unable to find the implementations for the functions that you've invoked or the classes that you've referenced in your code. Let's look at compiling and linking together with this high level view. There is a lot going on here. I'll walk through this step by step. Now, when you write code, you'll set up your function declarations and class declarations in header files. Header files have the .h extension. When you write your source code, if you wish to use functions and classes from libraries, you will include the header files for those libraries. And the header files are included using preprocessor directives, the hash include. The preprocessor will scan all of your CPP files to see which header files need to be included and become a part of your C++ file. That is the role of the preprocessor. Once the preprocessor has completed its job, the output will be sent to the compiler. The compiler will process all of your CPP files and create object files containing machine code instructions. These are the instructions your computer will understand and will be able to execute. And once the compiler has produced machine code, the linker will bring all of the individual components of your project together into a single executable or library that you can then run or use. In this video, we'll quickly discuss the different kinds of errors you'll encounter while writing code. The first thing is, let's talk about what it means to program and debug. Here is a quote by Dijkstra. If debugging is the process of removing software bugs, then programming must be the process of putting them in. And I must say, there are several times when I'm writing code when this is how I feel. If I write more code, there'll just be more bugs. But programming and debugging are basically a part of life. One thing that every software engineer realizes at some point in his or her life is that errors are inevitable. Creating and experiencing different kinds of errors is part of the software development process, and it's something that cannot be short circuited. It cannot be wished away. If you're going to write code, you're going to be introducing bugs, and you need to get good at tracking down these bugs. You need to be comfortable with the idea of errors in your code. You need to understand the different types of errors. You need to be able to catch and fix these errors early. When you first start programming, the kind of error that you'll encounter the most often is the syntax error. Why do these errors occur? Every programming language has its own rules of grammar, and when you violate those rules, that results in a syntax error. You've got the syntax of the program wrong. Now, syntax errors are by far the easiest kind of errors to fix. Syntax errors tend to occur the most often when you're first learning a new language and you're not familiar with the rules of that language. Syntax errors are always caught by the compiler, which means you get early feedback about the syntax errors in your code. So use these compiler errors, use the syntax highlighting present in the IDE or the integrated development environment that you're using to detect and fix these errors. A step beyond syntax errors are compilation errors and semantic errors. We know that compilation is a process that converts our high level source code into low level machine code, one that our computer understands, one that can be run on our machine. Now, errors which are detected by the compiler are usually from parts of your code that the compiler does not understand, is not able to translate. So the compiler doesn't know what you're trying to get at. The most common compiler errors are, of course, syntax errors when you've not followed the rules of grammar for that particular high level programming language, when you've not used the language correctly. But There are also semantic errors that the compiler can understand. Semantic errors are where the compiler is unable to understand what you've expressed in code. The syntax may be correct, but the entire expression does not make sense to the compiler. When you're writing code, once you move beyond the syntax errors and the semantic errors, that's when you'll commit logic errors. These are mistakes made by the programmer where you've coded the logic in your component incorrectly. Logic errors occur when you perform, say, the wrong comparison. You're comparing A and B, but instead you compare C and D. Or instead of multiplication, you perform addition or division. Logic errors cannot be detected using basic tools. It requires human audit and review of your code. Early detection of these logic errors tend to be more likely if you have extensive unit tests and integration tests in your code. So, having these tests are very critical and go a long way towards detecting logic errors. When you develop your code, you're writing code in a development environment. And finally, at some point, your code will be in production. Runtime errors are those errors which were not found during the development phase but suddenly occur in production. Runtime errors can be caused because of some unexpected inputs to a component which were not handled correctly, or unexpected interactions between components, again, which our code did not handle. Runtime errors tend to be pretty difficult to find in many cases because the actual error might occur very far from where the error originated. Runtime errors are detected via extensive testing, unit tests, integration tests, and also using monitoring to check your logs and other performance. If your code performs a lot of numeric computation, you'll encounter arithmetic errors. These are errors in numeric computations in your code, often caused due to unexpected input. You were not expecting a zero, but the user gave you zero. Divide by zero is a very common kind of arithmetic error. If you don't explicitly check for invalid values, you'll get arithmetic errors. You'll get overflowed results, underflowed results. You might end up using the wrong data types. Arithmetic errors are detected by tests that involve edge cases. You'll Rather than just testing your code for a normal range of values, you'll try extreme inputs, very large and very small values to see how your code behaves. Programs in production need resources. These resources can be in the form of memory, compute, files, disk space, network sockets, anything. All of these resources have to be acquired by your program and then released by your program. Now, resource errors might occur when you try to allocate more resources than available. You try to allocate more memory than is available for your program. You try to access a disk or a file that is not accessible. Trying to access these resources might result in some kind of exception being thrown that you then have to handle. Resource errors often tend to be hard to track down because they may not occur in your development environment, but they occur in production. The differences between your development and production environments lead to these errors. Another kind of error that you're likely to encounter is the interface error. This may occur when there is a disconnect between how your components are meant to be used and how they're actually used by the client. The client may end up calling an API with incorrect parameters, with insufficient parameters, with wrong values for parameters. Your code needs to be able to anticipate these wrong inputs and needs to fail gracefully. You also need to return clear error messages to the users of your component. So, clear error messages and good documentation for the API will minimize the occurrence of these interface errors. Before we jump into the demos, where we'll see how we can write good quality, high quality, and defensive C++ code, let's take a look at the environment that we'll be using for all of our demos in this learning path. First, let's take a look at the directory structure where we'll set up the project which will contain all of our code. Within my Mac OS machine, I have a desktop folder, and within the desktop folder, I've created a projects subfolder. It's within this project subfolder that I'll create my VS Code project. But before that, let's ensure that I have a compiler that will compile and build my C++ code. C++ is a language where the source code is compiled to object code. The object code is linked together to give you an executable. There are a number of different compilers out there which allow you to compile and link your C++ code. Now, the compiler that is available by default on the Mac OS is Clang++. And Clang++ is what I'm going to be using for all of the demos in this learning path. Now, if you happen to have another C++ compiler, that's totally fine. You can see here that the Apple Clang version I have installed on my machine is version 11.0.0, and this Apple Clang version supports all features of the C++ release C++ 17. It does not have complete support for C++ 20. If your coding environment is a little different, maybe you're using a different C++ compiler, maybe you're on a Windows machine and you have a Microsoft Visual Studio setup, or you're using some other paid C++ compiler, everything will work well and you should be able to compile and build all of the demos in this learning path using any of these other C++ compilers. I'll have something more to say about the C++ compilers that you can use when we come to the features of C++ 20 that we want to implement, just to play out with them. Not all compilers support all features of C++ 20 at the time of this recording. But that's nothing that you need to worry about right now. At that point, we'll use a site called wandbox.org that allows us to play with different C++ compilers to test out their features or to just run C++ code. Now, writing and developing code in C++ is a lot easier when you use an IDE or an integrated development environment. Now, there are a variety of IDEs there that you can use. If you're used to some other IDE, let's say like Microsoft Visual C++, you're free to choose your own. IDEs are great because they make it easier to write your code, help you spot mistakes early, especially syntax errors, and they also help you organize the files within your project. The IDE I'm going to be using for all of this course is Visual Studio Code. Now, I won't be showing you how I download and install this IDE on my local machine because that's extremely straightforward. Simply follow the links that you see on this page, code.visualstudio.com/download. Once you're here, you'll need to choose the operating system environment that you're working in. If you're using Windows, download the IDE, which is available for Windows 7, 8, and 10. If you're on Linux, you can see that there are install packages for Debian Ubuntu versions as well as Red Hat Fedora and the SUSE versions. Download the right one. Because I'm working on a Mac OS machine, the Mac version of the IDE is the one that I selected, downloaded, and installed on my local machine. Simply follow the install steps available on this page and it will walk you through the installation process. The installation process is fairly simple and pain-free. And here I am with my VS Code IDE opened up on my local machine. This is what the IDE looks like. I'm going to configure this IDE to make it easier for me to set up my project and write code. The first thing I wish to be able to do is to run a command from the prompt on my terminal window and bring up VS Code pointed to my current project. In order to do that, I need to hit Command Shift P on a Windows machine. This will be Control Shift P and this will bring up a list of commands within VS Code. Once you have this window up, simply type shell into that window and you'll see the shell commands that are possible to use with VS Code. Select the option here which says install the code command in path. This will configure the path environment variable on my local machine to enable me to run the command code on my terminal window, and when I run the command code, VS Code will be launched. The ability to launch VS Code from a terminal window is a very useful bit of functionality. So I'm going to go ahead and select this. And you can see here at the bottom right hand side, the shell command code has been successfully installed and configured as a part of my path environment variable. With this done, let's close this VS Code IDE, and I'm going to switch over to my terminal window and set up the project for the demos in this learning path. Here I am back in the desktop projects folder, where I'm going to create a new subfolder which will hold my demos. I use the makedir command to create the subfolder. The name of the subfolder is defensive CPP. Once I hit enter, this folder has been created, and I'm going to verify this by running ls-l. This will list out all of the subfolders or subdirectories in my projects directory. There's exactly one, defensive CPP. That's the one I just created. Let me now cd or change into the defensive CPP subfolder. From here on in, defensive CPP is going to be my current working directory, which will hold all of my C++ files. When I run ls-l here, you can see that this folder is currently empty. I'm now going to open up VS Code using the code command. Code followed by dot sets the current working directory as the main projects directory for VS Code. Running this code command will launch Visual Studio Code. And once that's up and running, you can see on to the top left, the current folder is the defensive CPP folder that we've just created. So this is my project folder. Here is where will exist all of my C++ files, including header files. I won't explore all of the functionality that VS Code has to offer, only the ones that I'm planning to use. You can click on this icon here to create a new file within your project. If you want to create a new subfolder within your project, you can click on this icon which says new folder. That will allow you to create a new folder right within your project. If you want to refresh the files within your project, you can use this refresh explorer icon. And finally, if you have a number of folders open within your current workspace and you want to collapse them, this is the icon that you will select. We now need to configure VS Code to use the Clang++ compiler. And in order to do this, I'm going to click on this new folder button here to create a new folder called .vs code. This .vs code within the VS Code IDE contains a bunch of files for the different configuration settings that you might need for VS Code, including compiler settings. The subfolder defensive C++ is my current workspace, and within this current workspace, I've created a .vs code subfolder. Now, within this VS Code subfolder, make sure you have that selected. Click on the new file button. This will now allow you to create a new file within your .vs code subfolder. This file is going to be called tasks.json. The tasks.json file is where you specify the settings for the C++ compiler that you're going to use. I'm now going to paste in some contents in this tasks.json file. Let's take a look at the compiler settings that we're going to be using to compile our code. Now we have the version of the tasks.json. You can ignore that. Let's take a look at the tasks array where we've specified the compiler settings within an entity. Let's take a look at some of the important features here. On line 7, you can see that the command that will be run to compile our C++ code is clang++. Remember, that is the C++ compiler that I have installed on my machine. If you're working on Windows or some other environment, make sure that this command points to the C++ compiler in your environment. So user bin clang++, that is the command that will be run to compile my code. Then let's take a look at the arguments that we'll pass to clang++. The args field on line 8 is where we specify the command line arguments that we want to pass in to clang++ when it compiles our C++ code. The first argument on line 9 you can see is -std is equal to C++ 17. This basically tells our clang++ compiler compile this C++ code using C++ version 17 features. Now, C++ 17 has been around for a while. It's a robust, well-tested, and fully functional version of C++. It was a major release in the year 2017, and I'll be using many of C++ 17's features in my code. So I want to compile against version 17. The stdlib argument on line 10 tells the compiler that make sure you link in the standard library features. We'll be using the standard library extensively in our code. The standard library is almost a must for C++ development. It'll allow us to use the IO stream classes for input output operations, string classes, collection classes, and so on. Next, we specify what exactly needs to be compiled when I run the command for compilation. On line 12, we can see that I specify the compilation of all of the CPP files within my current workspace, star.cpp. So line 12 is essentially telling VS Code that when I run the command for compilation, make sure you compile and link all of the C++ files in my current workspace. Line 13 will tell us the name of the executable. -o is the flag, and I want the executable to be called a.out. This is on line 14. All of the C++ files in my current workspace will be compiled, linked into a single executable called a.out, and you'll see when I run my C++ code, I'll always run this a.out executable. And finally, just turn your attention to the label on line 6, which says clang++ build active file. This label corresponds to the command that we'll use within VS Code to compile and link our project files. Now that we have the VS Code IDE set up, and we've also set up tasks.json, which contains the configuration settings for the compiler, we are ready to configure our VS Code IDE just a little more so that we get the right syntax highlighting. Essentially, we want to tell our VS Code IDE that we are going to be working with C++ 17 so that it only highlights syntax errors, which are errors in C++ 17. Now, this by default is set to C++ 11. So go to Code, go to Preferences, and then Settings, and click on Settings, and this will give you a chance to configure this setting. Now, on the left-hand side of the settings that we've opened up, you can see a bunch of commonly used settings: text editor, workbench, window, and so on. At the very bottom, we have extensions, and this extensions setting is what you need to expand. The VS Code IDE can be used for C++ and a bunch of other languages, and you can see some of them listed here. You can see that it's used for JavaScript debugging Node.js, for PHP, and so on. Now, C++ is what we're going to be coding in, so select the C option under Extensions. You can see a bunch of settings available for C and C++. You can see that the autocomplete that is used is the default autocomplete. That is good enough. You can also configure some of the other settings that you're interested in, but I'm going to use the search bar to search for the specific settings I want configured. I'm going to type in standard in the search bar. This will filter all of the settings to those that have the word standard. We are interested in configuring the C++ standard for syntax highlighting, and specifically the two settings that you see here at the very bottom, the default CPP standard and the default C standard. I'm going to configure those settings so that they say C++ 17. Now, you might say that this already says C++ 17. Well, that's because I had already configured this earlier. If you've just installed VS Code, this is set to C++ 11 by default, which means all of the C++ 17 features will be incorrectly highlighted as syntax errors. You can take a look at this drop down here and see all of the options that are available. C++ 17 is the right option to pick for all of the demos in this learning path. We'll be writing code in C++ and not in C, but for good measure, I'm going to select C17 from this drop down as well. This is not really required, but just for completeness, I have set this to C17 as well. Now, with this done, you can close the settings dialog. We are all set here. We are ready to run our first C++ program to make sure that everything works. Now, make sure that you do not have the .vs code folder selected. This is so that now when I click on new file to create a new CPP file, I want that file to be created within my top level workspace, within the defensive CPP folder and not within VS Code. Now, this is just going to be a test program that we run to make sure that our environment is set up correctly. And we'll write this code in the main.cpp file. Select main.cpp and let's paste in some C++ code. Now, this is the simplest code possible. We'll simply output hello world to screen. You can see that I have included the header for the IOStream library, which is part of C++'s standard library. This is the code on line 1. #include IOStream allows me to use commands such as cout and cin, which are part of the standard library. Cout outputs messages to the terminal window, and cin allows us to take in user input. Now, from within the IOStream library, I want to use two specific commands, so I have specific using statements for those commands. Once you've included a certain library, you have to specify to C++ what commands from that library you want to use. You can see that I've explicitly specified on line 3 that I want to use the cout command from the std namespace using std, the scope resolution operator, colon, and cout. And then on line 4, I've specified that I want to use endl again from the standard namespace. Now, a way to eliminate this explicit using statements is to simply say using namespace std. I don't really prefer that because then it's hard to see which commands you're interested in from that particular namespace, which particular libraries you're going to use. It's much better to explicitly call out the functions that you're planning to use, as I've done here on lines 3 and 4. The code itself is very straightforward. Within the main function, I've simply printed out to screen hello world. So cout followed by the stream operator, then hello world, the stream operator, and endl, which will add a new line to the end of hello world, and I return 0 for a successful execution of the program. Let's now go ahead and compile this program. You can head over to the menu up top, and within the terminal option, you'll get a drop down and go to run build task. Run build task will use the configuration that you've specified in tasks.json to compile and link your C++ code. Now, Shift Command B is the shortcut for run build task, and from here on in, I'll be using the shortcut rather than the menu option. You can see that I'm presented with a little dialog with an option that says clang++ build active file. If you remember, this was the label in my tasks.json corresponding to the command that I want to execute. This will essentially run the clang++ command to compile my C++ code. Select this option and you'll see that a terminal opens up at the bottom with the compilation output. You can see that the command that was executed to compile this code was user bin clang++. The command line arguments passed in to the compiler was standard equal to C++ 17, standard lib is equal to lib C++, -g followed by the path to my current workspace, and the files that were compiled were all of the CPP files, star.cpp, and the output was placed in a.out. So the executable that I have to run is a.out, and in order to run this executable, I'm going to click on this little plus button here that will bring up another terminal window. This terminal window points to my project's defensive CPP folder, and within this terminal window, if I run an ls-l command, you can see that an executable a.out is present within my defensive CPP folder. Now, this is the executable that I'll run. Now, on a Mac, I need to hit // and the name of the executable in order to run that executable. And that's exactly what I'll do. And there you can see hello world. Clearly, our VS Code has been set up correctly and our first bit of code compiles and runs. An important part of writing defensive code that can defend itself from unwanted inputs, is good coding style. Now, this connection might not be very obvious upfront, But with good coding style, you make your code readable and coherent for other developers on your team. And that is extremely important if you want robust, maintainable code. Now, here in this very simple example, I'm going to show you an example of code that is not readable and not clear and does not follow all of the good coding practices. Let's start off from the very top. The include statements, IOStream and string, that's totally fine. But on line 7, notice that I have specified using namespace std. Now, people often do this, but this is actually not a best practice. It's not a great programming practice because it does not clearly indicate what classes, objects, and commands you're interested in from the standard namespace. You're just blanket importing and specifying that you're going to use anything from the standard namespace. It's much better to explicitly specify what you use. Next, let's take a look at the function that I have defined called compute1. This is on line 11. Now, the problem with this particular function definition and declaration is the fact that it's not meaningful. Compute1 doesn't really tell me what exactly this function is trying to compute. Now, there is a helpful comment there, but if you've made the name of your function meaningful, that comment is not really needed. You can see the comment says compute the total income by adding the salary, stocks, and rental incomes. Rather than that, you could have just named the function so that anyone just reading the function would have figured out what it does. Next, turn your attention to the input arguments passed in to this compute1 function. This is on line 11. Double DBS, float FPS, float FPR. The prefix DB is used for doubles, FP for floating point values. This is the Hungarian notation, and because C++ is a statically typed language, it's strongly typed, you really do not need to use Hungarian notation in your code unless this is legacy code and you're trying to fit in. If you're working in a project that already uses the Hungarian notation, which uses prefix to specify the types of the variables, well, that's fine. There's nothing you can do about that. But if you're starting afresh, make sure that you don't use the Hungarian notation. It unnecessarily makes things harder to read. You can just use meaningful variables. The C++ compiler is strongly typed and it will check that the types you pass in are correct. Now on line 12, I simply return the sum of these three income streams. That's totally fine. Next, on line 16, I have a compute to function. Once again, this function tells me nothing about what's exactly being computed. I have to read the comments associated with the function. Also, if you look at the input arguments, I have a floating point M and a long LF. Hungarian notation, just harder to understand what these input arguments represented. Mortgage and food expenses, well, that's fine. The comments are helpful but unnecessary. These comments would not have been needed if you're given your functions meaningful names. Next, let's take a look at our main method. Now, the first thing that should jump out at you here is the lack of white space. There's a lot of stuff going on here, but we haven't really used white space to improve code readability. We've simply scrunched or bunched up all of our code, making it very hard to read. Let's take a look at what this code does. I have defined variables on lines 21, 22, and 23. I have DB salary, three floating point variables, and a single long variable. These variables will allow us to accept input from the user that we'll then store in these variables. These variables once again use the Hungarian notation, not really needed. Also observe that on line 22, I have declared multiple floating point variables on the same line. In this particular situation, that's fine, but that's generally not recommended. Next, I print out a bunch of statements asking for input from the user: salary income, stocks income, rent income. I then have cin commands to accept input from the user into the DB salary, FP stocks, and FP rent variables. So on lines 24 through 29, I've accepted values for all of the streams of income for a particular user. I then have a horizontal line using cout on line 30. I then take in mortgage expenses and food expenses. The code is all bunched up, very hard to read. Once I have all of this information on line 36 and 37, I call compute 1 to compute the sum of all of the streams of income, and compute 2 to compute the sum of all of the expenditures for a particular individual. Now, because we've said compute 1, compute 2, this particular line of code, which is not commented, doesn't tell me what the code is doing, which is a major no-no. It's very hard for another developer to maintain this code because they'll have no idea what's going on unless they look at the function definitions for compute 1 and compute 2. Well, leaving that aside, there are no spaces. I then store dbi minus dbe into the variable s. Now, these variables could have been much more meaningful. It could have been savings equal to income minus expenses. But no, our variables are short and terse. I then construct a string with the result of this computation, which gives me what my savings are, and then I print this string out to the console output on line 41. This is our code. Now, there is nothing wrong with the code. I'm going to go ahead and compile this particular file. And once the file has been compiled, I'm going to run it using ./a.out. And we'll specify some input and see what the result is. My salary income is $100,000. Stocks income is $20,000. Rental income is $13,000. Mortgage expenses are $45,000. Food expenses $12,000. My savings work out to a total of $76,000. This code runs just fine. There is nothing intrinsically wrong with the code that we've written, except that it's unreadable and unmaintainable. Let's see if we can do a little better. I'm going to update this very same code. So logically, this code does exactly the same thing, but let's turn our attention to how it's organized. On lines 4 through 8, you can see using statements for all of the specific commands that we want to use from the standard library. Standard : C out, C in, endl, string, and toString. This immediately tells any other developer on our team that these are the specific commands that I want from the standard namespace. You're not simply using the entire namespace. This is a good practice to follow to give a message to other developers of this particular bit of code to indicate what exactly you're using. Next, let's take a look at the function that we have defined on line 10, compute total income. Now, because the name of the function is meaningful, I don't really need additional documentation for the function because the function's name itself tells us the whole story. The input arguments to the function are also well named. They do not follow the Hungarian notation. We'll rely on C++ type safety for that. Salary, stocks, rent makes it very clear that income is computed by taking in all of these income streams. Next, we have the function on line 14, compute total expenses. Also very clear. The expenses are mortgage and food. And the total expenses are just the sum of these two expenses. Again, very straightforward, no unnecessary comments needed. And you can see that we've used new lines to space out these function definitions. Now, let's move on to the main code. You can see that the main function here is much longer, but that's not because we've written more code. We've just included more new lines. On lines 20 through 22, I have all of the variables for the income streams. Observe that rather than using the Hungarian notation to specify the type of the variable, I have made the variable names meaningful. They have the income prefix. Similarly, on lines 24 and 25, I have the variables for expenses with the expenses prefix. On lines 27 through 34, I use cin statements to read in the income stream values. On lines 38 through 42, I read in values for mortgage and food expenses. On lines 44 and 45, I compute the total income and the total expenses. Observe how anyone just looking at this code knows exactly what we are doing on lines 44 and 45. There is no commenting required. We store the total income and total expenses in meaningful variables. And on line 47, I compute savings using a variable named savings, total income minus total expenses. You can see that this code is almost like English. I then print out my savings out to screen on line 52. Let's go ahead and compile this code and then run the executable that is generated. The code is exactly the same. Once I run a.out, it will ask me for the values of my income. Here is my salary income, $100,000, stocks, 23,000, rental income, 15,000, mortgage expenses, 45,000, food expenses, 13,000, which gives me a savings of $80,000 a year. Defensive coding practices also involve following sound software engineering principles when you write your code. In earlier videos, we've discussed some good practices to follow within software engineering. When you follow these good practices, it makes it much harder for someone using your code to get things wrong, and that is in some ways defensive programming. Let's take a look at some code where we've violated some of the good software engineering principles, and you can see how difficult it is to work with such code. You can see that the clients of such code basically find it very hard to use your code correctly. Let's take a look at the example and I'll explain some of the principles that are violated as we discuss this. I've defined a C++ class here called bank account, and this is an extremely simple class. Imagine that it represents an account that you'd open at a bank. Maybe it's a savings account. Now, the only private members that this class has is an account ID and a floating balance. And you can make deposits and withdrawals to this account, and every deposit and every withdrawal is accompanied by a service charge. Now, this class represents a bank account, and you can see some of the public methods that we have in this bank account. On line 13, we have the constructor for this bank account that takes in an account ID and the balance, the opening balance for the bank account. And then on lines 15 through 17, I have methods that allow withdrawals by check, cash, and electronically. On lines 19 through 21, I have methods that allow me to make deposits to my bank account. Deposits can be made by check, cash, and electronically. And finally, each of these kinds of withdrawals and deposits incur service charges. And on lines 23 through 25, I have methods that deduct the right service charges for the different types of transactions. We have service charges for check transactions, cash transactions, and electronic transactions. Now, immediately, this header file, which gives us what methods are available in the bank account object, has several red flags. The most glaring red flag is the fact that deducting service charges is not internal to the bank account. It's a public method, which means clients have to explicitly remember to deduct service charges after every transaction. Now, this means you're not minimizing the responsibility of the client. You have essentially told the client it's your responsibility to take care of service charges, not mine. So, the principle of minimizing the client's responsibilities, that has been violated. Because we've made it the responsibility of the client to deduct service charges, rather than have the bank account do this behind the scenes, we have not minimized the client's responsibilities. And this has also broken the principle of encapsulation. We haven't encapsulated the idea of service charges within the bank account. Instead, we've exposed it to the client. We're clearly not off to a good start here, but we'll fix all of this before we are done with this demo. Now, before I move on from this .h file, let me just turn your attention to this Pragma once directive on line 1. This is a preprocessor directive in C++, which basically tells the preprocessor that if this header file is included more than once in any code, make sure that you include it exactly once. And this Pragma once directive is extremely useful in preventing multiple header files inclusion errors. It's useful to have this directive in every header file. Let's now head over to our implementation of the bank account in the bank account.cpp file. Observe on line 1, I include bank account.h. This include is in quotes, indicating that bank account.h is part of my current project. On lines 8 through 12, I have the constructor for the bank account that takes in the account ID and the balance. I have the initialization list on line 9, which initializes the account ID and balance member variables to the input arguments passed in. Now, each time I construct an object, I print out the starting balance. This is on line 11. Then on line 14, I have the implementation for withdraw by check. I take in the amount as an input argument. If the amount is less than or equal to the balance, only then do I allow the withdrawal. This is a form of defensive programming, checking your input arguments before you use them. But we won't focus on that at this point in time. This is something we've done right. If amount is less than or equal to balance, we subtract the amount and we specify the amount that we have left in our bank account. And we return true if the amount was withdrawn, otherwise, we return false. Withdraw by cash has essentially the exact same code. If amount is less than equal to balance, we subtract the amount from the balance, print out how much we've withdrawn and our current balance. This is on line 30, and we return true if the withdrawal was successful. Otherwise, we return false on line 35. If you scroll further down, you'll see another method for withdraw electronically, which essentially has the exact same code as the two previous methods. Only the cout statement on line 42 is different. The software engineering principle violated here is don't repeat yourself, or DRY. We haven't refactored the repetitive code in our code base, which means that maintaining this code base is going to be a nightmare. Take my word for it. On line 39, we check amount is less than equal to balance. We subtract the amount from balance, and everything else is the same. Take a look at the three deposit methods as well. These are defined on lines 50, 56, and 62. Deposit by check, deposit by cash, and deposit electronically. And you can see that the code within these three methods are also exactly the same. We simply add the amount passed in to the current balance. Now we have repetitive code. That is another software engineering principle that we have violated. We have basically repeated the exact same code in all of the withdraw methods and all of the deposit methods. And the repetitive code doesn't really stop there. If you look at the three deduct service charge methods defined on lines 68, 74, and 80, you can see that we have very similar code within each of these methods. On line 69, 75, and 81, you can see that the service charges for a check transaction, a cash transaction, and electronic transaction are all different, but the essence of the code is the same. This is also an example of repetitive code. Now, we have all of these flaws in this particular bank account definition. Let's take a look at our main.cpp file, and you'll find that the code actually works correctly. There is nothing wrong with our code, logically speaking. On line 10, I've created an object representing the bank account for Alice. Alice123 is the account number, $100 is the starting balance. On line 12, I've basically deposited a $100 check, but as the client of this bank account, I have to deduct the service charge for the check transaction myself. You can see that I obediently do this on line 13, but what if the client were to forget? There is no check against a client forgetting here. On line 15, I deposit $300 electronically, and then again on line 16, I deduct the service charge for an electronic transaction. On line 18, I have to explicitly check my withdrawal of $50 to see whether it's successful. If it is successful, I deduct the service charge for withdrawing by cash. This is on line 19. On line 22, I withdraw by cash, once again $500, and deduct the service charge for a cash transaction if this withdrawal was successful. So you can see that it's very painful for a client to work with this code, but everything works as expected because the client has accepted the responsibility and done the right thing in every case. Now let's go ahead and run this code, and the output here is correct. The starting balance is 100. We have deposits and withdrawals. The final balance is $446.50. Now, all of this is perfectly fine. Well, in the previous video, we saw some really egregious violations of sound software engineering principles. In this video, we'll attempt to rectify them and improve our code. Here we are in an updated bank account.h file. The first thing you should observe is that I have converted all of the service charge related methods to be private. On lines 12 through 14, you can see that deduct service charge for check, cash, and electronic transactions are all now private methods, which means that clients of our bank account class will not have to worry about those methods. They're internal methods to be used by the bank account class itself. This one change will fix two violations of software engineering principles. We will ensure that client responsibility is minimized, and we'll also ensure that our bank account class is encapsulated. Internal mechanics of the bank account class, such as the presence of service charges and what they are not exposed to clients. So, this is great. This is a step in the correct direction. You can see amongst the public methods, we still have the constructor, that's totally fine. On lines 19 through 21, we have three methods for withdraw by check, by cash, and electronically. And on lines 23 through 25, we have three methods for deposit by check, by cash, and electronically. Now, this still gives off a code smell. Why do we have three different methods? This makes me feel that the code within these methods is still repeated. Let's head over to bankaccount.cpp and take a look. We have the constructor on lines 8 through 12, no change there, and nothing really needs to change there. The constructor is perfectly fine. We have the withdraw by check on line 14. Once again, we have the code to basically check whether the amount is greater than balance, and then we perform the withdrawal. The one change, the improvement that we've made to this bit of code is that each time we actually withdraw the amount from our bank balance, we deduct the service charge for a check transaction. On line 18, you can see that withdraw by check under the hood invokes the deduct service charge check transaction. So we've essentially removed from the client the responsibility of deducting service charges. So this is a great step forward in minimizing client responsibilities. But the code is still repetitive. I have withdraw by cash and withdraw electronically defined on lines 28 and 42 respectively. You can see that the same code or very similar code to the withdraw by check that we saw earlier is present here in these methods. But each of these methods take care of deducting their own service charges. That is, like I said, a step forward. On line 32, you can see that within withdraw by cash, when we deduct the amount from the balance, we also deduct the service charge for a cash transaction. And on line 46, when we withdraw the amount electronically, we also deduct the service charge for an electronic transaction. So things are looking better, but they're not great. The same improvement is present in the deposit methods on lines 56, 64, and 72. You can see we've defined the three methods: deposit by check, deposit by cash, and deposit electronically. On lines 59, 67, and 75, we invoke the corresponding deduct service charge methods to deduct the right service charge for these different types of deposit transactions. So the repetitive code still continues here in the deduct service charge methods defined on lines 80, 84, and 88. They are self-explanatory, the same as before, but these are private methods and not public. That's an improvement. When you head over to main.cpp, you'll see how our code has improved thanks to our following the principle of minimizing client responsibility. It's no longer up to the client to remember to deduct service charges for the different transactions. That is done automatically by the bank account, which means clients have to write simpler code. Clients are more likely to get their code correct. So we initialize the Alice bank account on line 10, deposit $100 by check on line 12, deposit $300 electronically on line 14. I withdraw $50 on line 16. I don't check the return value to see if that amount was successfully withdrawn. I try to withdraw $500 on line 18. I check the return value and print out insufficient balance if the withdrawal was not successful. Let's go ahead and compile this code and then run it. The compilation seems to have gone through successfully. And when I execute a.out, you see that things look good. You can see the insufficient balance printed out at the very end when we try to withdraw $500. Now things look good. Our code has improved, but we can improve our code further. So let's head back to bankaccount.h and make a few changes. I really want to get rid of all of the repetitive code that I have in the withdraw and deposit methods. I want to follow the principle don't repeat yourself. A great way to accomplish this is to basically have the same code for all kinds of withdrawals and deposits and just tweak your code a little bit based on the type of transaction. And in order to flag the different types of transactions, I have introduced an enumeration or an enum indicating the type of transaction that the client wants. This enum is defined here on lines 6 through 10. This is an enum class, that is the modern way of defining an enum in C++. It has major advantages over the old enum keyword. The use of the enum class keyword to define the transaction type enum rather than just the plain enum keyword makes this a scoped enumeration. Scoped enumerations are a C++ feature that was introduced in C++ 11, and they have several advantages over traditional enumerations. Scoped enumerations are strongly typed as well as strongly scoped. When I say strongly typed, I mean that if you have a scoped enumeration, you cannot pass in an integer value in place of the enumeration. Enum values are mapped to integers under the hood, but that's an implementation detail. So you cannot specify the integer 0 to represent check, 1 for cash, and 2 for electronic. You have to convert that integer to be of type transaction type when you work with these scoped enumerations. Scoped enumerations are also strongly scoped, meaning the values that you assign to this enumeration will not conflict with other scoped enumerations that you have within the same namespace. So if the value of 0 corresponds to transaction type check, the same value can be assigned to a different scoped enumeration as well. So this is a major advantage. So we have transaction type, which is a scoped enum, and the values are check, cash, and electronic. And you can see within our bank account class, we've really minimized the number of public methods. And we've also reduced all of our service charge methods to a single private method called deduct service charge, defined on line 18. Deduct service charge simply takes in a transaction type and deducts the right service charge based on the type of transaction. Then within the public methods, we just have two methods, withdraw and deposit. Each of them take in a transaction type as an input argument and the amount you want to withdraw or deposit. Notice how much cleaner we've made this bank account interface. It's so much easier for the client to use. We've in fact further minimized client responsibilities. Let's take a look at the implementation of the bank account and you'll see major improvements there. You can see we have implementations of just three methods and a constructor. I have the deduct service charge, which based on the type of transaction deducts the right service charge. $2 for check, $1 for cash, and 50 cents for an electronic transaction. We've also refactored the code in both the withdraw as well as the deposit methods. There is just one withdraw method which takes in the transaction type, and the transaction type is essentially for deducting the right service charge. The rest of the code for amount withdrawal is the same, and we haven't repeated this code. There is just one implementation of this code. We invoke deduct service charge on line 29 and pass in the transaction type. Within deposit, once again, the code is exactly the same. We invoke deduct service charge on line 42 and pass in the transaction type. The main.cpp file here contains the client code for working with the bank account. We create a bank account for Alice on line 10. We invoke deposit twice on lines 12 and 14. We deposit $100 and $300, and each time we specify the type of transaction, check and then electronic. I perform a withdrawal of $50 on line 16. and then I attempt to withdraw $500, that's going to fail. Both of these are cash transactions. So the client also has a more meaningful way to interact with our API thanks to our use of scoped enums. Each time the client performs a transaction, instead of passing indices around or making sure the right method is called, it simply specifies the right transaction type. Here, the interesting details were in how we structured our code to follow good software engineering practices. When we run this code, the output is as we would expect. In an earlier video, we've discussed the different kinds of errors that you can encounter in a C++ program. In this demo, we'll actually see some examples of those errors, and we'll discuss exactly what you can do to fix those errors once you encounter them. We'll start off by looking at a few compile time errors. But before we get to the errors, let's look at our code correctly set up. Here I have a very simple calculator application. Here is my header file calculator.h. Observe the Pragma once on line 1. The header files simply specify the declarations of the methods that I'm going to define in a CPP file. The header file is for telling me what methods exist, and this header file is what I'll include in my client program. You can see that there are exactly 4 functions that my calculator app supports. We have add, subtract, multiply, and divide. And only the declarations of those functions are present here in this calculator.h header file. Add takes in 2 values, a double A and a double B, and the same 2 input arguments are passed in to subtract, multiply, as well as divide, and all 4 functions return a double value as their result. So this is my header file definition. Next, let's take a look at the CPP file where we'll specify implementations for all of these functions. The calculator.cpp file contains the definitions of the methods that I had declared in the header. So we have the add, subtract, multiply, and divide. You can see that add takes in A and B and returns A plus B. Subtract takes in A and B and returns A minus B. Multiply multiplies A by B, and divide returns the result, that is A divided by B. You can see that our CPP file contains an include for calculator.h. The use of the quotes indicates that this header file is part of my current project, and that's where my compiler should look for this header file in the current project, not as a part of some library that has been linked in. It's common practice to always include the header file where the functions have been declared into the CPP file where the functions are finally defined, where the implementations of the functions exist. Now, let's take a look at the main.cpp file, which contains the code that will use this calculator. You can see from the include statements that we include iostream from the standard library and calculator.h. The code in main is very straightforward. On line 9, we invoke the add function to add 10 and 25. On line 11, we invoke subtract to subtract 2345 from 1034.5. On line 13, we multiply 1234 by 100, and on line 15, we divide 189.234 by 100. Now, how does the compiler know where to find the methods add, subtract, multiply, and divide? Well, it'll look at the header files. Specifically, it'll find the declarations of these functions in the calculator.h file. The compiler will be happy with those declarations. The linker will then link in the definitions from calculator.cpp. Let's go ahead and compile this code, and you can see that there are absolutely no errors in the compilation. This is the first hurdle that we need to cross while writing C++ code. Our compiler or compilation process needs to succeed, and ours has. But this does not mean that code is correct or will run without errors. In this particular case, our code has run through successfully. You can see that the result of our add, subtract, multiply, and divide operations have been printed out to screen, and all of the results are correct, what we would expect. Now, let's introduce some compile time errors and ensure that the compiler indeed warns us. Now, compile time errors are syntactic errors. I've placed my cursor on line 11 and I'm going to press the backspace button to get rid of the semicolon here. Now, the C++ rule is that every statement should end with a semicolon, and I have violated this grammatical rule. This is a syntax error, and the compiler should warn me about this. There is no semicolon at the end of line 11. I'm now going to compile my code, and just as I'm about to compile my code, you can see that syntax highlighting kicks in, and you can see this red squiggly line under cout on line 13. Now, the error that I've introduced is on line 11, but the next line of code is what is highlighted. Basically, there is something wrong around that area. Let's compile our code, and from the output generated, you can see that we have a compile time error, and the compile time error is actually very clear. Expected semicolon after expression, and it points to exactly where the semicolon is expected. There's a little green arrow right after endl. That's where you need to put in the semicolon. Now, not all compile time errors are as straightforward or as easy to fix. Leaving out a semicolon is by far the easiest of all errors for you to commit, and the fix is also easy. So let's put the semicolon back as I've done so. Our main.cpp file at the end of line 11 has its semicolon back. I'm now going to switch over to calculator.cpp and get rid of the semicolon on line 12 here. So all of your CPP and header files will be checked for correct syntax. So calculator.cpp is also compiled, and you can see I get the same error, expected semicolon after return statement, now within calculator.cpp, and the exact line number is indicated as well. VS Code has also flagged our syntax error. If you hover over the red squiggly there, it'll tell you what the error is. So the IDE is extremely useful for these syntax errors. Now let's put the semicolon back on line 12 of calculator.cpp, and let's head over to main.cpp, where I'm now going to set up another syntax error. I've commented out the using statement for std C out. Now, this means that our code here does not know where the cout command comes from. You've included the IOStream package on line 1, that's where cout is defined, but you haven't told the compiler that you're using the std namespace and specifically cout within that namespace. Cout is not in the global namespace, it's in the std or standard namespace. The compiler doesn't know where to find cout, and that's why when you compile this code, you get all these errors. This can happen for classes in the standard library or in your own library. But in the standard library, the error message that you get from your compiler is often more meaningful. You can see that our compiler considers cout an undeclared identifier. It wasn't declared anywhere that the compiler could find because we didn't ask the compiler to look in the std or the standard namespace. But the compiler also knows that cout is part of the standard library, and it asks us, did you mean std : cout? That's a hint to us. The compiler is your friend. This hint is a good one. So I'm going to listen to my friend here. I'm going to uncomment line 4 using std : cout. But now I'm going to comment out line 2. Let's see what happens if you forget to include the header file for a function that you're invoking or a library that you're using, or a header file that contains the declaration of an object that you want to use in your code. Now, calculator.h contains the declarations for add, subtract, multiply, and divide. Now, VS Code has figured out that it has no valid declarations for these methods, and that is why add, subtract, multiply, and divide now have red squigglies under them. The IDE is trying to tell us that, well, you've invoked these functions, you expect that they exist, but I can't really find them. Where are the definitions and declarations for add, subtract, multiply, and divide? I can't find them. And when you compile this code, the compiler tells you the same thing. Here are the compiler errors. Use of the undeclared identifier add. The compiler is telling us that it has no idea what add, subtract, and multiply and divide mean. So that's something we need to fix. We can simply uncomment calculator.h and that will fix the error for us. But now I'm going to introduce another compiler error. I'm going to head over to calculator.h and I'm going to get rid of the declarations of add and subtract. So I have highlighted add and subtract here and I have deleted them. So I only have declarations for multiply and divide, but no declarations for add and subtract. If you look at the calculator.cpp file though, you'll find that we do have the definitions of add and subtract. So add and subtract are defined here in this CPP file, but their declarations have been removed. And this is also a compile time error. We've included calculator.h here in our main.cpp file. When we try to compile main, the compiler will look in the header files included in main.cpp to find declarations for add, subtract, multiply, and divide. Multiply and divide have been found, but you can see on lines 9 and 11 that add and subtract were not found. Well, that's because of us. We've gotten rid of the declarations in calculator.h. The calculator.h basically says, you know what? I don't know about add and subtract, and we've tried to invoke them within main.cpp, and that gives rise to this undeclared identifier error. Functions cannot be invoked unless they are declared, and the declaration is not found in all of the header files that we included in main.cpp. So I'm going to put back the declarations of add and subtract in preparation for the next video where we look at linker errors, runtime errors, and logic errors. Our calculator.h file here once again contains the declarations for all four methods add, subtract, multiply, and divide. I'm now going to head over to calculator.cpp and make a few changes. I'll comment out the implementations of the add method and the divide method. So essentially, I'm not defining implementations for add and divide, but I have declared these methods in the calculator.h file. Now let's see what kind of an error it is if we try to compile and run this code. Here is the main.cpp file. Ignore the squigglies under add and subtract. The IDE has not yet caught up with the new changes that we've made. Now everything looks good. We're invoking add, subtract, multiply, and divide, and we've also included calculator.h. Let's go ahead and compile this code, and this time around you can see that the error in the console output looks a little different. That's because this time around the error is a linker error and not a compiler error. How do I know it's a linker error? Just next to error in the console output, you can see that the linker command failed with exit code 1. This shows that the error that we get this time around comes from the linker and not from the compiler. Basically, the compiler has no problem at all with our code. Our compiler is happy because we have specified the declarations of add, subtract, multiply, and divide in calculator.h. Unfortunately, add and divide haven't been implemented, and to find the implementations of the methods that have been declared is the job of the linker. The compiler is happy. It found the declarations of the methods and it just assumes that the linker will be successful in finding the definitions or implementations of the methods that have been declared. But unfortunately, after the compile process was complete, when the linker tried to link in the various bits of code in our project to build a final executable, that's where the failure was. The linker message is quite clear. Undefined symbols for add and divide. You can see that in the console output. These symbols or functions have not been defined even though they have been declared in the header file. So the linker error tells us that the definitions are missing, which means we need to head over to calculator.cpp and I'm going to basically uncomment add and comment out multiply. Now, I have specified an implementation for the add function, but I have gotten rid of the implementation for multiply and divide also is not present. This time around, when I compile my code, you can see that it's once again a linker error and the linker clearly tells me that it wasn't able to find symbols for divide as well as multiply. And this leads us to something important. You need to be able to differentiate between compiler errors and linker errors. A linker will tell you when the implementation for a particular symbol has not been found. The compiler will tell you when the symbol itself cannot be found. So make sure you keep this in mind when you're debugging your programs, when you're looking at errors in your programs. Let's go ahead and fix this linker error by uncommenting the implementation of multiply and divide. We know that our header file contains declarations for all four functions. I'm going to uncomment the implementation so that we have implementations for all four functions as well. I'm now going to head over to the main.cpp file and introduce some runtime errors in my code and show you what these runtime errors look like. I have an invocation to the divide function here where I divide 189.234 by 100. Instead of dividing by 100, I'm now going to divide by 0. And divide by 0 is a runtime error. It is a runtime error because it has to do with invalid values that you pass into the function. And this is something that we'll only know at runtime. When we run our code, the compiler and the linker cannot help us with this error. So let's go ahead and compile our code. And you can see that the compile was successful. Don't be misled by the linker error that you see on screen. That's the previous output. The output that I have highlighted here in gray is the output for the current program. And you can see that we have compiled our code and there are absolutely no warnings. Things look good so far. Now we'll go ahead and try and run this executable a.out. And there you see it. Divide 189.234 by 100, but we've actually divided by 0. And that's why we get infinity as the output. The INF at the output indicate that some mathematical operation has resulted in an undefined infinite value. And this is an example of a runtime error. Let's see an example of another runtime error. So I'm going to fix my divide function. I'll go back to dividing by 100, but I'm going to change my multiply function to introduce a runtime error. This time around, I'm going to multiply two extremely large numbers. 123 multiplied by 10 to the power 200. That's the first number, 123e 200. The second number, which will be multiplied by the first, is 10 to the power 200, 1e 200. Every numeric data type in C++ has a certain capacity. If you try to place a value into a variable of a certain data type that exceeds the numeric capacity of that data type, that results in an overflow, and that is another example of a runtime error. Double values can hold a maximum of 10 to the power 308, roughly. Now, 10 to the power 200, that's perfectly within the double limits, but when we multiply the two, we'll get 10 to the power 400, which is beyond the numeric capacity of a double variable. That is the return type of multiply. Now, when we compile this code, everything will compile fine. It's only when we run this code that we'll encounter the error. Notice that the multiply operation results in an infinite value. That's because the result of the multiplication has overflowed the capacity of the double. This is an overflow error. Those were examples of runtime errors. Let's now fix our main.cpp, fix the runtime error, and let's head over to calculator.cpp where we'll introduce a logic error. A logic error is when there is something wrong in the code that you've written. Let's say within your multiply operation, you add a and b. So you specify a plus b instead of a multiplied by b as we've done here on line 12 of our calculator.cpp file. Well, this is an example of a logic error. The compiler and the linker and no tool can help you with logic errors. It's only by debugging and getting to the root of any error that you'll be able to figure out logic errors. We'll compile our code. Everything looks good here. Let's go ahead and run a.out. When you run this, you'll see that multiply 1, 2, 3, 4 and 100 gives you 1334. That is clearly wrong. That is a logic error that is present in our code. Logic errors are essentially found out only by debugging your code, writing unit tests, and maintaining those unit tests. With this demo, we come to the very end of this course on software engineering principles and types of errors. We started this course off by discussing important software engineering principles that allow us to write robust, maintainable, and scalable software. We discussed the importance of keeping your code simple and understandable, the idea of implementing functionality only when you absolutely need it, avoiding premature optimization, and the importance of refactoring your code to have common utilities in a single place. We then got a big picture understanding of how code in C++ is pre processed, compiled, and then linked together to give us the final executable or library. We set up and configured the VS Code IDE on our local machine in order to write code in C++. We explored some code which violated software readability and sound engineering principles and looked at ways we could improve such code. We rounded this course off by exploring the different kinds of errors that you might encounter in code, including compiler errors, linker errors, runtime errors, and logic errors. Now that you have a good understanding of how good code is written and the kinds of errors that you encounter in code, you are set up to tackle the next course in this learning path: defensive programming and defensive design, where you will learn how these practices and principles help you write code which continues to function even in the presence of unexpected events. We've discussed earlier that defensive programming is intended to ensure the continuing function of your program or software under unforeseen circumstances, unforeseen inputs. Now, defensive programming is really needed because of Murphy's Law. Anything that can go wrong will go wrong. Whatever software you write, whether it's a backend server, an application, a mobile app, anything, it'll never be functioning under the most ideal of circumstances. Something will always be wrong, either with the user input or the hardware that it's running on. You have to be able to handle it. It's important that you realize that defensive programming is about defending your internal software against external influences. Let's take a look at this visualization to understand where exactly you'll put in all of your defensive code. Here we have a piece of software which will interact with external third parties. These external influences include hardware that the program is running on, third party libraries or applications, user input, external components that you communicate with using communication stacks. Now, once you have external influences in your code, and this is pretty much unavoidable, you need to have a defensive programming barrier to protect against what can go wrong with these external influences. If your code is all internal, you don't really need this defensive programming barrier. For internal software, in fact, you should use offensive programming, and we'll discuss that later on in this learning path. For internal software, use asserts liberally to track down bugs early. But with external software, make sure you have this defensive programming barrier. So, what are the things you need to defend your code from? Well, inputs given to your code by the user or by other components could be incorrect or invalid. The operations performed by your code or other components it interacts with could be incorrect or invalid. Your code might encounter system issues and internal errors. And well, you also need to defend your code from other developers on the team so that they don't inadvertently change something and misconfigure your code. So, how do you defend yourself against invalid or incorrect inputs? Validate every input before you actually use them in your computation. These validations can include range checks, length checks, non null checks. This validation should occur as soon as the input is received because this prevents simple errors from becoming more complex system failures. Do not allow the erroneous input to propagate through your system. There are a number of ways you could report errors. You could maybe return an error code, return an error value, or throw exceptions. In order to ensure that your code does not perform invalid operations, it's first necessary to ensure that your inputs are correct and validated. Make sure you have extensive unit tests to ensure the logical correctness of your code, that the logic is correct, it produces the expected output. Make sure you add logging to your code and make use of error messages. This will allow you to monitor your solutions in a production environment. Your code may be correct, but you may have to deal with system issues, hardware failures, network failures, and so on. You can protect against these by adding invariant checks for operations. Make sure that the end of a method has the updated result that you expect. You manage and handle exceptions in code to look for failures proactively. Make sure you're monitoring your resources and code in a production environment. Other developers on your team may have no malicious intent, but if your code is not clean and maintainable, inadvertently they might do the wrong thing. Make sure you're expressing the intent in your code via the code itself, how it's structured, and via the commands that you've added. This will help newbie developers as well as experienced developers. Let's quickly summarize some of the defensive techniques that you can follow. Make sure that you're writing predictable code. Your code should follow the principle of least astonishment and should not have unexpected side effects. Your code should be consistent or certain. If it promises to do something, it should definitely complete its action and fulfill its promise. Make sure your code is complete. You're not writing half functions which do half the job and doesn't do the rest. Make sure your code fails fast or fails early. It doesn't propagate errors through the system. And finally, make sure that you're proactively looking for places where errors might occur and handling those errors and exceptions in your code. Writing predictable code is about following the software engineering principle of least astonishment. Components should behave as users expect them to and should not have unforeseen side effects, should not change something that is unexpected. Make sure you reveal your intention through API names, the parameter names, the documentation, and the return values. Do not allow execution of your code with wrong inputs. For your code to be consistent and certain, your inputs need to be validated. Only accept valid inputs so that your program behaves in the same manner each time it's executed. Do not accept conditional inputs where the execution changes based on a flag that you pass in. That makes it very complex for a user to understand. Consistent code also requires that your failures should be predictable and consistent. So don't fail under different kinds of circumstances each time. Make sure the conditions of failure are clear. Make sure that you return clear error messages so that users can fix the problem. Complete code involves thinking of all of the conditions that your code has to handle, anticipate all of these conditions and the possible inputs from the user, and make sure you write code to handle these conditions. Every branch of your operation should be thought through and complete. Failing fast and failing early is extremely important. Any errors which are propagated through the system become more complex errors and harder to track down. So, check for irrecoverable errors first and do not execute your code at all if these errors exist. What if the inputs that you have are wrong and you end up executing something that cannot be reversed? You're in trouble then. So, make sure that you're not failing too slowly. And finally, make sure you're liberally using preconditions, invariant checks, and postcondition checks. Preconditions ensure that your inputs are valid, invariants help track down side effects, and postconditions ensure that your code does what it's supposed to. So, when you use assertions for invariants, you can assert that things should happen at this place. You can also assert when things should not happen. Asserting when things should not happen is what will help you catch potential side effects and make sure you're reporting errors in the right manner via error codes, exceptions, status codes, and so on. The defensive programming techniques that we discussed in the earlier video are an integral part of defensive design. Defensive design involves planning for contingencies up front. We know that Murphy's Law says that anything that can go wrong will go wrong. So plan for these contingencies at the design stage of a project or undertaking. It's not just while writing code that you need to think of defensive techniques. While designing your components, you need to think of what can go wrong. Whatever API you're writing, whatever component you're writing, anticipate the misuse of that component. Expect that users will not use it the way that it's intended. If you've planned ahead for what can go wrong and how exactly the error should be handled and reported, well, you've defended yourself against users and external third parties. Anticipating and planning requires you to be proactive rather than reactive. Once you've anticipated your problems, make sure the code that you write is maintainable and written in such a way that it's easy to diagnose issues if they arise, and arise they will. And finally, test your programs early and often. Having automated tests that run on every check in, that run every day, will help you figure things out as soon as the error has been introduced. While discussing defensive design, it's important that you understand the differences between robust programs versus reliable programs. Robust programs are those that do not crash in the presence of unexpected input. So, if you've given the program wrong data, it will not crash and just fail in a way that is not recoverable. Robust programs are also those which are not tricked into performing an undesirable action. You can't make it do something wrong. Reliable programs, on the other hand, are predictable programs. They produce predictable results under different conditions. No matter what branching operation your code has to implement, the result along every branch should be predictable. Reliable programs also exhibit consistent behavior for success flows and failure flows. So, your happy flows produce consistent results, errors and exceptions are handled consistently as well. Robust and reliable programs are not mutually exclusive. The idea of defensive design is to have programs that are both robust as well as reliable. When we think of designing and architecting a piece of software, we mostly think of how the software should accomplish what it should. But defensive design is about expecting the unexpected. Defensive design basically says user input is always suspect because users always make mistakes. Not all user inputs are malicious, but some might be. These malicious inputs could try to breach your system or crash your system or try to access secure sensitive data. Thinking of defense upfront as a part of the design process is also a secure programming strategy, though defensive design is not only about security. Such attacks can try to bring down systems and services, and defensive programming goes a long way towards mitigating such attacks. When you receive input from the user, this user input can be either sanitized or validated, and there is a difference in these two approaches. You have to figure out which one is the right one in your use case. Input sanitization involves taking in the input and cleaning it up to remove any unexpected or wrong values. Input sanitization is primarily a secure programming technique which is used to mitigate security attacks such as cross site scripting and SQL injection. Input validation, on the other hand, is checking whether your input meets certain criteria because only those inputs that meet your preconditions are valid for that system. So, only accept inputs that satisfy all of the conditions to produce a valid response. So, it's more about whether this input makes sense and not about whether this input could be malicious. Based on what kind of input you accept from the user, validation could include any of these. You could check to see whether all the required fields in a form, say, have values. You can also check to see whether the data for every field is in the right range. This is for numeric fields. Another check might be to see that data is of the right type. If you had a drop down, make sure the drop down have valid values and only those values can be input by the user. You also need to ensure that data is in the right format, especially for date and time fields. Another check might be that data is of the right length for password fields, for example. Another aspect of validating inputs is authentication and authorization. Authentication is a check to see whether a particular identity is allowed to access the system at all. Authorization checks to see whether that identity is allowed to perform certain actions on that system, read or write or execute. Especially with login based systems, authentication and authorization are integral defensive checks. So, what do you do when the unexpected occurs? Make sure you have useful error messages and prompt messages so that users are able to recover from these problems. If the user made a mistake, he or she should be given a chance to recover. Allow only authenticated and authorized access, that's on you. As I mentioned earlier, they are important secure programming techniques. And if errors occur and you cannot recover from them, use error reporting and exception handling liberally. We've discussed earlier that errors in your program are inevitable and you need to embrace those errors. Errors in user input, they are also inevitable. That's because of Murphy's Law. Anything that can go wrong will go wrong. So, what you really need to think of is the right error handling technique. There are many different kinds of errors that could occur while running your program. Compile errors, runtime errors, logic errors, out of memory errors, disk corruption, network errors, and so on. For all of these cases, the best way to test for these errors is to run simulations. Simulate errors and see how your code behaves in the presence of these errors. The simulation of errors in your test cases are an extremely important part of testing. That's because in your development environment, you may not encounter these issues. So, code in production may not work in exactly the same way as code in development does. So, simulations will mimic production issues. Now, how exactly you choose to handle errors depends on the type of error that it is. Errors may be recoverable. This means that the program knows how to recover from this failure and knows how to continue with normal operations. Errors may be unrecoverable as well. In such situations, the program cannot proceed under these circumstances and has to terminate or bail out. Expecting the unexpected involves continuously looking for errors. Try and detect your errors as close to the user input as possible, as close to where the error occurs. Now, this allows you to fail fast and does not propagate your errors through the system. However, this is not always possible. Most errors in programming are detected deep in the code at low level functions, far from where the original error occurred. Now, let's say you detected an error right before you were about to write your data out to a database. These low level functions will not know how to respond to this kind of error. They can't really tell the user what to do because they are very far away from the user. This is why low level functions need to propagate errors to high level functions, and the high level functions can then respond correctly. What we need is a robust mechanism for propagating low level errors up the stack so it can be handled by a high level function which knows what to do. There are several techniques that you can use to propagate errors through your code. You can use return codes to signify when a function has completed successfully or it has failed with an error. You can choose to use status parameters to indicate the presence of an error. The status parameter is an input argument that you pass to a function that is modified by the function. You can choose to have the function return errors in a state object that is part of the return value. So the state of the object will be different in the case of success or error. And finally, you can choose to have your method or function throw exceptions indicating there was an error. We look at each of these error propagation mechanisms in detail, starting with return codes, where we use the return value of a function or an API to tell the caller whether or not the function succeeded. Now, this may not always be ideal because now your return values are reserved for errors and cannot be used to return other objects or other state. It also puts the onus of checking for errors on the invoking function. So the client has to invoke the function and then check to see whether the function completed successfully or there was an error. So you're not minimizing client responsibilities. It makes it very easy for the client to ignore return values. There is no way you can force the client to check for return values. You could also choose to use status parameters to flag errors. The status parameters are additional input arguments that you'll pass into a function. Now, this has one advantage in that return values can be used for other objects. But remember that every method invocation now requires you to specify these additional status fields. Once again, many high level programming languages, including C, do not have forcing functionality to ensure that the status parameter has been checked for errors. If you propagate errors using error state, the error information is actually stored within objects that are then returned. So you either return success and a valid object or you flag an error. And it's the responsibility of the client query the object to get details about the error. Once again, just like error codes and status parameters, every invocation of the function or the method needs the object that has been returned to be checked for error state. And there is no forcing mechanism to ensure that errors are handled correctly by the client and not ignored. Now, because of the flaws associated with all these other types of error reporting, many high level programming languages support exceptions. Exceptions are what you throw when you encounter an error, and exceptions are usually reserved for unrecoverable errors, so you can use them for recoverable errors as well. Now, the beauty of exceptions is that they can be caught and handled. You cannot ignore exceptions. Force the client to acknowledge the presence of an error. Your return values are still free, so the function can return the valid object if a valid object exists. There are no additional parameters that you need to pass into the function, and the client does not need to check for errors in the object state. Exceptions also force you to change the flow of your program. So all of the error handling code is separate in a different block. So for normal conditions and normal operation, you have one code flow and the error conditions are clearly called out with a different code flow. And the best thing is, exceptions in programming languages such as C cannot be ignored. You can't say, I won't handle this error case, otherwise, your program will be terminated. So, exceptions have to be accounted for and handled. Exceptions are built into the C programming language and are the right way to flag and propagate errors. Defensive programming involves the extensive use of exceptions to check the input values in our code. Now, you should also use assertions liberally in your code for any assumption that you make. You may assume that a variable is in a particular range. You may assume that a file exists and is accessible and can be written to. You may assume that data in a collection is not empty. Assertions are used to make these assumptions explicit in our code. Assertions help you fail fast if what you're assuming is false and allows you to verify the correctness of your assumption and the validity of your code. Assertions are usually disabled in production code and they should be used liberally because they're very powerful for discovering and avoiding bugs early on. So, when would you choose to use exceptions versus assertions? Assertions are used to find and remove bugs before your software is released. They're not present in production code. Exceptions, on the other hand, are used to deal with errors which can even occur with correct code. Exceptions are present in production code. If you have control over the calling code, that is the code that is invoking your method or function, you can use assertions to check that the input values are valid. If you have no control over the calling code, that's an external client, you should use exceptions to flag errors to the client. A very important principle in writing defensive C code is pay attention to compiler warnings. Now, if you have a code that habitually produces a lot of compiler warnings which are actually indicative of bugs will be lost. So it's important that you write compiler warning free code so that compiler warnings, if they do occur, are immediately brought to your attention. Not all compiler warnings are important, but if you have hundreds of warnings in your code, you might miss an important warning that will help you find subtle bugs in your code. These subtle bugs may not manifest itself till your code is in production, so it's important that you pay attention to these warnings upfront. Let's take a look at a couple of examples of compiler warnings. I have a .h file here called stocksutility.h. This contains a bunch of method declaration related to stock prices. Get today open price given a ticker will give you the open price of that stock today. Get yesterday close price will give you the closing price of a stock based on the ticker. Is above threshold will take in a ticker as an input argument along with a price threshold. It will check to see whether the open price of that ticker for today is above the threshold that you've specified. We won't actually be tracking real-time stock prices here. This is a demo after all. Here within stocks utility.cpp, I have implementations of the methods that we had declared. Get today open price takes a ticker as an input argument, and if the ticker happens to be Google, Amazon, or Microsoft, it will return some value for the opening price of that stock. These are the only three stock tickers supported. For any other stock ticker specified, we'll return 0. The code for the second function here, get yesterday close price, is set up in a similar way. For the input ticker, we'll check to see whether ticker is equal to Google, Amazon, or Microsoft. For each of these tickers, we have some value of the closing price that we'll return. If we've specified a ticker other than these three, we'll simply return 0. That's on line 30. And then finally, we have is above threshold, which takes in a ticker as an input argument and a threshold. We then call get today open price for the ticker and get the price for that particular stock ticker. We check to see whether the price is above threshold. This is on line 36. If yes, we'll say that this ticker price is above the threshold. Otherwise, we get into the else block, and on line 40, we'll print out to screen that this ticker's price is equal to or below the threshold. So very, very simple. Let's now head over to main.cpp. Now, here is where things get interesting, and we'll get to discuss compiler warnings. Now, within the main function, you see that I have a variable for the ticker and I have two variables for thresholds, threshold 1 and threshold 2. For some reason, I have this additional variable defined. I then ask for what ticker the user is interested in. On line 16, I take in the ticker value specified by the user. I then ask the user for a threshold, and on line 19, I accept the threshold specified by the user. And I store that in variable threshold 2. So I have two threshold variables. Threshold 2 contains the value specified by the user, but when I invoke is above threshold, I pass in threshold 1. Now, threshold 1 has been declared on line 13, but it hasn't been initialized. It is an uninitialized variable. I have no idea what value will actually exist in threshold 1. Now, this code is fairly small and this uninitialized variable is easy to spot or identify. But in large code bases, such uninitialized variables will exist, and it's important that you track them down because at this point in time, I have no idea how this code is going to behave because I've passed in an uninitialized variable to is above threshold. Now, you would think that the compiler should warn me about this, but by default, it doesn't. When I compile my code, you can see that there are absolutely no warnings in the output. Now, I might feel my code is clean and I might go ahead and run my program. I'll have this false feeling of confidence that everything is okay with my code, but I'll get some strange results. I've specified the ticker Google and the threshold as 2000. Google is at 2306, which is above the threshold 0. Why is the threshold 0? Well, that seems strange. Let's try this again. Now I know something is wrong, but I don't know what. So I try it again and specify ticker as Amazon, threshold as 4000. I get Amazon is at 3247.6, which is above the threshold 0. Once again, the threshold that I have indicated or passed into this program is not the one that's used. Since this is a runtime error, the only way for me to figure out what's wrong is to debug my code. But what if I had compiled with some additional input arguments to my Clang++ compiler? This is exactly what I'm doing here now within my terminal. In order to get warnings about uninitialized variables, I need to pass in additional command line arguments. I've invoked Clang++. I want to compile main.cpp and stocksutility.cpp. Only the C++ files should be specified here, not the header files. C++17 is what I use, and I have three additional input arguments: -w all, -w extra, and -w pedantic. -w here stands for warning flags, and you're essentially enabling a bunch of warnings by passing in these as input arguments when you compile your code. All and extra will flag a number of different warnings, including uninitialized variables. Let's hit enter and observe that now you get compile time warnings when you compile your code. The W all, W extra, and W pedantic enables a number of different types of warnings. Amongst those is the uninitialized variable. You can see that the warning very clearly says threshold 1 is uninitialized when it is used here while passing into the is above threshold function. So the warning, had we seen it earlier and fixed it up front, we wouldn't have encountered the runtime error at all. We would have used the right threshold variable and passed that in to our is above threshold function. So remember, use the additional warning flags to get additional warnings from your code. I'm going to set these flags in my tasks.json file. Observe the args that we pass in to our clang++ command for compilation. I'm going to expand these arguments. So you can see here on lines 11, 12, and 13, I've passed in -w all, -w extra, and -w pedantic. Now, when I build using VS Code's build command, the compilation will take into account these additional arguments, and you can see the uninitialized warning is present once again. Well, we really need to fix this warning. So let's head over to main.cpp and let's now get rid of this threshold variable, the extra one. I'm going to have just a single variable called threshold1. Now, threshold1 will contain the value that the user input. All variables are now initialized. When I compile this code, you'll see that the warning has disappeared. I have absolutely no warnings, as you can see from the highlighted portion here at the bottom. Ignore the warning up top. Look at the bottom portion of the console starting at executing task. You can see there is no warning in our code. Let's now run clang++ with the same command line arguments. Our executable has been built without warnings. That's a great thing. Let's now run it. Let's look at Google threshold is 2000. It's 2306, which is above the threshold 2000. I'll run the exact same code and specify ticker equal to Amazon threshold 4000. Amazon is at 3247, which is equal to or below the threshold 4000. I've updated the code in main.cpp and in our stocksutility.h and stocksutility.cpp files. Let's look at what the updated code is, and we'll also see some new compiler errors that I have introduced. In the main function here within main.cpp, I've invoked a method called isTodayOpenUp. This takes in a ticker as an input argument and checks to see whether this particular stock opened up today as compared to yesterday's close. There are two invocations to isTodayOpenUp. On line 12, we check with the ticker Google, and on line 14, we check with the ticker Microsoft. Let's take a look at the declaration of this method in stocksutility.h. We still have the previous methods to get the open price, close price, and is above threshold. And on line 11, there is the declaration of is today open up. Let's now head over to stocksutility.cpp. All of the other functions defined here we are familiar with. Let's focus our attention on the function defined on line 45 is today open up. It returns a void and takes in a string ticker as an input argument. Now, everything is correct about the code, but there is a subtle bug that exists. You can see on line 46, we access the open price of that particular ticker today. We invoke get today open price. And on line 48, we access the close price for that ticker yesterday using get yesterday close price. Here is where I've inadvertently introduced a bug. Both get today open price and get yesterday close price return double values, as you can see from the inset picture on lines 5 and 7 in the inset. So we need a data type of type double to store the open price for today and the closing price for yesterday. But observe on line 46 and 48 in our code here, we've stored these values in variables of type integer. This is not an error in C++, but the compiler will generate a warning for this. Essentially, by storing double values in integer data types, we are losing information. All of the information present in the decimal values will be lost when we store this information in the int data type. And then once we have the open price today and the close price yesterday, we simply print out to the screen whether the open price today showed that the stock opened up or down. This is the code on lines 50 through 52. So that's what is today open up does. But there is a subtle error here. Let's try and compile this code and see whether the compiler warns us about this error. You can see that the compiler does nothing. It's absolutely silent, even with the W all, W extra, and W pedantic. In the console output, you can see that Clang++ takes those additional input arguments that we have specified while compiling this code, but those input arguments are not sufficient to flag this compile time warning. When we run our executable, you can see that all of our double values have been truncated to integers. Google's open today is 2306, but if you look on line 11, it's actually 2306.5. And yesterday's close Google says 2291, but if you look on line 23, it was 2291.7. And the same is true for Microsoft's open today and close yesterday. The use of integers to store these values resulted in the decimal places being truncated. Now, it would be nice if the compiler warned us about this. Let's head over to tasks.json and add in an additional flag that will give us warnings about these implicit conversions that occur in our code. The problem in the code that we've written is an implicit conversion from type double to type integer. If you want the compiler to flag such conversions, you need to specify an additional flag. You can see this flag on line 12. It's called -w conversion. This will tell the compiler, look for implicit conversions and flag them as compiler warnings. Now, you may choose to ignore these warnings, but it's better practice not to. Let's go ahead and run this code once again. We have an implicit conversion on line 46 and 48, and you can see that the compiler has flagged these two lines. The console output of the compiler very clearly indicates a warning. Implicit conversion turns floating point number into integer, and there are two such warnings, and then the exact line of code is also identified. In our demo code here, this implicit conversion wasn't really a big deal, but you can imagine in a huge code base, this implicit conversion will lead to loss of precision, and somewhere at some other point in your code, you'll get an error because of this. So let's fix this. And the way I've done this is by changing the code on lines 46 and 48 to store today's open price and yesterday's close price in variables of type double. You can see the double for open price today and close price yesterday. Compile this code, and this time the code will compile with no errors or warnings. The compilation output at the bottom shows absolutely no warnings. So things look good. And this time when we run a.out, we get the floating point values. We get the decimal places in our output. I'm now going to change this code a little bit and show you an example of another common issue which results in a compile time warning that you should watch out for. I've changed the code in my stocks_utility.h file. I've reduced the declaration here to just two methods that I've implemented: get today open price and get yesterday close price. Observe that the input arguments that these methods expect are of type integer. So you pass in an index that represents a ticker, and then you get the open price and close price for that ticker. So I've changed the code to use indices to represent stock tickers rather than specifying the entire ticker in the form of a string. And I've made the corresponding changes to the CPP file as well. Get today open price accept a ticker index as an input argument, as does get yesterday close price. But I've introduced a slight bug in my code, a common bug amongst developers. On line 12, you can see while comparing ticker index 2, which is the index for Amazon's stock price, I use the single equal to, that is the assignment operator, rather than the double equal to, that is the comparison operator. If execution reaches this if condition, the value of 2 will be assigned to ticker index. Since 2 is greater than 0, that if condition will evaluate to true and we'll get the value 3247. So it's not actually performing a conditional check, it's assigning the value of 2 to ticker index. And I have introduced the exact same bug in get yesterday close price. On line 24, I check whether ticker index is equal to 2, but I've used the assignment operator rather than the equality check, the double equal to. Now, this is an issue, and you'll see the issue when we run our main program. Our main code accepts a ticker index from the user, one for Google, two for Amazon, three for Microsoft, and then gets the open price for that stock today. When we compile this, thanks to the compile flags we've already configured, we get a bunch of warnings. The warning says using the result of an assignment as a condition without parenthesis. So you haven't used parenthesis to indicate that you want this to be an assignment. You're essentially using the single equal to assignment operator as a conditional check, and that is a big red flag. This is a compiler warning. If we ignore this warning, our code will essentially not work. With the warning, the executable has still been generated. Let's run a.out and we'll specify 1 as an input and we get the open price for Google. Things look good. Let's specify 2 as the input and we've got the open price for Amazon. Looking good so far. But now, if we run our code once again and specify 3, that is Microsoft, as the ticker we're interested in, we still get the price for Amazon. When our assignment statement on line 12, ticker index equal to 2 was encountered, ticker index was set to the value of 2 and we got the price for Amazon. So clearly, this is a pretty egregious thing to do. This is a warning that has to be heeded. So let's fix this. I have changed the code on line 12 and line 24 to use the double equal to for a conditional equality check rather than an assignment. If I now compile this code, the code will compile without any warnings. That looks beautiful. And when we run this code, it will work correctly. For 1, we get the open price of Google. When we specify 2, we get the open price for Amazon. And when we specify 3, we get the open price for Microsoft. In this demo, I'll show you an example of how you should be reporting errors that you check for within your user interface code. Now, any validation you perform within a user interface is very close to the user. You're typically validating the input that the user has provided. In such cases, it does not make sense to throw exceptions to flag errors. Instead, you should just report the status of the validation in the form of a return value. We know that exceptions have several advantages over other forms of error reporting, but if your code is within the user interface, it's validation code, it's close to the user, you'll find that error reporting using return values and error codes have their own place. Here is a header file that I have, loginutility.h, which contains some functions used to test the validity of the login information that a user provides. We won't be building the entire user interface, but this will give us an idea of how validation code for login is written. I've declared two functions here: is valid email address, which takes in the username in the form of an email address and checks to see whether that is in the valid format. And I have is valid password, which takes in a password that is a string and see whether the password matches the strong password requirements. We can now look at the implementations or the definitions of these functions in the login utility.cpp file. On line 9, you can see the definition of is valid email address. It takes in a string username. We'll check to see whether this is a valid email address. The username has to be an email address in our example here, using a regular expression. On line 11, you can see that I have created a regular expression for a valid email. Now, this regex functionality is available because I've included the header hash include regex on line 2 and I'm using std:/regex on line 6. You don't need to worry about the exact syntax of the regular expression for a valid email address. Suffice to say, the email address contains letters, both lowercase as well as uppercase letters and digits. We should have the at the rate sign followed by more letters or digits, then a dot, and then letters or digits once again. This is what the regular expression on line 11 tells us. We'll use regex match and see whether the username specified by the user is a valid email address. Next, on line 16, I have the definition for the function is valid password. It takes in a string password. I have set up a valid password regular expression. A password is valid if it contains at least one digit, at least one lowercase character, at least one uppercase character, at least one of the special characters asterisk, period, or exclamation mark. The password should be at least 8 characters in length, but no more than 32 characters. We'll see whether the password that the user has specified matches this regular expression. If yes, we'll return is valid password true, otherwise, we'll return false. This is on line 19. Now, let's take a look at the main.cpp file, which is where we have the code which accepts an input from the user. On lines 12 and 13, I have two variables, username and password. On 14 and 15, I have a Boolean variable tracking whether the email address is valid and another Boolean variable tracking whether the password is valid. I've run a while loop starting on line 17. So long as the email address entered by the user is not valid or the password entered by the user is not valid, we'll keep asking the user for the username and the password. So I take in the username on line 20, I take in the password on line 23. I then invoke is valid email address and store the result in email address valid on line 25. On line 26, I invoke is valid password and store the password in password valid. Now, if the email address is not valid, that is the check we perform on line 28, we'll immediately output to the user the email address specified was invalid. And this is exactly why it makes sense to report such errors using the return value. Now, if the is valid email address code had thrown an exception, this code would be not as clean as you see it here. Catching exceptions, as you shall see in the demos that follow, results in code that is not as clean. So, if the error has to be reported close to the user and has to return to the user immediately, using return values is better. So, if the email address is not valid, we continue on line 31 and we go back and ask for the email address and password again. The password is not valid. That's the code on line 34. Well, we'll output to the screen the password specified was invalid and we'll re enter the while loop. Otherwise, if we exit the while loop on line 39, we'll indicate to the user that they've successfully registered with a valid email address and password. Let's now compile this code, and this code should compile without any errors. Our executable is present in a.out. Let's go ahead and run this executable. And I'll first specify an invalid email address, Alice at Skillsoft, and you can see that the output says the email address specified was invalid. We are back at the prompt asking us for an email address. This time I'll say alice@skillsoft.com and it asks us for a password. The password ASDF is invalid and we are prompted for our username again. alice@skillsoft.com it is. This time my password contains lowercase letters, the uppercase letter A, and three digits 1, 2, 3. But this password is also not valid because I don't have a special character. I'm going to try one last time, and this time I include the special character asterisk, and this time my username as well as password is accepted and I have been registered. We've seen that when user input errors are discovered very close to the user, we usually use return values or status codes to flag the error to the user. But what if the error is found very deep in the call stack, very far away from the user? Then you should use exceptions to ensure that error is propagated up the call stack. Let's see how we can use exceptions in this demo. Here I have a student class. Every student has a unique student ID, name of a student, and a scores map, which keeps a mapping of the scores that the student has received in different subjects. Those are the private member variables. Under the public methods, we have the constructor on line 16, which creates a new student object using an ID and a name. On line 18, we've declared an add score method, which takes the name of a course and the score the student has scored in that course. And on line 19, we have a method called print details, which prints out the details of the student to the console window. Let's take a look at the implementation of this student class. On lines 16 through 18, we've defined the constructor for the student ID and name are the input arguments. And in the initialization list, we initialize the member variables, also called ID and name. On lines 20 through 27, we have the implementation of the add score method in the student object. The input arguments are course and int score. The interesting thing here is the exception that we throw. Defensive code involves the use of exceptions to flag errors wherever the errors are encountered. Now, in the add score method, we check whether the score that has been passed in by the user is in the right range. If we find that the score is less than 0 or the score is greater than 100, well, that's an invalid score and we'll throw an exception, which is the out of range exception. Exceptions in C++ can be used to flag situations which are not correct, incorrect, or errors. Out of range is a built in exception available as a part of the standard namespace. This out of range exception object is available to us on line 22 because of the using statement that you see on line 14. You can see that this using statement includes the out of range exception object part of the standard namespace. And this exception object is available to us because of the include statement you see on line 4. Include std except will bring in all of the exceptions defined in the standard namespace. Back to line 22 where we throw the exception. Now, this exception accepts a message as an input argument. That's the exception constructor. And the message should be a meaningful one to make it easy for you to track down what the error was. So I've clearly said score invalid for the name of the course. It's out of range. I've also included the wrong score that was passed in as a part of this error message. Now, once the exception is thrown, the execution is terminated right there on line 22. If there is an exception, that's where execution stops. If the exception is not thrown, we'll head over to line 26. If the exception is not thrown, it means that the score is in the valid range and we'll insert that score corresponding to that course into our scores map, insert or assign. The second method defined here, print details, is fairly straightforward. On line 29 is where the definition starts. We simply print out to the screen the ID and the name of the student on line 30. I then have a for loop that iterates over every key and value stored in the scores map. This for loop is a range-based for loop that was introduced in C++ 17. Within the scores map, we have key value pairs I get a constant reference to the key as well as a value, and I print out every key and value present in the scores map. That does it for the student class. Let's head over to the main file and see how we use this student object. I've instantiated a student named Alice on line 15 with the student ID and the first name. Notice that I have a try catch block. The try block extends from line 17 to 23, the catch block from line 24 to 27. Within the try block is where we include the code that might throw an exception. So the exception need not be thrown, but if you feel that the code is likely to throw an exception, you should always have that code within the try block. So I have the invocation to add score, three invocations in fact, on lines 19 through 21 within the try block, and I also print out details for Alice on line 23. Observe the catch statement on line 24. I catch the generic type exception. So exception is the base class for all of the exceptions in the standard library. When you catch a reference to exception, it'll catch all exceptions thrown that derive from this base class. The out of range exception that we throw within add score derives from the exception base class. So if that exception is thrown, it'll be caught by this catch block. Make sure that you always catch a reference to the exception. So exception ampersand and not just exception. We'll discuss why that is important in just a bit. Now, if an exception occurs, we'll print out exception caught, and e.what will give us the message corresponding to that exception. We'll also, on line 26, print out the type of exception that was thrown. The type ID and the name of the type ID that I have specified there will give us the type of exception. Now, you can see that this time around, all of the scores are in the valid range 23, 89, and 75. So we'll compile this code and run this code, and no exception should be thrown. The code that was executed this time around was the code in the try block. We did not enter the catch block at all because no exception was thrown from our try block code. Let's update the code that we have in main.cpp and change the score that we have for chemistry. Instead of it being a valid score, I'm going to set the score to be 101, which is clearly out of range. This is the only change that I have made. I'll compile this code and then run it, and you can immediately see that the output has changed. The output says exception caught, and nothing was printed out for Alice. The execution reached line 21. Line 21 threw an exception. The execution immediately switched over to line 25 within the exception block. The exception due to the code on line 21 causes the code on line 23 to be skipped. So we do not print the details for Alice. Instead, we execute the code on lines 25 and 26. We say exception caught, score invalid for chemistry, out of range, it's 101, which is clearly not in the range that we had specified. That is the result of the code on line 25. And you can see that the type of the exception says ST12 out of range, indicating that it is an out of range exception. On line 24, we got a reference to an object of type exception, but because we used a reference, the object remembers its type. It remembers that it's an out of range exception. We preserve the type of the exception. Whenever you encounter an exception, the execution moves to the exception block. Let's try this once again. I call add score on lines 19 and 20 with valid scores. Then I print out the details for Alice on line 22. And then I call add score for chemistry with a value of 101, which is invalid. And I print out the details for Alice once again on line 26. The exception block remains the same as before. So this time I print details before the exception and print details after the exception as well. Compile the code and let's execute it. The first three lines of the output, which gives us the ID and name for Alice and the course math and physics with their corresponding scores, these are because of the print details on line 22 before the exception. The code on line 24 causes the exception, which means the code on line 26 will never be executed, and we'll get into the exception block. In our main code so far, we've been catching a reference to the base class exception. But the exception that was originally thrown is the out of range exception, as you can see here on screen. Let's change the code that we have in main.cpp to explicitly catch the out of range exception. I have the using statement on line 12, and on line 29, I'm going to change the reference to be a reference to an out of range exception. With this change, you're telling C++, I'm only interested in catching out of range exceptions and any exception derived from out of range. I'm not interested in the other exceptions that might be thrown within the try block. When we compile and run this code, nothing changes in our case because the exception thrown by the code on line 25 is an out of range exception that is caught by our catch statement. But what if our add score method throws two different types of exceptions? I've updated the code in student.cpp. On line 20, you can see a vector of valid courses that a student might enroll in. Imagine that the only courses on offer this semester are math, physics, and chemistry. I've also changed the code in the add score method. In addition to the out of range exception thrown on line 28, on line 32, I check to see whether the course specified by the user is amongst the courses that are valid for this semester, whether the course is math, physics, or chemistry. I use the collection find algorithm for this, and if the course is not a valid one, I'll throw an invalid argument exception, and I'll indicate that this course is not offered. So add score now throws an out of range exception on line 28 or an invalid argument exception on line 33. Given that add score can throw multiple types of exceptions, I've changed my code a bit in main.cpp. Observe that I have two catch blocks, just a single try block, but one try block can have multiple catch blocks, and that's valid in C++. The first catch block on line 28 is what we enter when we get an out of range exception. You can see that catch is a reference to an exception of type out of range. So if we get an out of range exception, we'll specify that we have an out of range exception that was caught, and we'll print out the type of the exception. On line 31, we catch a reference to an exception. Remember, exception is the base class of the out of range exception and other exceptions in the standard library. So we'll get to line 31 only if the condition is such that we do not have an out of range exception, but we have some other exception deriving from the exception base class. So when you have multiple catch blocks, always catch the more specific exception first. So out of range is the more specific exception that should be caught first, and then we catch the more general exception, which is just exception on line 31. Having made this change, let's go ahead and compile and run this code. Observe that when we encounter the out of range exception, that's the exception thrown on line 25, we enter the catch block for the out of range exception. Score of 101 is out of range. That was what was thrown. So we execute the code on lines 29 and 30 to print out the output, out of range exception caught, and the type of the exception. Let's change our code such that the add score method now throws the invalid argument exception. So we'll add the score for biology. This is not one of the courses that is offered this semester. Only math, physics, and chemistry are offered. So we should get a different exception from our code. Once again, let's compile and run this code. The exception will be thrown on line 25, and you can see that this time around, because the exception thrown was an invalid argument exception, the catch block for out of range was not the one executed. Instead, the invalid argument exception was caught by the more generic catch block on line 31, where we catch a reference to the exception base class. Invalid argument derives from exception, which is why that was the catch block code that was executed to handle this exception. It's not always necessary to have a catch block handler that catches a reference to the generic base class. You can have multiple catch block handlers where each block catches and handles a specific type of exception. Observe the changes that I have made here. On line 28, I specifically catch the out of range exception. On line 31, I specifically catch the invalid argument exception. If another kind of exception is thrown within our try block, well, that will not be handled with the current setup. If no exception is thrown, only the code in the try block will be executed. If an exception is thrown based on the type of exception, the correct catch block will be executed. You can see that when we tried to add biology as a course, that threw an invalid argument exception, which means our catch block on line 33 was the one that was executed. The course is not offered biology. If you have code within a try block that can throw exceptions, you can have not just two, but three or any number of catch blocks to handle specific exceptions in that code. Here is an example where I have three catch blocks, but there is an issue with the way I have set up the catch blocks. Let's take a look first. On line 29, I catch the general exception. A reference to exception is what I expect in the catch block. On line 33, I catch the out of range exception. And on line 37, I catch the invalid argument exception. Now, the issue with this code is that I've caught the catch block for the base exception class on line 29 is specified before the catch blocks for the more specific exceptions. Both the out of range exception as well as the invalid argument exception are classes that derive from the base exception class, which means they are also exceptions. And instead of having those exceptions be handled by the more specific catch blocks, every exception will be handled by the general catch block specified on line 29. Whatever the exceptions thrown, the two catch blocks defined on line 33 and 37 will never be entered. The code within there will never be executed. Thanks to the additional flags that we specify while compiling our code, you can see that there are warnings indicating exactly this. The exception of type std invalid argument will be caught by an earlier exception handler. The same warning is present for the out of range exception as well, and you can see the squigglies in the code on line 33 and 37. As we've discussed earlier, it's always good practice to keep your code warning free. But if we chose to ignore this warning, the code will not behave as we expect. When you run this code, let's take a look at the exception caught. When we tried to add biology to the student Alice on line 25, the exception thrown was an invalid argument exception, but the catch block code executed was the code on lines 31 and 32. You can see that the console output says exception caught. That is the cout on line 31. It does not say invalid argument exception caught. But the type of the exception is ST16 invalid argument. So the type has been preserved thanks to our data type being a reference to an exception, but we haven't executed the right catch block. I'm going to tweak the code on line 25 just a little bit. I'm going to add chemistry, which is an accepted course, but with a score of 101. The score is out of range. So the exception that will be thrown will be an out of range exception. Once again, when we compile this code, you can see a bunch of warnings indicating that the right exception block will not be executed because we put the more generic block first. When you run this code, even though an out of range exception is what is thrown, the code that was executed is the code within the exception block. 31 and 32, those are the lines that were executed. Using different catch blocks for catching different types of exceptions makes sense if the handling of the different exceptions is different. If you plan to handle all of the exceptions in your code in exactly the same way, so the handling code is the same, you can simply choose to catch the more general purpose exception. So on line 29, I have a reference to exception and I have a single catch block. This will ensure that all of the exceptions thrown within our try block will be caught and handled by this one catch block. And this is perfectly valid. So if I were to compile and then run this code, now that I've thrown an invalid argument exception, that is caught by our exception block. Let's say we were to change our code to have it throw an out of range exception. We add score for chemistry with score 101. Let's compile and run once again. The out of range exception is also caught by our one exception handler. So only if you need different handling for different types of exceptions, you specify multiple catch blocks. Now I have made a couple of changes to this code. One change is a minor one. On line 25, I add the score for biology, which is not a course that is offered this semester. But the more significant change is on line 29. Rather than catching a reference to an exception on line 29, I catch an actual exception object. So instead of having the ampersand, I only have exception. Now, the problem with this code is each time an exception is thrown, the copy constructor of the exception object will be invoked and a new copy of the exception object will be passed into the catch block. Now, this is not the only problem. Now, because we are catching the base class exception, it's only the copy constructor of the exception base class that will be called, which means any additional member variables or other information that you have in the derived classes out of range or invalid argument will be lost. This is basically object slicing. So the exception that is caught will be sliced, so the information in the derived classes will be lost. You'll only have the information present in the exception base class. We'll discuss object slicing in more detail later on in this learning path, but just keep in mind this very, very important rule. Never catch exceptions without a reference. Never catch exceptions as objects. Always catch them as references. So, with that in mind, let's see how this works. I have compiled my code and I'm going to run it. The exception that is thrown by the code on line 25 is invalid argument exception. However, notice that the exception that was caught was of type standard exception. ST9 exception is the name of the type ID. Basically, thanks to the exception being sliced, a new exception object was created of the base class type. I'll tweak the code just a little bit. I'll add chemistry with a score of 101. So that is the out of range exception that should be thrown, but I'm still catching the object exception, not a reference to exception. So the type will be lost, the object will be sliced. Once again, let's quickly compile this code. There are no warnings and then run. You can see that the exception caught is once again of type standard exception. The additional error message indicating that this is an out of range exception, the course and the actual score, all of that is lost because of object slicing. One way of writing defensive code that protects against unwanted inputs specified by the user of your code and also ensures that the action taken by your code has indeed occurred, that the action is complete, is by using preconditions and postconditions. Now, preconditions for your code, that is, preconditions ensuring that the input arguments are in the right range, they are valid, and so on, can be checked using exception handlers. And you can use assertions to check for postconditions. We'll see how you can check for preconditions using exceptions and check for postconditions using assertions in this demo. Once again, I'm working with the student class that we are familiar with. You can see that the member variables of student are ID, name, and a scores map. These are defined on lines 9, 10, and 11. The public methods are we have a constructor that takes in a student ID and name on line 15. We have a get ID that is a very simple getter method to access the ID of a student. Observe on line 17, I'm following best practices and marking this method as const. The presence of this const keyword indicates to anyone using this code that get ID will not change any of the member variables of the student object. I have add score as before to add a score for a particular course. This is on line 21. I have also overridden the comparison operator for a student class. So you can compare one student with another to see whether this is the same student. The operator double equal to does this on line 23 and it takes as an input argument a constant reference to the other student. This constant reference essentially means that the operator comparison can only call other const methods in the student that is passed in as an input argument. And finally, we have print details on line 25. Since that only prints out the details of the current student that is also marked const. Let's take a look at the implementation of this student class in the student.cpp file. On line 19, I've defined a vector of all of the courses that are offered this semester. The courses are math, physics, and chemistry. I have the constructor for the student on line 21 through 23. You can see that a student is constructed using the ID and name of the student. Let's take a look at the implementation of the add score method. The add score method defined on line 25 takes in the course and the score for that course for that particular student. Now, we are following defensive programming practices and checking to ensure that the course and score are both valid values. This we do using exceptions. This is our preconditions check. So if we find that the score is not in range, if it's less than 0 or greater than 100, we'll throw the out of range exception on line 27 and we'll say that the score is invalid for this course. On line 31, we'll check to see whether the course that we are trying to add the score for is within the vector of courses, which represents the courses that are offered this semester. If it's not within that vector, and we figure this out by using the find method in our standard algorithms, we'll throw the invalid argument exception on line 32. Only if the course and the score are both valid will we insert that course and score as a key value pair in the scores map. This is on line 35. Let's take a look at the comparison operator that we've implemented. The operator double equal to, which takes in a reference to a student const. We'll compare the ID of the current student with the other student's ID. We'll compare the name and we'll compare the scores map. We can use the double equal to for comparison because these are also operators overloaded for string classes as well as map classes in the standard collection. And then print details. We'll print out the ID and the name of the student. We'll use a for with ranges to iterate over the key value pairs in the scores map and print out the course and the corresponding score. Now I plan to store all of the student objects that we create in a student's database. And here is the header file for our student database object. It has just one private member variable, a map of the student's name to the student object. This is on line 10. The public methods include all of the methods that you'd want to perform create, read, update, and delete operations on the database. On line 13, we have the constructor, which is just a simple no argument constructor. Add student takes in a reference to a student, a const reference as an input argument and adds the student to the database. The database here is simply our map. Update student will update the information for a particular student. Delete student takes in an ID and will delete the student with that ID. And print details will print out all of the students that are present in our database. Now that we know what methods are implemented, let's take a look at the actual implementation in students database.cpp. Now, we are not actually connecting to a database, not for this demo. We'll simply add a student to our map. The map will serve as our database of students. So here in add student on line 22, I check to see whether a student with the same ID is already present in our map. This is on line 24. If yes, this is our defensive programming and our preconditions check, we'll throw an invalid argument exception which says the student is already present in the database. We can't add them again. If this exception is not encountered, that means that the student is not present in our database on line 28, we'll basically place that student with the corresponding ID in our student's map. Let's take a look at the update student where we also have a preconditions check. The input student, the input argument, is checked against our database to see whether a student with the same ID already exists. If not, if we find no student with the same ID, update cannot be performed. So if we can't find a student with this ID in our student map, on line 33, we'll throw the invalid argument exception which says the student is not present in the database. If we find that the student already exists in the database, we'll update that student's entry using insert or assign on line 36. We've implemented delete student on line 39, which accepts an ID as an input argument. We'll use that ID to check within our students map if a student with that ID exists. If we cannot find a student with that ID, we'll throw the invalid argument exception and say a student with this ID is not present. This is our preconditions check. If we do find a student with that ID on line 44, we'll call studentsmap.erase and essentially get rid of the student with this ID. Now, observe that we are performing defensive programming at every method here. Within add student, update student, and delete student, we have a check to ensure that the preconditions for each of these actions are satisfied. Only if the preconditions are satisfied do we go ahead with the implementation of the code for add student, update student, and delete student. This is defensive programming. Finally, let's quickly look at print details. Here I've used a range-based for loop to iterate over every key value pair in my student's map, which will give me the student ID and a reference to the student object. When I have the reference to the student object, I'll simply invoke print details on that student object. Now that we've seen the code, let's take a look at our main.cpp file. So on lines 20 through 22, I have the student Alice and I've added scores for math and physics. On lines 24 and 25, I have the student Bob with a score for physics. I called studentdb.add student on lines 27 and 28. And after having added these students to our database, I'll print out the details of the database. All of this is within a try block. If any exceptions are thrown, it will be caught by our general exception handler on lines 31 through 34. I'll now go ahead and compile this code. It compiles without warnings. Let's run it. And you can see that both Alice and Bob have been successfully added to our students database because all of the preconditions specified in our code were satisfied. We did not try to add a student who already existed in the database, and we didn't perform any other invalid operation. Now let's try to perform a few invalid operations, and you'll see that our defensive code will stop us from doing so. Now I have two definitions for the student Alice, one on line 20 and another on line 30. You can see that the student IDs are the same, the name is the same, the physics and math scores are exactly the same. When I try to add another Alice on line 34, our database should complain. So let's try exactly that. When I run this code, my preconditions check fails, and you can see that I get the exception. The student is already present in the database. This is an invalid argument exception. Let's try another operation on our students database. We'll update the details for Alice. So Alice was originally added with a physics score of 89 and a math score of 23. This is on line 21 and 22. But we find that Alice's score in math was actually wrong, so we want to update her score. On line 34, you can see that I've updated Alice's math score to 39 and I call studentdb.updateStudent on line 36. Update student can only be called on students where their details already exist in the database, so everything will work as expected. And you can see at the bottom here that Alice's math score has been updated to 39 from the original 23. But what if you try to update the score for a student where the student is not present in the database? On line 32, I have a student, Charles. I haven't previously added Charles, but I try to update Charles on line 35. No student with this ID, student 777, is present in our database. If we try to compile and run this code, we'll encounter an exception thanks to our preconditions check. Here, I leave it to you as an exercise to ensure that delete students precondition check also works as expected. We've seen how you can add preconditions to your code using exceptions. Let's now see how you can have post conditions to ensure that your methods have done exactly what they claim to do. We'll add post conditions using assertions. Assertions are basically a way to check whether a particular state is true, whether an action has been performed and the end state is what we would expect. And we'll do this for all of the operations we perform on the student database. There is no change to the .h file. We still have add student, update student, delete student, and print details. The post conditions that we've specified are in the student database implementation. We'll be checking our post conditions using assertions, and for this, you need to include another library from the standard library. On line 6, you can see an include for C assert, and this is the assertions library that we'll use for post condition checking. Here we are within the student database.cpp file. Let's take a look at add student. On lines 25 through 27, we have the preconditions check. On line 29, we actually perform the action where we add a new student to the database. And on line 31, I've added in a new post conditions check. The add student method adds the student passed in as an input argument to our database. Now, on line 31, I want to check to see whether the student has been added successfully. And this is why I have the assertion or post condition check. I search within the student's map to find the student with the specified ID. And if I do find the student, well, our assertion will pass, there'll be no error, and the code will be executed successfully. If we find that the student with the particular ID has not been added to the map, the assertion will fail. And we know that there is something wrong with our database add student code. So this assert here ensures that the student has been added correctly. I similarly have a post condition check in update student as well. We have the precondition check on lines 35 through 37. On line 39, we update the already existing student details. On line 41, I check to see whether a student with that ID is present. The first assertion on line 42 is to check whether the student whose details we have updated, that student is indeed present. We have found a student with that ID. The second assertion on line 43 checks to see whether the student with that ID has updated details. If the second value, that is the student instance that is in our database, is equal to the updated student details that we use to update the student. And finally, I have added assertions to the delete student code as well. We have the preconditions check on lines 47 through 49. So long as the student exists, we delete the student on line 51. And then on line 55, I assert that that student is no longer present in our database after deletion. This is our post condition check. Now, with all of these post condition checks in place, all of the assertions that you see on lines 31, 42, 43, and 55, essentially we know that if any of these methods are invoked, we know that they are guaranteed to succeed or an error will be thrown. So that is how the post conditions help. Switching over to the main class, I created the student Alice on lines 20 through 22 and added scores for Alice. Bob is on line 24 and 25, and on lines 27 and 28, I add Alice and Bob to our database. Let's go ahead and compile this code. And now, when you run it, everything passes. All of our preconditions have been met, our post conditions have also been met, which is why we have cleanly executing code. Let's try updating a student who has been added to the database. I've already added Alice. Now I have another Alice created on line 32. The student ID is the same, student 1234. Alice is now Alice Jackson, and her math and physics scores have both changed. Let's compile and run this. Once again, if the preconditions and post conditions have both been met, the update will be successful and we have Alice Jackson in our database, as you can see from the console output. Bob still remains the same. For the sake of completeness, let's test out deletion as well. We've added Alice and Bob to the database, and on line 32, I delete the student with ID student 1234, which is Alice. That student is present in our database. So if you were to compile and run this code, you'll see that Alice will have been successfully deleted. The print details on line 34 only prints out Bob. Alice has been erased from the database. This demo brings us to the very end of this course on defensive programming and defensive design. We started this course off by understanding what exactly defensive programming is all about and how it helps us build robust software. We saw that defensive programming tries to ensure that our software continues to function as expected even under unforeseen circumstances. We discussed that there are many aspects to defensive programming, including code quality, writing comprehensible code, and having our code behave predictably despite unexpected inputs or user actions. We saw that defensive programming is an integral part of defensive design, which involves planning for contingencies up front, right at the design stage of software development. Defensive design allows us to write software that is both robust as well as reliable, and we understood that these mean subtly different things. Defensive programming involves proactive reporting of errors in our code, and we explored different error reporting techniques we can use, including error reporting using return values, status parameters, error objects, and of course, exceptions. We saw that exceptions offer a significant advantage over the other error reporting techniques since they are enforced by the language and clients cannot ignore errors. We also understood when we would choose to use exceptions versus assertions in our code. We rounded this course off by checking preconditions on method inputs and postconditions on method results. With the foundation of defensive programming laid, you are now ready to tackle the next course in this learning path, writing defensive C++ code. In this video, we'll go over some C++ specific language features that allow us to write defensive code. Now we'll discuss defensive C++ coding as a part of the core library as well as the standard library. This will be a quick overview because many of these features we'll cover in demos to come. C++ supports arrays. Arrays are collections and they are created using the new and the square bracket operator. Avoid using arrays, use collections from the standard library instead. Also, if you're creating overloaded functions, ensure that they all have the same security characteristics. The API or interface that you expose to clients should be stable. It should not change unnecessarily, but it should be easy to update if you have to. Make sure that all code that is security critical is at a central place so it can be patched exactly once. And finally, make sure you use the pointer to implementation or the pimple idiom. With the pointer to interface idiom, you'll expose the interface to your client, hide the implementation details, and you'll ensure that a change in implementation does not require your client to be recompiled. The standard library contains a large number of collection containers which are widely used. You can access elements of these containers with iterators. Now, there are certain functions which make use of unpaired iterators. So, iterators do not have a begin and end. These can be misused. Keep that in mind. Use your iterators carefully because iterators can be moved past the end of the collection. You need to watch out for that. Prefer the use of .at methods to access the elements in a collection rather than the operator square brackets. That's because .at performs bounds checking. The operator square brackets does not. And if you're using strings in your program, prefer the standard library string class rather than C style strings. The coding guidelines for C++ can be divided into four broad categories: fatal coding errors, defensive C++ code, good programming practices that you ought to follow while writing C++ code, and then code readability and other niceties. Now, these are the categories as created by Jerry Swan in this defensive C++ guide, which I highly recommend. I believe this is an excellent resource for C++ programmers. What are some examples of fatal coding errors? Not implementing the copy assignment correctly. Think of whether your object should be non-copyable. Can the compiler copy this object, or do you need to provide a custom implementation? Do not perform bitwise copy on objects, that always leads to issue. Do not copy polymorphic objects by value, and take care that all of your expressions have defined results. While initializing static variables in different translation units, beware of the static initialization order fiasco. We'll cover this in more detail in a demo. Do not have global or static variables in one translation unit or one C++ file. Depend on values which are static variables in another translation unit. If you're creating temporary objects within a function, do not return a reference to these objects. Temporary objects will go out of scope as soon as the function exits. So you should not be holding a reference to those objects outside of the function. Once you've avoided the fatal coding errors, here are some principles to follow for writing defensive C++ code. First, do not ignore compiler warnings because compiler warnings may be indicative of more subtle problems down the line. Minimize the visibility of your data. Make your member variables private and make sure that only the methods that external clients need to use are public. Make sure you restrict access to class attributes and make the maximal use of the const keyword, indicating that this particular method does not update member variables. It might be tempting to provide a large number of default constructors in your class for flexibility, but make sure your constructors leave your object in a valid state. If you need to convert objects from one type to another, prefer explicit type conversions using static cast, dynamic cast, reinterpret cast, and so on. Don't use C style casting. Minimize the use of pointers and reference cast and use resource allocation is initialization techniques to manage resources. We'll have more to say about RAII in this learning path. RAII encourages the use of smart pointers in the standard library to manage resources instead of managing them directly by yourself. And here are some good C++ programming practices for you to follow. Don't use magic numbers, use enums instead to represent values. Keep your functions very short, as short as possible, and use lambda functions where applicable. Avoid using raw pointers, use smart pointers instead. Don't manage memory yourself, leave it to the smart pointers, and make sure you avoid C style casts. If you want to avoid copying large objects, prefer the use of references rather than pointers. When you override a base class implementation, make sure the base class function is a virtual function. Operator overloading may not be applicable for all classes. Think through and use it with care. If you're writing looping constructs, prefer for loops with a clear terminating conditions. It's easy to get while loops wrong. Here are some C++ techniques for improved code readability. Use prefix operators rather than postfix operators, plus plus a rather than a plus plus. Minimize vendor specific dependencies. If you're using libraries from a vendor, don't write code specific to that vendor. Use forward slashes in path names. The backslash is an escape character in C++. Prefer a single exit point within your function. Do not have multiple exits if possible. And make sure when you read and write attributes that you do it one at a time, not multiple attributes at a time. An important tenet of defensive programming in C++ is to ensure that all of the constructors that you have for a particular object always leave that object in a valid state. We'll see an example here of having unnecessary constructors which leave the object in an invalid state. We'll see how you should clean this up and we'll discuss how you should think about how your objects can be constructed. Here we have an employee class. The header file here is employee.h. The private member variables on lines 9 through 12 are ID, name, salary, and department. Now, it might be tempting to have a variety of different constructors for this employee. You might think that this offers flexibility to the user. But if your constructors do not leave the employee object in a valid state, essentially they are useless. Here you can see that I have a number of different public constructors for employee. On line 16, I have the default no argument constructor. On line 18, I have a constructor that takes in only an ID and a name. On line 20, I have a constructor that takes in the ID, name, and salary. And on line 22, I have a constructor that takes in ID, name, salary, and department. Now, Of these, let's assume that you have a valid employee only if the employee has an ID, name, salary, as well as a department. The first three constructors will leave the employee in an invalid state. They should not exist, but they do. For some false feeling of flexibility, you're now burdening yourself and you have to write code for all of these constructors. You can see on lines 9 through 11, I have the specification of the default constructor, which sets the ID and the name to the empty string, salary to 0, and department to the empty string. This is a meaningless employee. This constructor should not exist. Then the constructor on lines 13 through 15 sets the ID and the name, but salary is 0, the department is the empty string. The constructor on lines 17 through 19 sets the ID, name, and salary, but department is the empty string. You can't have an employee without a department. The only valid constructor here is the one on lines 21 through 24. Here we initialize the ID, name, salary, as well as the department. And we have the print details implementation, which simply prints out the details of every employee. Having the first three constructors, which are constructors that leave your object in an invalid state, results in an unnecessary burden on you as well as the user of your code. Once a user sees those constructors, they'll go ahead and use them, and that will result in invalid objects being created. Here you can see that we have employee E1 created using the default no argument constructor. E2 and E3 also use invalid constructors. Only employee E4 is in the valid state. All I've done here is constructed employee objects and I print out the details of every employee. This is the code on lines 14 through 17. Now let's run this code after compiling it and we'll see that most of the objects that we create are not valid. Logically, it makes no sense to have an employee with no ID, no name, no salary, or no department. You should ensure that such constructors do not exist in your code. So let's go ahead and fix this. On lines 9 through 12, you can see that our member variables are still ID, name, salary, and department, but we have specified exactly one constructor, and this constructor will leave our employee object in a valid state. This is the constructor declared on lines 16 and 17, which takes an ID, name, salary, and department as input arguments. We still have the print details method. This actually results in a major simplification of the code that we write in employee.cpp, and it also allows us to think more deeply about the single constructor that we have. Now, let us say that there are only a few departments in your organization. Your organization only has engineering, HR, analytics, management, and sales. I have defined the vector of these valid departments on lines 16 and 17. Now, having done this, we can set up our constructor so that it performs additional checks to ensure that any object constructed is valid. The constructor is defined on lines 19 and 20. It takes in those input arguments. On line 21, we have the initialization list, initializing the values of ID, name, salary, and department. In the body of the constructor, I perform additional checks. Think of these as preconditions, checks performed using exceptions. Now, you might have other checks to ensure that your employee object is in the valid state. The checks that I have performed include checking to see whether salary is positive. If the salary specified is less than or equal to 0, we'll throw an invalid argument exception and say, please specify a positive value for salary. Next, we check to see whether the department associated with this employee is one of the valid departments in our organization. So we use the find method in our standard library to check whether the department specified is present in our valid departments list. Otherwise, we'll throw an invalid argument exception saying, please specify a valid department. Print details, the implementation remains the same. So ensure that the constructors that you have leave your object in a valid state. That's exactly what we've done here. Thanks to all of the defensive C++ code that we've written, any object that we instantiate of type employee will be in a valid state. Here, within the try block of my main code, I've instantiated an employee object, Ron. Ron has a salary of 123,000 and is in HR. Now, I'm going to compile this code and run this code, and you can see that the object Ron has been successfully created because all of the input arguments were valid. You can see the details of Ron in the console output. But what if I tried to instantiate an employee with wrong parameters? Here I have Ron once again, but he belongs to the customer service department, which is not a department currently present in my organization. If I try to run this code, you'll find that an exception is thrown. You can see that the exception message says, please specify a valid department. What if we try to create an employee with a negative salary? Well, that's clearly wrong. Here is Ron once again belonging to HR, but with a salary of minus 123,000. If we try to compile and run this code, once again an exception will be thrown. Thanks to our defensive code, invalid objects will not be created. We haven't fully thought through all of our constructors. Remember that C++ has the copy constructor as well as the move constructor. Do you want your employee objects to be copied? Is that allowed? That is something that depends on the kind of class that you have defined. Certain classes, such as database connections, may not be copyable. Employees may be. Here, our employee object is by default copyable. That's because the compiler automatically generates a copy constructor for us. So if I try to create a new employee Ron copy on line 14 and assign the original Ron to this Ron copy, the copy constructor, the default copy constructor will be invoked and a copy of Ron will be created. Let's compile and run this code. There are two Rons here, our original Ron and our copy of Ron. Now, if you think through and figure out that you do not want your objects to be copied, you have to explicitly get rid of the copy constructor in your employee class. For every class you write in C++, if you do not have an explicit implementation of the copy constructor, the copy assignment operator, the move constructor, and the move assignment operator, the compiler will automatically generate one for you. So if your class is of a type where copying is not permitted, you should go ahead and delete the copy constructor and the copy assignment operator, as I've done here. On line 20, I have specified the copy constructor and I have an equal to delete. This will essentially tell C++, I don't want this copy constructor. In exactly the same way, I have a specification for the copy assignment operator on line 23, and I have an equal to delete, indicating that the default generation should be suppressed. I do not want a copy assignment operator. Now, if I compile and run the same code again, where I copy Ron into Ron copy, that won't work. And this is a compile time error. The error very clearly tells us that the call has been made to a deleted constructor of employee, and that deleted constructor is the copy constructor on line 14 of main.cpp. By explicitly marking as deleted the constructors you do not want, you are thinking through what actions can be performed on your object. Back in your employee.h file, let's say you want the default implementation of the copy constructor and the copy assignment operator. Simply replace the delete by default. Equal to default tells the compiler that you want the default implementation of these constructors. The code here is the same as if you did not have any specification for these constructors at all, but is a way of explicitly saying you want these constructors. And this time, when you compile your code, there are no compile errors because copy is permitted. Ignore the old compile errors you see here. Look at the bottom, there are no new compile errors. And we can run this code, run a.out. And here you see we've successfully managed to create a copy of Ron. So think through carefully. Do you want the copy constructor and the move constructor? Do you want the copy assignment operator and the move assignment operator? If not, go ahead and explicitly delete them. But remember, if you delete those constructors, you won't be able to use your objects with the collections in the standard library. They make heavy use of copy and move. In this demo, we'll explore the importance and the use of the const keyword. The const keyword can be used to mark methods as constants. Constant methods essentially indicate that they do not update or change the values of the member variables of a class. We'll also see how you can pass input arguments to functions or methods where the input arguments are marked const. And we'll see the link between this. Before we look at how the const keyword works, here's a little bit of advice for you. If you have methods that do not update member variables, mark them as const upfront. Don't go back and retrofit the const keyword. By that time, there'll be a lot of code that already use those methods, and it's very hard to track down and mark a method as const after the fact. So when you're writing code for a particular class, think hard about which methods should be marked const and which methods perform some kind of update and shouldn't be marked const. Here is an example of the same employee class which we looked at in the previous demo. Every employee has an ID, name, salary, and a department. We have the employee constructor, just one constructor defined on lines 15 and 16. And we have a method, compute total salary, that computes the total salary of an employee, including a bonus. The bonus percentage is passed in as an input argument. This salary computation does not update any of the member variables of an employee object, so that method should ideally be marked const upfront. I haven't done so, and this will be a slight annoyance later on. Print details should also be marked const. It only prints out the details of an employee. Let's look at the implementation of the employee class. I have a vector of valid departments in my organization defined on lines 16 and 17. This is the same as in the previous demo. I have a constructor for the employee which takes in an ID, name, salary, and department. And I have defensive code within the constructor to ensure that the employee object constructed is valid. So if salary is less than or equal to 0 or it's an invalid department, we'll throw exceptions. Let's look at some of the code that is new. I have compute total salary implemented on line 35. It takes in a floating point bonus percentage as an input argument, and it computes the salary as salary plus bonus percentage multiplied by 0.01 multiplied by base salary. It does not actually update the salary. This is a const method but hasn't been marked const. Print details only prints out the details of this employee. Once again, this should have been marked const, but it isn't. Now I've written some code in main.cpp working with employees. I've created 3 employees on lines 9, 10, and 11, Ron, Harry, and Hermione. They have different salaries and are in different departments. After having created these employees, I print out their details on lines 13, 16, and 19. I also compute the total salary for each of these employees. They have a different bonus percentage. This is on lines 14, 17, and 20. Now, this is the code that we'll compile and run, and you'll see that everything works as expected. Compilation was successful. Let's run our code. And here are 3 employees and their total salaries. So far, so good. We haven't really missed the const keyword in any way. But what if we want to give our employees a one-time special bonus? And I'm going to create a new function for exactly this. Now, because that function needs to access the salary details of an employee and salary is a private member variable, I have defined that function as a friend of our employee class. A function that is a friend of a class can access the private member variables of that class. So this compute special bonus friend function can access the ID, name, salary, and department of every employee. Now, compute special bonus takes in a const reference to an employee as an input argument, that is the first input argument, and a floating point value for the regular bonus percentage. Now, this reference to a const employee is to basically ensure that this compute special bonus function does not update the employee in any way. We don't want it changing the ID, name, salary, or the department of the employee. We want to ensure that it only accesses the values in the employee and does not update them. Now, let's define the method within this header file, the compute special bonus. I've done that on lines 27 and 28. So this is the function that is a friend of our employee class. Let's now implement this function in employee.cpp. Now, compute special bonus takes in a reference to a const employee and a regular bonus percentage. You can see this on lines 45 and 46. We then call employee.compute total salary on line 48. So we compute the total salary of the employee and then add the bonus to that total salary. The special one time bonus given because our organization has done very well is 10%, and you can see that on line 51 where we multiply total salary by 1.1. But now, here is a hitch. If you wait for a bit, you'll see that the highlighting of our IDE will bring it to our attention. This friend function accepts a const reference to an employee. But when we try to invoke employee.compute total salary, this compute total salary method may update the member variables of the employee object passed in. Because compute total salary may update member variables of the employee, we cannot invoke that method from a const reference in case it violates the constness of our employee. And this is a compiler error, as you shall see when we compile this code. This argument to member function has type const employee, but the function that we are invoking, compute total salary, is not marked const. Any function that accepts a const reference to employee cannot call compute total salary, cannot call non-const methods of the employee object. And this can be a problem if you're using other library functions with your objects. Now, because our code base is small and this is a demo, the fix for this is easy. Head over to employee.h and go ahead and mark compute total salary as a const method. You need to do this in the header file as well as the implementation. Now, for good measure, let's go ahead and mark print details as const as well, because that should be const. The const keyword is what we've added. In a huge code base, there might be many references to your employee class, and many of them may not be const references. Going back and marking functions as const is always a problem. Let's head over to the implementation and make the fix there as well. You can see that compute total salary as well as print details have been marked const. Now that compute total salary has been marked const, it can be invoked from compute special bonus. The code on line 48 is no longer an error. We can only invoke const methods from a const reference. Before we run this code, let's update our main.cpp. Here, I have Ron, Harry, and Hermione once again. And on lines 13 through 23, you can see that for each of them, I invoke print details, compute total salary, and compute special bonus. Let's run this code and see what the result looks like. On the console output, we have the details for Ron, Harry, and Hermione, along with their total salary. And then we also include the special bonus and print out the final salaries for each employee. When you're writing code and modeling entities in the real world, it's quite often the case that you have to use inheritance or is a relationships to model these entities. For example, when you have employees, some of these employees might be full-time employees and contract employees, and then you'll set up an inheritance relationship where full-time employees and contract employees derive from employee. Once you set up the inheritance hierarchy, it's quite possible that you might want to re-implement some of the methods in the base class. This is referred to as overriding the functions in the base class. Now, keep in mind that you should only override virtual functions. If you try to re-implement non-virtual functions from the base class, this leads to inconsistent behavior. Different versions of the function will be called on the object based on whether you're holding an object of the base class type or the derived class type. So you're essentially changing the implementation based on the type of object that you're holding, which is strange. This will become clearer with an example. Here is my employee base class. Every employee has an ID, name, and salary. These are the member variables on line 8, 9, and 10. We have a constructor defined on line 14. We have a getter get salary marked as const, which returns the salary of the employee. On line 20, we have a method compute total salary also marked const, and print details is also const. Let's look at the implementation of this employee class. This should be fairly straightforward. Compute total salary, you can see on line 13, simply returns the base salary of the employee. And print details print out the ID name and salary of that employee. Employees may be contract employees and they will be represented using the contract employee derived class. You can see on line 6, contract employee publicly inherits from employee. The private member variables over and above the member variables in the employee base class include overtime rate and overtime hours defined on lines 9 and 10. The constructor for a contract employee defined on line 14 takes in a couple of additional input arguments, overtime rate and overtime hours. Let's look at the implementation of this contract employee class. I have the constructor on lines 10 through 14, which initializes the member variables of the employee base class as well as overtime rate and overtime hours, which is part of the contract employee class. Now, notice that I have a new implementation for compute total salary on line 16. So, I have re implemented or overridden compute total salary in the contract employee class to account for the overtime rate that contract employees are paid, but the compute total salary in the base class was not marked virtual. Similarly, I have also overridden the print details method in the contract employee to print out the overtime payment to the contract employee, but print details was also not marked virtual in the employee base class. Employees may also be full-time employees. Let's look at the header file for these. You can see that for a full-time employee, there is an additional bonus percentage. That's the private member variable on line 9. The constructor for the full-time employee also takes in the bonus percentage as an input argument. You can see this on line 14, in addition to the other details of an employee. Let's look at the implementation of our full-time employee class. The constructor on line 10 takes in the bonus percentage as an additional input argument and initializes that. Compute total salary is once again re-implemented. We've overridden a non-virtual function in the base class. So the total salary now includes a bonus for this full-time employee. Print details also prints out the bonus percentage as well. So print details has also been overridden and we know that it's not a virtual method in the base class. Now this is going to cause us some problems. Let's head over to main.cpp. We have three employees, Ron, Harry, and Hermione, defined on lines 11, 12, and 13. Ron is of the base class type, Harry is a full time employee, and Hermione is a contract employee. We then invoke Ron.printDetails, Harry.printDetails, and Hermione.printDetails on lines 15, 18, and 21. We also compute the total salary for Ron, Harry, and Hermione on lines 16, 19, and 22. Now, because Ron, Harry, and Hermione are of the right type, employee, full time employee, and contract employee, respectively, all of these functions will work as expected. The print details and the compute total salary of the derived classes will be called, as you shall see when we run this code. On line 11, we can see that Ron is of type employee. In the output, you can see Ron has only his base salary of 123,000. On line 12, you can see Harry is of type full-time employee, so he has an additional bonus. And in the output, you can see that his bonus percentage is 5 and his total salary is a little more than his base salary because he gets a bonus. On line 13, you can see that Hermione is a contract employee, so she gets overtime pay. And in the output, you can see that Hermione's base salary is 50,000 with overtime, she gets $53,000. So everything work as expected because Ron, Harry, and Hermione are of the right type. But now, what if I introduced a new function, print employee details on line 9, which takes a constant reference to an employee as an input argument? It then calls print details and computes the total salary of the employee. Now, within print employee details, I only have a reference to the base class type. I do not know whether this is a full time employee, a contract employee, or just a plain employee. And now our overriding of non virtual methods is going to cause problems. I have Ron, Harry, and Hermione, employee, full time employee, and contract employee, respectively. And then I pass in these as input arguments to print employee details on lines 20 through 22. When I compile and run this code, the output is going to be kind of unexpected. When you see the output, you might expect that for Harry, the bonus percentage is included in his total salary, and for Hermione, her overtime hours. But that is not the case. Because print employee details only had a reference to an employee object, the base class implementation of compute total salary was invoked. That's because this is a non virtual method. Overriding non virtual methods will invoke the implementation based on the data type. And this is not the runtime polymorphism we expect in C++. So we've completely lost runtime polymorphism by overriding non-virtual methods. In the console output, you can see that the base class implementation of print details are called for all three, Ron, Harry, and Hermione, and their total salary also just includes their base salary. No overtime pay, no bonus for Hermione and Harry, respectively. What do you need to do to fix this? Well, make sure that you only override methods that are marked virtual in the base class. Here, we can head over to employee.h and make sure that compute total salary and print details are both virtual. Just use the virtual keyword and that's it. This will fix our code. So, contract employee can now override compute total salary and print details, as can full time employee. That is totally allowed. So the implementations here can remain as is, nothing needs to change. So now we'll go back to main.cpp and recompile and rerun this code, and this time the code will work as you expect it to. Even though print employee details only has a reference to the employee object, when employee.print details is invoked on line 10, the right implementation of print details based on the runtime type of the employee will be invoked. The same thing is true for compute total salary. If you're a contract employee, your overtime hours will be included. If you're a full time employee, your bonus will be included. The right implementation of compute total salary will be invoked. You can see from the console output that Harry has got his bonus back and Hermione has her overtime pay. So, to take advantage of runtime polymorphism that C++ offers, make sure you pass the methods that need to be overridden in the derived classes as virtual in the base class. In this demo, we'll discuss the perils of object slicing in C++. Now, if you have an inheritance hierarchy, you'll have variables which can be of the base class type or the derived class type. Now, if you try to assign a derived class to a base class type, you'll find that members of the derived class might be sliced. This happens when a derived class object is copied to a base class type. And this is object slicing. Object slicing is far easier to understand with an example, and that's exactly what we'll look at here. I have a class employee, and I have two derived classes, contract employee and full time employee. An employee has a name, ID, and salary. We have a constructor for the employee on line 14, a getter for salary on lines 16 through 18, and we have compute total salary and print details, both of which have been marked as virtual functions. This is the same employee class as in the previous demo. There is no change to the implementation of this employee class as well. We have the constructor on lines 9 through 11. Compute total salary simply returns the base salary. This is on lines 13 through 15. And print details on lines 17 through 21 prints out the details of the employee. Let's look at contract employee. On line 6, you can see that contract employee publicly inherits from employee and has an overtime rate and overtime hours for each employee. The contract employee implementation has again not changed from the previous demo. We instantiate the contract employee by specifying the overtime rate and overtime hours. We have overridden compute total salary on lines 16 through 20 to add the overtime rate multiplied by the overtime hours to the base salary, that is the total salary of the employee. And we've also overridden print details to print additional information about the overtime payment to the employee. We have the full-time employee class on line 6. You can see that full-time employee publicly inherits from employee. Every full-time employee gets a bonus. So we have a bonus percentage member variable on line 9. And if you look at the implementation of full-time employee, this class has overridden the compute total salary and the print details method from the base class. Now, all of this overriding is completely fine because these methods are virtual in the base class, the base employee class. The main.cpp code is also the same as before. For the time being, we'll make changes in a bit. You can see that we have Ron, who is of type employee, Harry of type full-time employee, and Hermione is a contract employee. We invoke print employee details and pass in Ron, Harry, and Hermione. This is the code on lines 20 through 22. Now, pay close attention to the input argument of the print employee details function. You can see that it is a const reference to an employee. It's a const reference, which means the employee object will not be copied into this input argument. Instead, a reference to the original employee object passed in. That's what this function uses. When the input argument to a function is a reference to an object, for all of the overridden virtual functions, you'll see runtime polymorphism. So when employee.print details is invoked on line 10, the right methods for the contract employee, the full-time employee, and the base employee will be called. The same thing is true for employee.compute total salary, the invocation on line 11. The right implementation of this method will be called based on the runtime type of the object. That is, now if you were to compile and run this code, everything would work as expected. You can see from the output that Ron, who is just an employee, has only the base salary. Harry, who is a full-time employee, gets a bonus and his total salary is a little higher. Hermione, who is a contract employee, gets the base salary plus overtime. So the right methods have been invoked on the employee object, which has been passed in by const reference. But what if you were to tweak the input argument just a bit? Let's say I were to get rid of this little ampersand here, which tells the compiler that the employee object is to be passed in by reference. This very small change, which seems tiny, almost trivial, has profound implications. What this means is that the employee object passed into the print employee details will now be passed by value. So when you invoke print employee details with an employee object, the copy constructor of the employee base class will be invoked to copy over the employee information to this input argument, and that copy is what is used within the print employee details method on lines 10 and 11. Creating a copy of an object is a wasteful operation and it takes up additional memory. Now, if that were the only problem, well, this is a performance issue, but there is one other problem. Remember that employees can be full-time employees or contract employees. Harry is a full-time employee and Hermione is a contract employee. When we call print employee details on line 21 and pass in Harry, now Harry is of type full-time employee, but the copy constructor of the employee base class is what will be called. So the additional information in a full-time employee, the bonus information, well, that will be sliced off. Object slicing will occur. The bonus information will be completely lost in the employee, passed in as an input argument to print employee details, and we won't get runtime polymorphism. So only the base class details will be printed out for Harry. The derived class details have been lost. And the same is true for Hermione. The invocation of print employee details with Hermione as an input argument on line 22 will result in object slicing. Only the base class copy constructor will be called. All of the additional information in a contract employee, the overtime hours, the overtime rate, all of those details will be sliced off. So when we print out the details for Hermione within print employee details, only the base class information will be printed out. Let's see this in action. I'm going to very quickly compile and run this code, and you can see that the output for Ron, Harry, and Hermione looks exactly the same. Even though Harry is a full time employee and Hermione is a contract employee, the additional information about the derived classes that represent these types of employees has been lost. Object slicing, because of the input argument type on line 9 in print employee details, has caused this. Within print employee details, the additional information about full time employees and contract employees has been lost. So, print details only prints out base class details, and compute total salary only gives us the base salary. The way we specify our input argument has resulted in object slicing here, but object slicing can occur in other types of code as well. Let's take a look. I have tweaked the code in main.cpp. We still have Ron of type employee, Harry of type full time employee, and Hermione of type contract employee. This is the code on lines 11 through 13. Now, let's say I want to assign these objects to other variables. This is what I have done on lines 15 through 17, but all of these variables are of type employee. So, Ron emp, Harry emp, and Hermione emp are all of type employee, and I assign Ron, Harry, and Hermione to these variables respectively. Now, object slicing will occur on lines 16 and 17. What we are doing here is assigning objects of the derived class type, full time employee and contract employee, to objects of the base class type, employee. So the additional information in Harry and Hermione, information about the bonus, information about the overtime rate and hours, will be sliced off, and only the base class information will be left with Ron emp, Harry emp, and Hermione emp. So on lines 19 through 26, when we print details and compute the total salary for these copies, only the base class information will be printed out again. Let's try this. Let's go ahead and compile our code and then run our code. Thanks to object slicing, we've lost the derived class details available in the original Harry and Hermione objects. We only have the base class details, and those are printed out in our console window. Now, this happens even when print details and compute total salary have been marked as virtual. Object slicing really doesn't have much to do with the virtual keyword. Even with overridden virtual methods, object slicing can occur if you try to copy over a derived class type to a base class type. Once an object has been sliced, you cannot get back the original information, not even using casts. I've tweaked the code just a little bit here. Object slicing still occurs on lines 16 and 17, but I've tried to use a static cast on lines 19 and 20 to try and get the original Harry and Hermione objects back. And the red squiggly should tell you that there is a problem. So there is no suitable user defined conversion from employee to contract employee. The information that has been lost because of slicing cannot be gotten back. You cannot take the sliced employee object and try to get the original contract employee or full time employee back. No cast is going to help you with this. And if you try and compile this, it's a compile time error. When working with good, clean C++ code, you should ideally never have to cast your data types from one type to another. But sometimes you can't help it. Maybe you're working with some kind of third party library and you know that the object is of a particular derived class type, but it's available as a base class and you need to perform a cast. Here in this demo, we'll explore the different kinds of casts that you can use and why you should choose certain types of casts over the traditional C style cast. We'll continue working with the same inheritance hierarchy of employee, where the derived classes are full time employee and contract employee. Here is the employee base class with ID, name, and salary defined on lines 8 through 10. We have the constructor for the employee on line 14, a getter for salary on line 16, and we have a virtual method print details defined on line 20. As you can see, this is a fairly simple class. We have an implementation for print details in the employee base class along with the constructor. Let's take a look at the header file for the contract employee class where I've made a few changes. Now, a contract employee has an overtime rate, and we have the number of hours the employee has worked. The new method that I've added to a contract employee here is on line 18, get overtime pay. This is a const method. This basically computes and gives you the overtime pay for a contract employee. The constructor and the print details are as you would expect, no change from the previous demo. Let's look at the implementation of the contract employee in contractemployee.cpp. The constructor on lines 10 through 14, that remains the same. We have the implementation for get overtime pay, which is simply the overtime rate multiplied by overtime hours. And we have the print details where we print out the overtime information as well. The full-time employee class that derives from the employee base class has the bonus percentage as an additional member variable. This is on line 9. There is also a new method available only for full-time employees, the get bonus pay on line 16. This is a const method. It simply computes the bonus pay for every full-time employee. The constructor and print details, we're familiar with those. The implementation of full-time employee should contain no surprises. Take a look at how get bonus pay is implemented on line 15. So we get the base salary and we multiply that by the bonus percentage and multiply that by 0.01. It's now time for us to take a look at our client code in main.cpp. I've instantiated 3 full-time employees. Ron, Harry, and Hermione are all full-time employees in this example. This is the code on lines 21 through 23. I then invoke the compute total cost function and pass in Ron, Harry, and Hermione to get the total cost to company of employing these 3 employees. Now, this is the code on line 25, 26, and 27. Turn your attention to line 9, where compute total cost is defined. You can see that the input argument to compute total cost is a reference to employee, so employee ampersand. So within the compute total cost function, we only have the employee object. But we want to invoke methods that are available on full-time employee. How do you do that? Well, this is when you kind of scratch your head and say, I'm going to have to perform a cast. There is no other way. The only way here of getting a full-time employee from an employee object is to perform a cast, and that's fine. If that's what you want to do, you need to go ahead and do that. This is again only if you have to. But look at the casts that we have employed here on line 11. On line 11, we are using a C style cast. The C style cast essentially is a bracket with the type of the object that you want to cast to, which in our case is full-time employee. So we are taking the employee reference and casting it to be a reference of type full-time employee. Whenever the compiler encounters a C style cast, essentially what you're telling the compiler is do whatever it takes by hook or crook. Just try and make this object a full time employee, whether or not it is a full time employee. And this is exactly why C style casts are very, very bad. You should never use these in your code because this essentially does not care what type employee actually is. It'll just try to forcibly cast it as a full time employee reference. Now, here we know we are okay for this particular small bit of code because Harry, Ron, and Hermione are all full time employees. Once we've performed the cast on lines 13 through 15, we print out the details of the employee and the total cost to company, which is the salary plus the bonus pay of the full-time employee. We wanted to invoke get bonus pay, and that's why we had to perform this cast. So now if we compile and run this code, everything will seem great. We've successfully computed the total cost to company for each of our full-time employees, Ron, Harry, and Hermione. But the C style cast is insidious. There is no way to search and find such casts in your code. And if the cast does not work, you're basically left to your own devices trying to debug this. I've made a teeny change to the code here. Harry and Hermione are no longer full time employees, they are contract employees. And I have invoked compute total cost on both Harry and Hermione on lines 25 and 26. Now on line 11, I have a C style cast to convert the employee passed in to an object reference of type full-time employee. And that's the one that's going to fail. The thing is, with the C style cast that we've used, the failure will not be obvious. It's not that an exception is thrown that we can catch and debug. Our code will simply take the memory occupied by our contract employee object and try and interpret that as a full time employee, as we'll see when we run this code. You can see that the output for Ron is correct. So 123,000, bonus percentage 3, and then the total cost to company around 126,000. Take a look at Harry. He is a contract employee. So overtime seems to have been printed out, but the total cost is completely garbage. It makes absolutely no sense. How did we even invoke get bonus pay on a contract employee? And how did we get the number of 534,000? I have no idea. C++ just kind of force fitted our contract employee to be a full time employee and did some garbage. The same thing is true for Hermione as well. How did we ever invoke get bonus pay on a contract employee, and how did we get this number of $100,000? So the output that you get with these casts is unpredictable. The cast won't even let you catch errors. And these C style casts are insidious because you can't even easily track them down and fix them. If you have to perform casts, use the static cast rather than the C style cast. I've made two changes to this code. I've switched Harry and Hermione back to being full time employees, and on line 11, I have used the static cast to cast the employee input to be of type of reference to full time employee. Now, if you're awake and paying attention, a good question to ask me at this point would be, how is this static cast helping? How is the static cast an improvement over the C style cast? And I'd have to tell you, they're exactly the same. And you'd be like, why do we need the static cast instead? So the implementation and the end result of using the static cast versus the C style cast is the same. But the fact that we're using the static cast makes it very clear to all of the readers of our code that this is a casting operation. And later on down the road, if you're cleaning up your code and you want to get rid of the cast, the static cast keyword makes it very easy for you to search for static cast and get rid of them if you can. The static cast has an extremely ugly syntax. It's an ugly operation, and that is why we have to do it the hard way rather than just performing a C style cast, and then you'll never be able to find where the casts are in your code for cleanup. So make sure you use the static cast rather than the C style cast. You'll find that they work in exactly the same way. The result shows you that the casts were all successful, and we've computed the total cost to company for Ron, Harry, and Hermione, all full time employees. But what if we try to cast the wrong kind of object? I'm going to change Harry and Hermione to be contract employees rather than full time employees once more. The only change is on lines 21 and 22. Harry and Hermione are contract employees with overtime pay. When I compile and run this code once again, I'll get the same garbage in my output that I got with the C style cast. Our static cast on line 11 has forcefully converted our contract employees, Harry and Ron, to be of type full time employees to invoke the get bonus pay method. But the output is not really meaningful. We have overtime information, but somehow that overtime information has been used as a bonus percentage to compute bonus pay. The output is garbage. So static casts do not warn you about wrong casts that cannot be performed. It'll just perform the cast exactly like how C style casts do. But it's easier to search for, and you know where the problem might lie. In the previous video, we've seen how a static cast works. We've seen that the static cast is used for cases where you basically want to reverse an implicit conversion. An implicit conversion has occurred, and you need to get the original type of the object back, and you're completely sure that this will not cause any errors. If you're not sure of the actual type of the object, using a static cast is actually dangerous. The static cast can only be used in cases where we are absolutely certain that the cast will not fail. We are sure that this particular object is of type full time employee, so let me cast it to be of type full time employee. Those are the cases where the static cast makes sense. But what if you're not sure? What if you want some additional checks to ensure that you're not casting to the wrong type? Well, in that case, you would use the dynamic cast. The dynamic cast is a much safer cast to use, and it is an intelligent cast. It will only perform the cast if the object can be converted to the target type safely. So, if you want to perform an intelligent and safe cast, use the dynamic cast instead. The dynamic cast is extremely useful when we do not know the actual runtime type of the object. The employee can be a full time employee or a contract employee. We don't know what the runtime type is. And if we feel that the cast has a chance of failing, use the dynamic cast. The dynamic cast, if it cannot cast to the target type, will either return a null pointer or throw a bad cast exception, and you know that your cast has failed. So you're not trying to do something unsafe, your program doesn't return some garbage silently. In our code here in compute total cost, we have a reference to an employee as an input argument. We use dynamic cast to try and convert that employee to a full time employee. And we'll print out the details and the total cost to company of the employee. In our main function, we have three full time employees, Ron, Harry, and Hermione, and we pass these employees to compute total cost. Now, since all three are full time employees, the dynamic cast should succeed in all three cases. Since the cast will succeed, the dynamic cast works exactly the same way as the static cast and the C style cast did. We have Ron, his bonus percentage, and his total cost to company, and the same thing for Harry and Hermione as well. Everything looks good. But what if both Harry and Hermione were contract employees? Earlier, when we used the C style cast and the static cast, it silently gave us the wrong answer and it performed the cast just fine. What does the dynamic cast do? Let's compile and run our code and see. Dynamic cast was unable to convert our contract employee to a full time employee, and it basically threw an exception. This is a bad cast exception and the program was aborted. Getting exceptions in your code is a great thing because you know where the error is. If you try to perform the wrong kind of cast, the dynamic cast will stop us. So, that is the preferred way to cast from one type to another. Now, when you first heard of C++, people likely told you C++ is extremely hard because you have to manage memory yourself. Now, modern C++ almost completely eliminates the need for you to manage your memory directly. However, memory management is still hard if you're working with raw pointers, and that's what we'll look at here in this demo. We'll see how the use of raw pointers makes it very hard for you to manage your memory, especially if your code can throw exceptions, as all code likely will. We'll see how you can use the unique pointer from the standard library in order to avoid managing your own memory and let C++ do it for you. Here I have a class named resource, which can stand for any kind of resource that needs to be cleaned up. This can be a database connection, a socket, anything. I imagine that we connect to this resource using some kind of connection string. So on line 8, I have defined a private member variable called connection string. This resource has a constructor which accepts the connection string as an input argument. This is on line 12. I have also defined a destructor for the resource, which will clean up all of the connections made by this resource. This is on line 14. And finally, we expose this connection string using a getter get connection string on line 16, which is a method that is of the const type. It simply returns the connection string. Let's look at the implementation of this resource class. I have the constructor which accepts the connection string. We use the initialization list on line 10 to initialize this string, and I simply print out to screen constructing. We don't actually set up any of the resources or any of these things for this demo. Take a look at the destructor on lines 15 through 17. We'll simply print out destructing and the connection string for this resource. Now, with this constructor and destructor, we'll always know when an object is constructed and when it goes out of scope. Now, in main.cpp, we'll create a new resource, but on the stack on line 22, you see that we have created a resource object with the connection string named MySQL connection. This object is on the stack. Now you're familiar with C++, you know that objects on the stack are cleared up or destructed, their resources released, their memory freed when they go out of scope. Observe that on line 21 and 25, I have the open close curly braces. This is a nested scope within my main function. Our resource on the stack will be constructed on line 22. It will go out of scope on line 25 when the destructor of the resource will be automatically called by C++ because this is an object on the stack. But before that, we'll do something with our resource. Look at the function do something with resource on line 24. It accepts a reference to the resource as an input argument and simply prints out the connection string of the resource. Let's run this code and see how it works. We'll compile it. And when we run this, you'll see that we construct MySQL connection on line 22. We then do something with the resource that just prints out MySQL connection. And when this object on the stack goes out of scope, which it does when it encounters the closing brace on line 25, it will be destructed. So destructing MySQL connection will be printed out to screen. But what if this resource object was constructed on the free store, the heap? Then all we'll have on the stack is a pointer to this resource. On line 22, you see that we have a pointer to the resource, p resource. We construct the resource using the new keyword. This new keyword allocates memory for the resource on the heap or the free store. The resources again has the connection string MySQL connection. We then do something with the resource on line 24. Do something with resource now accepts a resource pointer as an input argument. We use the arrow operator on line 16 to print out the connection string for this resource. Because this resource object is created on the free store, the heap, and not the stack, the resource memory will not be automatically cleared up when the pointer goes out of scope. So on line 25, when we encounter the closing curly brace, the resource will not go out of scope. Let's compile this and you'll see that even though the resource is constructed, it will not be destroyed automatically. When we allocate objects on the heap, it's up to us to free up its memory. We have to explicitly delete our resource to free up its memory. And that's exactly what I have done here. The change to the code that I have made creates a pointer to a resource on line 22. I then do something with this pointer to the resource. And on line 26, I'm explicitly calling delete on p resource. So you have to ensure that every new, the new is on line 22, is matched up with a delete. Our delete is on line 26. At this point, you should feel pretty happy that you've done the right thing. You have cleared out any memory that you've allocated to your resource. So you can see that we construct the resource and the resource is destroyed as well. The destructor is called. The delete keyword on line 26 is what calls the resource destructor. But what we have here is just the best case, the happy path as it's called. What if do something with resource were to throw an exception? An exception basically stops the execution of your code right there. And that means that delete p resource on line 28 will never be called. Your memory will never be freed and you'll let a memory leak. The change that we've made to do something with resource is to have it throw an invalid argument exception. Something bad happened. Now, the exception will be encountered on line 26 where we invoke do something with resource. Delete p resource will never be called. Let's compile and run. You can see that we constructed our resource on line 24. That was successful. We printed out the connection string. That was successful as well. But then we encountered an exception. The invalid argument basically stopped the execution of our program and we leaked memory. Delete p resource was never called. The lesson here is memory management in the presence of exceptions is hard. We have to account for the fact that exceptions change the path of our code. If you know your code can throw exceptions, you might try to write defensive code like what I have done here. So I have created a new resource on line 24 using the new keyword. Then within a try block, I do something with the resource. And if that was successful, I delete the p resource within the try block itself. That is on line 28. I also have a catch block where I explicitly catch the invalid argument exception. If we encounter that exception, We execute the code in the catch block. We'll print out the message of the exception. Once again, I delete the p resource on line 32. When you handle exceptions, you have to remember to free up memory in the catch block as well. And you can see that this code is pretty ugly. And if your code was more complex than this demo, it's hard to figure out all the places where an exception might occur and you have to clean up resources. This will work correctly. If you try to run this code, you'll see that the resource that we created has been destroyed even though an exception was thrown. So even though something bad happened, we call the destructor for MySQL connection. In general, working with raw pointer resources is not a good idea. So what should you do instead? Well, you should use the unique pointer available as a part of the standard library. A unique pointer is a smart pointer available as a part of the standard library. This is a pointer that owns and manages another object through a pointer and then disposes of that object when the unique pointer itself goes out of scope. If you have a pointer resource in your code, the right way to manage it is by using a unique pointer or one of the other smart pointers in the standard library. The unique pointer is the smart pointer that you'll choose when you do not want multiple objects referencing the same pointer object that the unique pointer is managing. Let's see how we can use the unique pointer to manage memory. You can see on line 12, I have the using statement for make unique. That's what I use to create a unique pointer. And on line 11, I have a reference to the unique pointer from the standard library. Now, within the main function, you can see that I have created a unique pointer on line 25. The smart pointers should always be created on stack, but they'll hold a pointer to the resource that you pass into the smart pointer. So the unique resource variable on line 25, which is of type unique pointer to resource objects, is on the stack. I use make unique to get and manage a pointer to a resource object, and the connection string for the resource is what I pass into the constructor for this. That is MySQL connection. Now I'm going to call do something with resource within the try block and I'll catch an invalid argument exception. Observe that I haven't deleted my resource anywhere. I've just used the unique pointer and that'll take care of it. If you look at the do something with resource function, you can see that it takes a reference to the unique pointer as an input argument. Observe that with this reference, we can access the connection string exactly as though we were dealing directly with the pointer object. This is on line 17. I then throw an invalid argument exception. Notice that we haven't explicitly created our resource object or deleted it anywhere in this code. That is managed for us by the unique pointer. When it goes out of scope, the resource memory will be cleaned up. Let's compile this code and run this to see this in action. You can see our MySQL connection resource was created. The MySQL connection was printed out to screen. Then something bad happened. That is our invalid argument exception. And in spite of that exception, the destructor for our resource was called. That's because on line 33, with the closing curly brace, when the unique resource went out of scope, the corresponding resource that it manages, our connection, was also cleaned up and its destructor called. We didn't have to manage the memory of that resource ourselves. Now, let's say that our do something with resource does not throw an exception. What happens then? The unique pointer will still take care of managing the resource. Let's run this code. The make unique on line 23 constructed our resource pointer. The connection string was then printed out. And then on line 31, with the closing curly brace, the unique resource, unique pointer went out of scope. And when it went out of scope, it also cleaned up any pointers that it was managing, which is our resource pointer. And that's why our resource was destroyed. That's why its destructor was called. In this demo, we'll discuss what the static initialization order fiasco is all about, and we'll see some techniques that you can use to avoid this fiasco. Now, the static initialization order fiasco occurs because of the order in which your C++ object classes may be compiled. As the name suggests, the static initialization order fiasco has to do with variables which have static storage duration and dependencies on those variables. Variables which have static storage duration may be global namespace variables, static variables, or static class members. So, this fiasco occurs in the order in which these static variables are initialized. And we'll see an example where we run into this fiasco, and we'll also see how we can work around such fiascos. The static initialization order fiasco occurs in C++ because of the way translation units in C++ are compiled and then linked together. What is a translation unit? A basic unit of compilation in C++. This is usually one source code file, one CPP file, which includes all of the headers after the file has passed through the preprocessor. This means that all of the header definitions in the header files that have been included are now part of that one CPP file. That entire single CPP file is compiled in one go, and it's called a translation unit. So if you have multiple CPP files in your project, each CPP file will be a translation unit. The compilation and linking process and the execution of C++ works in such a way that all of the static variables in one translation unit are initialized according to their definition order. In contrast, the initialization of static variables between translation units has an issue, and this issue is referred to as the static initialization order fiasco. Let's see an example, things will become clearer. In this demo, I have two files in my project, circle.cpp and main.cpp. The main.cpp file depends on circle.cpp. Each of these files is a translation unit. Let's look at what's in circle.cpp. I have a function which gives me the area of a circle once I've passed in a radius. That's just pi r square. I have a global variable, that's a static variable defined on line 6, and this global variable holds the area of a circle of radius 10 by invoking area of circle and passing in 10 and storing the result. This is my first translation unit. Let's now head over to main.cpp and look at the second translation unit. This second translation unit depends on circle.cpp, the first translation unit. On line 6, you can see that I reference the global variable global area circle 10. This is an extern. The extern keyword tells the compiler that this variable is defined in another source module outside of the current scope. The linker then finds this actual declaration and sets up the extern variable to point to the correct location. So this within main.cpp, we reference global area circle 10 defined in circle.cpp. Then on line 8, I have a static variable in this translation unit called area circle 10, which basically references global area circle 10. So it gets its initial value from the global external variable, which has been initialized in the circle.cpp translation unit. This essentially means that the initialization of a variable in this translation unit, main.cpp, depends on the variable in circle.cpp having already been initialized. At this point, if global area circle 10 is not initialized, the initialization of area circle 10 will be wrong. Within our main method on line 12, we simply print out the area of the circle with radius 10 and we reference the variable initialized in this translation unit, area circle 10. So we know what value it has been initialized with. Let's now compile and run this code in the regular way and see what result we get. What value is area circle 10 initialized with? And the answer that we get in the console output is the area of circle with radius 10 is 314. This means the variable area circle 10 defined on line 8 of our code here in main.cpp has the right initialized value. So things seem to look good. This program actually worked because of pure luck. It's not actually well formed because there is no guarantee as to which order the translation units themselves will be linked together. Will the global area circle 10 initialized in circle CPP be initialized first or the area circle 10? Here we happen to get lucky that we got the right output. Let's see an example where things can go horribly wrong. I'm going to run an ls-l. So you can see I have the a.out and the other related output related files here. I'm going to get rid of all of the a.out files so that we can compile and link afresh. So you can see I just have circle.cpp and main.cpp left. I'm now going to explicitly compile circle.cpp and get the object code for circle.cpp. So if I run ls-l after compilation, you see that I have circle.o, that is the object code for circle.cpp. I'll now separately compile main.cpp as well using clang++. Main.cpp should produce object code in a file called main.o. And the ls-l tells me that main.o has also been generated. I'm now going to link these files together to produce the final output. Observe the order in which I link these files together: circle.o and then main. This means the code in circle.o will run first, and the global area circle 10 in circle.o will be initialized first, and then the code in main.o will run, and the area circle 10 will be initialized. So circle then main has circle running first and then main. I'm now going to produce another executable, but this time I'm going to link the files in a different order. I'm going to have main first and then circle, which means the code in main will run first and then the code in circle.o. This means area circle 10 will be initialized before global area circle 10, and that's going to be a problem. I'm going to run ls-l and you can see that the two executables have been created: circle then main, main then circle. You'll find that if you were to run the executable circle then main, you'll get the right response in your console output. The area of the circle with radius 10 is 314. That's because the circle code initialized global area circle 10, and that value was then used to initialize area circle 10 within main.cpp. But if you were to run main then circle, you'll immediately find a problem. The result you get is completely different. The area of circle with radius 10 is 0. Why did this happen? That's because main was initialized first. Area circle 10, whose value was initialized using global area circle 10, essentially got the value of 0 because global area circle 10 in circle.cpp hasn't been initialized at that point in time. It's initialized later on, but we already have the wrong value for area circle 10. This program is wrong. This is the static initialization order fiasco, and we need to fix it. How do we do it? Let's change the way we initialize our variables in both of these CPP files. I'm going to change the code in circle CPP. Rather than using a static variable in circle.cpp, I've set up a function which gets me the area of circle 10. On lines 5 through 9, I've defined this function. You can see that it uses a static variable within the function on line 6, but you can see that when we ask for the area of a circle with radius 10, we'll have to invoke a function in main.cpp. The fact that we are not accessing a static variable in circle.cpp gets the compiler and the linker to do the right thing. In main.cpp, you can see that I initialize the variable area circle 10 using the function from circle.cpp, get global area circle 10. The fact that we are invoking a function will ensure that function initializes the variable correctly for a circle of area 10 and returns the right value to initialize this particular variable. In order to demonstrate that things work correctly, I'm just going to delete all of the outputs that we got from the previous run. So I'm going to delete all of these files. Let's start afresh. I'm going to run clang++ on circle.cpp to produce circle.o. I'm going to run clang++ on main.cpp and that will give me main.o. When I run ls-l, you'll see that we have both circle.o and main.o. These are the new object files for the updated code in main and circle. We'll now link these files together. First circle and then main to give us the executable circle then main. Here circle will be initialized first. I also produce main then circle where I link main first and then circle. Let's run ls-l and ensure that these executables are present. You can see circle then main then circle. Things look good. But what happens when we run these executables? I'll first run circle then main. This gave us the right output previously. It gives us the right output now. The problem was when we had linked in main first and then circle, and the initialization of static variables in main depended on circle. This time around, you'll see though that the area circle 10 defined on line 8 in main.cpp gets the right value. That's because we initialized this variable using a function invocation. This function invocation is invoked at runtime. The right computation is performed within circle.cpp, so we are not dependent on the initialization order between translation units, and we have the right output. Essentially, what we've done in circle.cpp is lazily initialize the static variable global area circle 10. This is the code on line 6. It's lazy initialization because the initialization will only occur when we invoke the method get global area circle 10. In order to avoid the static initialization order fiasco, don't have your translation units depend on static variables initialized in other translation units. Use lazy initialization instead. When you're writing code for your project, you'll often find the need to use collections. Collections are basically container objects that hold other objects that you need to keep track of. Based on your use case, you might need different types of collections. Maybe you just need a simple list which stores your data in an ordered sequence. Maybe you need a set which stores unique elements. Maybe you need a map which stores your data in the form of key value pairs. No matter what your use case, it's highly unlikely that you'll roll your own collection data structure when you can use one from the standard library. The standard library in C++ originally used to be called the standard template library, and it contains a wide variety and range of containers that you can use out of the box. All of these containers are collections which are implemented as class templates, which means that you have a lot of flexibility in the kind of data that you can store in the containers of the standard library. You want your elements in an ordered sequence? Use the vector collection. You want key value pairs? Use the map. All of these are available in the standard library, and that's what you should be using. The collections in the standard library offer you a wide variety of methods that you can use to access the elements in the container, add elements to the container, remove elements from the container, and so on. However, there are certain good practices that you need to follow while accessing elements in the container, and that's what we look at here in this demo. The container that we'll work with is very straightforward. We'll use the vector. A vector is a container used for storing data in a sequential order. Vectors are major advantages over arrays because they can hold additional elements and expand as needed. The capacity of a vector is not fixed. The vector takes care of moving things and expanding its capacity under the hood. Let's look at this simple code that we have here on screen and understand the best practices involved in using square brackets to access the elements of a vector versus the at method. You see that I have included the vector header file on line 2. And on line 8, you can see the using statement using std vector. I've instantiated a vector on line 11. It's a vector that contains string data types. It's a vector of names, and we have Alice, Bob, Charles, Dora, and Elise. These are the names contained within the vector. All I've done on lines 13 through 17 is used cout to print out the names at the different indices of the vector using the at method. So names at 0 will give us Alice. Vectors are 0 index based, just like arrays in C++. Names at 1 will give us Bob, and names at 4 will give us Elise. That's all this code does. Very straightforward. As is obvious from here, the at method is used to access elements at specific indices in a vector. And the at method is what you should prefer to access elements. Let's see first how the at method works. So I go ahead and compile this code and I'll run it. And you can see all of the names nicely printed out on the console window. Nothing really interesting here. But what if we try to access a name at an index that is out of bounds? Names at 10 would be a valid access if I had 11 elements in my vector and I don't. So clearly, this is wrong. Let's see what the at method does when you try to access an element that is out of the range of elements present in the vector. So we'll compile and run once again. When you run this code, you'll immediately find that after printing out all of the valid accesses using at, I get an exception. The at method has thrown an out of range exception, indicating that we have an invalid access that is out of the range of the elements in that vector. And that is great. Improper access has been detected. And this exception ought to make things easy for you to debug and fix. Now, vectors also allow you to use the square bracket notation to access the elements of the vector. So, kind of like using arrays, and people are often tempted to use the square bracket notation because it's so intuitive and something that they're familiar with. And you can see from the console output that as long as you're accessing valid index positions using the square bracket notation, everything works just fine and you get the result that you expect. However, use of the square bracket notation to access the elements at specific indices suffers from one major drawback. The square bracket operator is not required by the C++ standard to perform bounds checking. And in fact, its implementation in several compilers, including GCC as well as Clang++, the bounds checking is not performed. In contrast, the at method must perform bounds checking. So if you have code that is not performance critical, you should prefer to use the at method rather than the square bracket operation. Let's use the square bracket to access the elements at indices 10 and 13. We know they're out of bounds. And if you compile and run this code, you'll find that we get Alice, Bob, Charles, Dora, and Elise, and we get nothing for the square bracket access of the elements at index 10 and 13. So there is no error at all. Bounce checking has not been performed. And I think it's the empty string that has been returned. Now, based on the type of data you use, this return value might be different. And basically, the operation of the square bracket access is not defined. So prefer to use at method to access elements in a vector rather than the square bracket operator. With this demo, we come to the very end of this course on writing defensive C++ code. We started this course off with a quick overview of the important points you need to keep in mind while writing C++. We discussed that you need to avoid fatal errors, write defensive C++ code, make sure that you follow sound programming practices, and try to follow good code readability practices along with other coding niceties. The rest of the course was very hands on, exploring defensive practices in C++. We saw how constructors should be specified only for valid object states and the need to think about whether objects are copyable and movable. We saw the pitfalls of overriding non virtual functions, which results in us losing runtime polymorphism for our objects. And we encountered object slicing when we inadvertently pass arguments by value rather than by reference. We also discuss the importance of using static cast and dynamic cast for casting rather than using the old style CCAS. We saw how smart pointers in the standard library can make our resource management on the heap store a lot easier, and we rounded this course off by discussing and understanding the static initialization order fiasco and seeing how we can avoid this. You are now armed with defensive C++ techniques and best practices and are ready to tackle the next course in this learning path, managing memory in C++. If you've worked with raw pointers and memory allocation and deallocation in C++, you know it is really hard. Modern C++ offers a number of techniques and libraries which are part of the standard library to help make things easy. Memory management in modern C++ follow the principle of resource acquisition is initialization. First, let's define modern C++. This is a colloquial term, it doesn't really have a formal definition. It's used to refer to the current style of C++ programming using light, precise components that use the type system and new features gainfully. This term modern C++ was originally popularized in the book Modern C++ Design, published in 2001 and written by Andrei Alexandrescu. So, how do you know you're writing modern C++ code? If you're embracing new features and new standards with every new C++ release, they give you a better way and the right way to do things. If you're writing C++ in exactly the same way as you did before the introduction of C++ 11 in 2011, well, what you're writing is classical or legacy C++. That's not modern C++. If you take advantage of all of the new features that have been offered in C++, starting from C++ 11 and going through to C++ 14, 17, and 20 today, well, that's modern C++. Here are some of the philosophical ideas behind modern C++. Use code to express your ideas. Make code meaningful in variable names and in function names. Write ISO standard C++. There is C++ that is the right way to do things, and there is C++ that is the hard way to do things. Make sure your code is written in such a way that your intent comes across to those who are reading and modifying your code. Write your code in such a way that your errors are compile time errors rather than runtime errors. So prefer compile time checks to runtime checks. Also, whatever cannot be checked at compile time should be checkable at runtime. It should be caught before production. If your errors are indeed runtime errors, make sure you catch them early. You can see that modern C++ philosophy has a lot of overlap with sound software engineering principles. Modern C++ also says that you should not leak resources. Well, all C++ says this, but modern C++ gives you smart pointers to help you manage these resources. Do not waste time or space, write optimal code. Prefer that your data is immutable rather than mutable. You should not be able to update your data unless you have to. Do not expose the internal details of your data structures and constructs. Encapsulate them. Make sure that you're using all of the supporting tools provided: IDEs, debuggers, profilers, and so on. And make sure you're using libraries rather than rolling your own implementation. Library code tends to be robust and well tested, and it's not your responsibility. Modern C++ relies heavily on the resource acquisition is initialization programming technique. RAII basically binds the life cycle of a resource such as memory. This is a resource that must be acquired to the lifetime of an object that is created on stack. This binding allows us to manage the resource on the heap or the free store using stack based constructs, which are much easier. Now, we all know that resource management in C++ is non trivial. Now, when I say resources, I refer to entities that exist in limited supply. Memory is an example, file handles are examples as well. A thread of execution is also a resource, an open socket is also a resource. Now, a word about memory: memory on the free store or a heap is a resource because it has to be explicitly acquired and released. Stack memory is managed by your C++ program. When you define variables in C++, so long as you're not using the new keyword, that object is created on the stack. So every object created on the stack has a specific lifetime, and that object's memory will be released when it goes out of scope, and that's handled by C++. By scope, I mean the nested pair of curly braces within which your stack object is created. So, when the program encounters the closing curly brace where the object has been created, well, that object will be released and will no longer exist. Managing the lifetime of stack based objects that come into scope and go out of scope is very easy for C++ to figure out. What about resources that you explicitly acquire? Memory on the free store or the heap, file handles, sockets. When are these acquired resources out of scope? And unfortunately, C++ cannot figure this out by itself because it has no idea how many different wrappers or parents share access to that resource. If C++ cannot figure this out, whose responsibility is it? Well, yours. So, any resource that is explicitly acquired by the program has to be explicitly freed by the program, and you have to decide when to acquire the resource and when to free the resource. Now, any resource cannot be safely released unless you're completely sure that there is no entity accessing that resource. If entity A and entity B are sharing a database connection, both have to stop using it before that connection can be released. So you need to keep track of all of the entities that have access to that resource and figure out whether they need it or not. Sounds quite painful, doesn't it? Also, this is error prone. The requirement is that a resource should always be released. Otherwise, you're leaking resources, such as memory, and soon your program will run out of memory. In addition, you should release your resource exactly once and not multiple times. Freeing up a single resource multiple times is an error in C++. And furthermore, you should ensure that your resources are released even when exceptions are thrown in your code. So you have multiple code paths along which you need to release resources. Manual handling of resources in C++ is hard, but exceptions make it even more difficult because exceptions change the execution path of your code. So you have to account for cleanup of resources in the presence of exceptions. Let's look at an example. Here is some simple dumbed down code. You have a file that you open up, file.txt. So you have a handle to that file. Then you do something with that file and close that file. Now, do something with that file might throw an exception, and if that happens, well, f.close will never be called. An exception in this method will terminate your program or change the execution path of your program. F.close will never be reached. Here is another example where we allocate memory on the free store or the heap. Memory is also a resource. We create a new resource object. We then do something with that resource and then we call delete on that resource object to free up memory. Resource is a pointer. Now, do something with resource might throw an exception, which means delete memory will never be called. So the memory will never be deallocated. Before we move on to RAII, let's understand some details of resource acquisition and release. Any object that uses a resource usually acquires the resource in its constructor. Any class that acquires resources in its constructor should have a destructor. So once an object of that class goes out of scope, the resource can be released in the destructor. So if you're working with resources, you need to ensure that you write destructors for your classes. That is your responsibility. It used to be that the classes that you write in C++, if they are managing resources, need to follow the rule of three. So, any class that acquires resources, such as memory on the free store, a file handle, a socket, anything, needs a custom destructor. Once you have a custom destructor for a class and objects of your class can be copied, well, you also need your own custom copy constructor. You need to implement your own copy constructor. And finally, any class with a custom destructor also needs a custom copy assignment operator in order to be able to assign objects of this class to other variables. Now, C++11 introduced the concept of move semantics. Move semantics allow you to move the ownership of a resource to another object while you give up ownership. So it's different from copy semantics. Once we had move semantics, rule of three became rule of five, which meant that classes with a custom destructor need to have a custom copy constructor and a custom copy assignment operator. That's what we discussed before. In addition, these classes also need the custom move constructor and a custom move assignment operator. Now, moving the rule of 3 to become a rule of 5 means more burden on the developer. Managing resources has just become harder. Well, instead of the rule of 3 or rule of 5, you should just follow the rule of 0. It's important that you realize that the rule of 3 and rule of 5 are only for those classes with exclusive ownership of resources. Other classes, if you do not own resources, can just follow the rule of 0. They need not set up their custom implementations of copy and move constructors or even the destructor. They can use the implicit compiler generated definitions of constructors, destructors, and assignment operators. These do the right thing for stack based resources. Given a choice as a programmer, I want to follow the rule of 0. I want to avoid managing resources because it's just too hard. So the question now is, how can you design your classes in such a way that they can follow the rule of 0? Well, delegate your resource management to a class in the standard library that implements RAII. Resource acquisition is initialization. If you remember, RAII is the C++ programming technique that binds the life cycle of a resource that must be acquired to the lifetime of an object, making it easier to manage resources. With RAII, you only instantiate and manage the lifetime of an object on the stack. This object will be a smart pointer that is part of the standard C++ library. This smart pointer then takes care of managing your resource, which is something that needs to be acquired and freed. The standard library in C++ offers many such smart pointers that you can use based on your use case. The shared pointer allows multiple objects to share a resource. The unique pointer allows just one object to have ownership of a resource. That resource cannot be shared. These smart pointers have already been coded to do things right. The object, the smart pointer resource, will be created on the stack. The constructor of the smart pointer will take care of acquiring resources, and the destructor of the smart pointer will take care of releasing those resources. Now, the rule of 5 has not gone away, but what you've done is delegated to the smart pointer, which is an RAII object. Well, they need to follow the rule of 5. The destructor needs to free resources, constructor and assignment operators need to take care of copy and move operations. The advantage here is that smart pointers in the standard library are already implementing these for you, and they are robust and well tested. So use these objects from the standard library rather than rolling your own. Initialize these RAII objects on the stack so objects are destructed when they go out of scope. Smart pointers should be stack resources and not heap based resources. There are some facts of C++ that you just cannot get around. And one of these facts is, if you're creating resources on the heap or the free store in C++, that is, you're newing up memory for a particular resource using the new keyword, well, you are responsible for freeing that memory yourself. So, all of the memory allocated on the heap, also known as the free store, is your responsibility. You allocate that memory, you free up that memory. And this fact actually is an important reason why it is often difficult to program in C++. It's hard to keep track of allocating and deallocating memory. In modern C++, though, there are smart pointers that help you with exactly this. What we'll see here in this demo is an example of managing memory yourself. You'll see all of the hoops that you have to jump through. And then we'll see how you can use smart pointers from the latest versions of C++ to manage this memory for you. Let's imagine that the resource that you're working with, which has to be allocated on the heap, is a database connection. Here I have the header file for the class DB connection. You can see on line 8 that this database connection has a connection string. We have the constructor on line 12, the destructor on line 14. The destructor will run to clean up our connection to the underlying database. And I have a getter for the connection string on lines 16 through 18. The implementation of this DB connection resource is very straightforward. We have the constructor implemented on lines 9 through 13, where we initialize the connection string and we simply output to screen constructing and the connection string of the DB connection. The destructor also doesn't actually perform any cleanup. That's not needed for this demo. All we'll print out is destructing and the connection string. Next, we have a class known as DB wrapper, and this wrapper class wraps around a DB connection object. In the real world, your connection objects are often set up like this. The DB wrapper will allow you to reuse connections between multiple clients. It may use some kind of connection pooling, and a variety of other things can be built into the wrapper. We'll keep things simple. Our DB wrapper has the name of the database, that's the variable on line 9, and has a pointer to a database connection, PDB connection on line 10. The fact that this is a pointer indicates that the DB connection object will be allocated on the heap. The constructor for DB wrapper simply takes in a database name. It has a destructor as well on line 16. Get name will give us the name of the database. That's a getter on lines 18 through 20. And on line 22, I have a method called create connection. This create connection, which takes a connection string as an input argument, will create a new DB connection resource. Now we can move on and look at the implementation of dbwrapper.cpp. The constructor is on lines 10 through 14, where we initialize the name of the database, DB name, and we also initialize the DB connection to a null pointer on line 11. This is important. We want to ensure that when we first set up a database connection, it points to null, clearly indicating that there is no connection yet. I also have a cout statement here indicating that we are constructing the wrapper and the name of the database. The destructor for the wrapper is on lines 16 through 20. This is where we clean up our memory allocated to the DB connection. We free up memory using the delete keywords on line 17. You see that we delete PDB connection and we print out to screen destructing wrapper and the name of the database associated with this wrapper. And finally, we have the create connection method, which is where we allocate the memory for a new database connection. It takes a connection string as an input argument. We use the new keyword on line 23 to create a new database connection using this connection string. So we are clearly handling all of the memory allocation and deallocation ourselves. Now let's go ahead and take a look at the client code in main.cpp. First, we'll keep things simple. Observe the open-close curly braces on lines 11 and 17. This allows me to create a nested scope within my main function. Within the nested scope, I have created two DB wrappers for MySQL and MongoDB. I haven't created any connections associated with each of these wrappers. I simply print out the name of the database and I end the program. So very straightforward. Both of the DB wrappers are created on the stack. This will allow us to see how objects on the stack are constructed and destroyed. So the MySQL wrapper is constructed first, then MongoDB. Then we print out the names of the databases MySQL and MongoDB respectively. The MongoDB wrapper is destroyed first and then MySQL. So destruction always happens in the reverse order of construction. Let's now create a connection resource for each of these wrappers. I invoke MySQL.createConnection on line 15 and I create a connection using the connection string MySQL_con. I do the same thing on line 16 for MongoDB. MongoDB.createConnection and the string is MongoDB_con. Now, each wrapper has an underlying connection and when the wrapper goes out of scope, the connection needs to be destructed as well. Let's see if that happens. And yes, indeed it does. The code on lines 12 and 13 produce the first two statements in the console constructing the two wrappers, MySQL and MongoDB. When we invoke create connection on lines 15 and 16, we construct the connections, that is lines 3 and 4 in the console output. We then print out the name of the database and then When the wrapper goes out of scope, the destructor for the wrapper is called, which in turn calls delete on the underlying connection. That's why you see destructing MongoDB con first, then the wrapper is destructed, then destructing MySQL con, and then the wrapper for MySQL is destructed. So it seems like we've handled memory correctly, right? That wasn't that difficult, but let's make things a little tricky. I've simplified things to have exactly one wrapper, the MySQL wrapper that is created on the stack. I then invoke MySQL.createConnection twice on lines 14 as well as 15, and I create connections with different connection strings. But if you remember our code from create connection, as you can see from the inset picture, when I create a new connection by allocating memory for a new DB connection object, I don't actually free up the memory of the old connection. I had forgotten to do it in this place, and this will result in a memory leak. This basically means that when the DB wrapper goes out of scope, it will clean up the memory for one connection, but not the older connection whose memory we leak. And this is what you'll see when we run this code. So in the console output, you see that we've constructed the wrapper MySQL. We've constructed two connections, MySQL con 1 and MySQL con 2, but we've destructed only one connection, MySQL con 2. We've essentially leaked memory for the first connection, MySQL con 1. Well, you might say that's not too bad. It's exactly one place. I can fix it there. So I'll just go to the place where I create a connection. I'll delete the already existing PDB connection. If it was null previously, this delete PDB connection won't do anything. So there's nothing wrong there. And then I'll create a new one. This seems to have fixed our problem. And in this particular case, it has. Let's just look at the construction and destruction of the connection. On line 14, when we create our first connection, you can see constructing MySQL con 1 in the output. On line 15, when we create a second connection, the first connection is first destructed. So destructing MySQL con 1, then constructing MySQL con 2. And at the end of the program, MySQL con 2 is destructed along with the wrapper. So things look good, and we may feel that we're out of the woods, but let's try another scenario. I have MySQL, my DB wrapper. I create a connection, MySQL connection 1. So only one connection to worry about. But now I essentially copy MySQL DB wrapper over to another MySQL DB wrapper. This is on line 16. Now the code on line 16 is a copy operation and will invoke the default copy constructor generated by the compiler. The default copy constructor does not free up existing memory. The problem here is not of a memory leak, but we'll end up trying to free the same memory twice. So the MySQL wrapper and another MySQL wrapper will both try to free up the memory for the same connection. And we'll see that when we run this code. When you look at the output, the first thing that ought to jump out is the error at the bottom. Pointer being freed was not allocated. This means that we've tried to free some memory twice. How did that happen? Well, we constructed our wrapper MySQL. This is on line 12. And you can see the console output constructing wrapper. Then we constructed the first connection, MySQL con 1. That's the only connection. When we perform the copy on line 16, the wrapper, another MySQL, the copy that is, also points to the same connection. Now, when the program exits, the wrapper MySQL is destructed, which also destructs MySQL con 1. Then the copy, another MySQL, is destructed and it tries to free up the same memory associated with MySQL con 1. It fails, and that's why we get that error. So our invoking the default copy constructor to perform the copy caused this issue because our original as well as the copy pointed at the same object in memory and both tried to free up that object. Now, this is an issue not only with copying but also with assignment operation. Let's say an example. I have two wrappers, MySQL and another MySQL. I create a connection for MySQL on line 15. And then finally on line 17, I decide to assign MySQL to the variable another MySQL. Now, under the hood, this will invoke the assignment operator, and an assignment operator implementation has been automatically generated for us by default by the C++ compiler. Now, the default assignment operator does not manage memory yet again. When you compile and run this code, you'll encounter the same problem as before. The same bit of memory, our connection to MySQL Con 1, will be freed twice, and that will result in an error. Let's try running this code. When you look at the output, once again at the very bottom, you see the error pointer being freed was not allocated. So what happened? So we constructed the two wrappers, MySQL and MySQL v2. This is because of the code on lines 12 and 13. Then we constructed the connection, MySQL con 1. Then we performed the assignment operation on line 17, and that essentially had a second wrapper point to the same underlying connection. When the first wrapper went out of scope, it destroyed the original connection. So you can see destructing wrapper MySQL, that also got rid of the connection MySQL con 1. So destructing MySQL con 1 means the connection memory was freed up. Then another MySQL comes in and tries to free the same memory again, but that memory was already freed. And that's what caused this error. So it's pretty clear that just because we have a pointer with memory allocated on the heap, we have to take care of both the copy constructor as well as the copy assignment operator. You must admit things are getting out of hand at this point in time. But let's bite the bullet. I have on line 16 the copy constructor, which takes as an input argument a const reference to DB wrapper. And on line 18, I have the copy assignment operator, once again, which takes a const reference to a DB wrapper. We'll then head over to the implementation of DB wrapper and go ahead and ensure that all of the pointer resources are freed and allocated correctly. On lines 16 through 21, you can see the copy constructor. In the copy constructor, we'll initialize the name of the database and we'll create a new DB connection for the copy. And we'll have that DB connection with the connection string with copy as a prefix so we can differentiate it from the original connection. This is just for the purposes of this demo. Essentially, what we're saying is whenever we copy a wrapper over, create a new connection resource to be managed by the copy. Don't let the copy reference the same old connection resource that is present in the original. Then at the bottom on lines 23 to 34, we have the copy assignment operator. The code here is a little more complex. On lines 24, 25, and 26, we check for self assignment. We try to see whether we're assigning the variable to itself. If yes, we then return a reference to this, the current object. If not, we'll delete or free up the memory for the pre existing connection that the current object may have. This is on line 28. Once we free up that memory, we'll then create a new DB connection object and we'll have the prefix assignment for the connection string so we can clearly identify the DB connection formed using assignment. And finally, on line 33, we return a reference to the current object. At this point, you may say, finally, things will work and copying will. So let's try creating a connection, then copying MySQL to another MySQL. And when you run this code, you'll find that the constructors and destructors will line up and there'll be no error. The copy takes care of freeing up the copy of the connection, and the original takes care of freeing up the original connection. Let's go ahead and try the assignment operation. We have MySQL and another MySQL. On line 18, I've assigned MySQL to another MySQL. If you compile and run this, you'll find that things work correctly as well. There is no error. The original wrapper takes care of the original connection. The assigned wrapper takes care of the assigned connection. So each frees up its own memory and things look good. But we've actually not considered one more case, and that is the move constructor and the move assignment operator has also to be implemented. The move constructor and the move assignment operator takes care of situations where you want to move the ownership of resources to another variable. You just don't want to copy. Now, we won't go into the details of move, but you can see that on line 20 and 22, I've implemented the move constructor and the move assignment operator. You know they're moves because we have the double ampersand indicating that the input arguments are value references. I'll also implement the move constructor and the move assignment operator. The move constructor is on lines 37 through 44. Observe on line 38, we call std move on the DB name to move the ownership of the resource to this object that's being constructed, and we create a new DB connection on line 40. Once we've done that, we delete the old DB connection on line 43. The move assignment operator is on lines 46 through 61. We check for self move on lines 47, 48, and 49. Delete the original DB connection. We call std move on the DB name on line 53. Create a new DB connection and then delete the DB connection on the DB wrapper from which the connection was moved. So, move involves a change in ownership for a particular resource. So, it's not a copy, you move the ownership of the resource over from the original object. I won't run and show you the mechanics of the move. The move is typically used by standard library collections to move resources over when the capacity of the original collection has been exceeded, typically used by vectors. But what is clear from all of this is that resource management on the heap or the free store is hard. And really, you shouldn't be doing this yourself. You should be using the classes available, the smart pointers available as a part of the standard library. They follow the principle of resource allocation is initialization, and that's what we look at next. In this demo, let's see how we can use resource acquisition is initialization, that is the right way to manage free store resources within C++ using smart pointers in the standard library. So rather than having us manage our own resources, we'll make the use of smart pointers that will manage the resource for us. The example here is the same as in the previous demo. We have the DB connection with a connection string with a constructor, destructor, and a getter for connection string. Here is the implementation of DB connection. We print out a message in both the constructor as well as the destructor. We have the DB wrapper object, which is a wrapper around the database connection. Now, the database connection, as before, is allocated on the heap or on the free store, but rather than managing this memory ourselves, we'll make use of a smart pointer. And the smart pointer that we'll use here is the shared pointer. Before we look at the characteristics of the shared pointer, let's understand how smart pointers work in general. Smart pointers wrap around a pointer resource. A pointer resource we know has memory allocated on the heap or the free store. Smart pointers are abstract data types that simulate a pointer while providing added features that are useful for us, especially automatic memory management. So, if you use a smart pointer to wrap a resource that is allocated on the heap, that smart pointer will manage the memory of that resource. So rather than managing the life cycle of the pointer resource yourself, you're tying the life cycle management of pointers to the life cycle of this smart pointer object. Now, there are many smart pointers available as a part of the standard library. The unique pointer that we dealt with in an earlier demo, that's a smart pointer. The shared pointer is another example. There are other smart pointers available in C++ as well, and you'll choose the right smart pointer based on your use case. Now, the shared pointer that I have used here is specifically designed for those scenarios where an object in memory, in our case, the database connection, may have more than one owner. So, you want the same resource to be shared amongst multiple owners. I want the same database connection to be shared across multiple DB wrappers. And that's why I've chosen the shared pointer resource as the smart pointer here in this use case. When you use smart pointers, what you're essentially saying is let these smart pointers take care of resource acquisition is initialization, the right way to handle memory on the free store. I won't manage my memory myself. I'll just use the smart pointer. Notice on line 11, our DB connection object is wrapped within the shared pointer resource. One thing to keep in mind about smart pointers, such as the shared pointer, they're always allocated on the stack. So, this DB connection shared pointer is created on the stack. So, it'll go out of scope along with other stack variables. So, my DB wrapper has a DB name on line 10 and a shared pointer which holds a DB connection allocated on the free store. Then I have the constructor on line 15, the destructor on line 17, a getter for the DB name on lines 19 through 21, and I have the create connection, exactly like earlier. Let's take a look at the implementation of this DB wrapper. Notice in the constructor, there is absolutely no change. I simply print out constructing wrapper on line 14. The destructor has a change. In the destructor on lines 18 through 20, I haven't actually freed up the memory for my DB connection. Well, I leave it to the shared pointer to take care of that. When the shared pointer variable goes out of scope, the memory associated with the DB connection that it wraps around will also be freed. So I don't have to explicitly free any memory here in the destructor. And that is a major change. There is a change in the create connection method as well, defined on line 22. It takes a connection string as an input argument. On line 24, we call dbconnection.reset. We are invoking the .reset method on the shared pointer. When reset is invoked without any input arguments, the current object releases the ownership of this managed object. So our current DB wrapper releases the ownership of the DB connection. Now, there might be other owners to this DB connection. The current object knows nothing about those. That's up to the shared pointer to manage. The current object says, I no longer own this DB connection because I'm going to create a new one. And on line 25, we use make shared to create a new DB connection with the connection string. We've given up ownership of the old connection and created a new connection, and we need to do nothing else. We do not have to implement the copy constructor, the copy assignment operator, the move constructor, the move assignment operator. Nothing. Things will just work. Let's see an example. Here in main.cpp, once again, I have an inner scope starting on line 12 and ending on line 19. Within that scope, I have a DB wrapper called MySQL, and I invoke create connection twice, once on line 15, then on line 16, and I print out the name of the database. Now, this should not cause any memory leak, and if you run this code, you'll find that it doesn't. So the code on line 13 produces the first line of the output, constructing wrapper MySQL. Then the create connection on line 15 constructs MySQL con1 in the output. The create connection on line 16 gives up ownership of the first connection, MySQL con1, and that's why you see the destructing MySQL con1 in the output. There was just one owner, that owner has given up ownership, so that connection can be destroyed. The smart pointer takes care of this. So MySQL con1 has been destroyed, MySQL con2 has been constructed, and that's destructed when the wrapper goes out of scope in the usual way. So we got everything for free without having to handle memory ourselves. Let's try another use case. Once again, I have the MySQL DB wrapper. I create connection to MySQL con1, and then I copy MySQL over to another variable called another MySQL, the copy constructor. The last time around, if we did not manage memory correctly, this resulted in an error where we tried to free a portion of memory twice. Let's try it this time around with our smart pointer. Absolutely no error. The same portion of memory was freed exactly once. What happened was MySQL, the wrapper was constructed, then the MySQL con1 connection was made. When we performed the copy on line 17, the smart pointer ensured that the number of owners for the DB connection was incremented by 1. So it said MySQL as well as another MySQL are both owners of the underlying DB connection named MySQL con1. So when the objects went out of scope, the shared pointer ensured that the memory was freed exactly once. And you'll find that things are taken care of for us even in the case of assignment. I have two wrappers, MySQL and another MySQL, defined on lines 13 and 14. I have created a connection for both of these wrappers on lines 16 and 17. So both DB wrappers have pre-existing connections. I then assign MySQL to another MySQL on line 19. Now, this should ensure that the memory for all of the connections is handled correctly. And let's see whether that happens. We'll go ahead and compile and run this code. And you see absolutely no errors. We have two wrappers, MySQL and MySQL v2. This is because of the code on lines 13 and 14, and you can see the corresponding constructing wrapper statements in the output. Each of these wrappers have their own connections. The create connections on lines 16 and 17, and you can see that two connections were constructed in the console output. Now, the first connection was destroyed, destructing MySQL v2 connection 1. This is because of the copy assignment on line 19. The original connection associated with the another MySQL wrapper was destroyed, and then another MySQL took joint ownership of MySQL con 1, the same connection as MySQL wrapper. And you can see that while destroying the wrappers, the memory for the connection was freed exactly once. The shared pointer took care of this. And with this, we come to the very end of this course, Managing Memory in C++. We started this course off with a discussion about modern C++ and what that term actually means. We saw that older versions of C++ before C++11 are referred to as classic or legacy C++, and all versions after C++11 are collectively called modern C++. Modern C++ lays down philosophies and standards for how code should be designed, making our life easier and our code more readable and robust. We saw that managing memory on the free store or heap of C++ is hard. In fact, handling resources of any kind which have to be explicitly allocated is hard. We saw some of the pitfalls that could occur when we have to allocate and free those resources in the presence of multiple code branches and exceptions. We then discussed the rule of 3 and rule of 5, which state that any class that manages its own resources needs to implement the destructor, the copy and move constructors, and the copy and move assignment operators. However, we saw that by having smart pointers from the standard library manage our resources, our classes could follow the rule of 0. Smart pointers use resource allocation is initialization or RAII to bind the lifecycle of a resource to the lifetime of an object on stack, making our C++ less error prone as far as resources are concerned. Now that we have a strong understanding of a range of C++ techniques, we can look ahead to what C++ has in store for us in the latest version C++ 20. That's in the course Up Ahead, Designed by Contract and Features in C++ 20. If you want to make writing defensive code an integral part of your design process, you should follow Design by Contract. Design by contract is a term that was first coined by Bertrand Meyer while designing the Eiffel programming language. The Eiffel programming language implements design by contract as a part of its language features. We introduced design by contract briefly earlier in this learning path. Design by contract is a metaphor for how the different components of your software system collaborate with each other based on mutual obligations and benefits. Any interaction between components in a software system involves two parties. You have a client who requests a service. This client wants a benefit from the second component. The second component is referred to as a supplier. The supplier provides the service, is obligated to provide the service. In order to be able to avail of services and provide services, clients and suppliers enter into contracts. The contract refers to the agreement between the two parties, which is documented and enforced in some manner. The service provided by the supplier to the client is the benefit obtained by the client. The payment terms or what the client gives in return is the benefit for the supplier. So there is mutual benefit. Now, in order to avail of these mutual benefits, each party is prepared to incur some obligations. That is mutual obligation. The client needs to agree to the terms set by the supplier. The supplier should provide the service in a timely manner. Design by contract is extremely applicable to software systems. The software interface or the API that you have specified defines the contract in a very precise and checkable manner. These interfaces can be thought of as classes and methods that fulfill the contract, which can be used by the client. The contract is fulfilled by using three components: preconditions, postconditions, and invariants. We've already discussed these before, so I'll go over them quickly. Preconditions are predicates that need to hold true when we enter a function or a component. They'll be checked at the very beginning. Invariants are predicates that have to hold true at some point in the computation that you're performing, and postconditions are predicates that hold true upon exit from a function. Precondition checks are performed on the inputs that you pass to a program. These inputs should satisfy certain criteria or meet certain conditions before the program can execute. Invariants are basically properties in the program that are assumed on entry and guaranteed on exit. So these properties do not change during program execution. The execution of a program needs to change state or produce a result. Post conditions refer to the updated state of properties that are guaranteed when the program execution is complete. Here is a high level visualization of how design by contract works. There is a lot going on here, so let's break this down. You can see that our software component is here at the very center of everything. The software component will run code to produce a result. Preconditions are checked on the input values to the software component. If the preconditions are not met or there is some other unexpected error while running your computation, well, make sure you propagate this error. Make sure you throw an exception to indicate that something bad has happened. Once your program has completed execution, check to see whether it has done what it has promised to. Those are post conditions, which are usually checks performed on output values. Now, it's quite likely that your program execution produces side effects. Some of these may be inadvertent, others may be needed. Use invariants to check to see what properties should not be changed during program execution. Contracts as a feature that would be part of the C++ programming language and enforced by C++ were supposed to be part of the C++ 20 release. The technical specifications for how exactly these contracts would work, the keywords used, the structure, everything was complete. However, the feature was not ready in time for C++ 20. So the current plan is for this to be included in C++ 23. At the time of this recording, it's not possible for us to design by contract as a part of the C++ language. However, let's take a look at how exactly contracts are supposed to work. When they'll be released, we'll be ready for it. You can see on screen here the general structure of a contract attribute. The contract attribute here includes one of these keywords: expects, ensures, and assert. These are used to check for preconditions, postconditions, and invariants, respectively. The modifier term specifies the contract level or the enforcement of the contract. The possible values are default, audit, and axiom. And the conditional expression here represents the actual condition or the predicate that the contract will check. Every function that adheres to a contract will use the expects keyword to perform the precondition checks before the function is executed. The ensures keyword will be used to check the post condition after the function has executed is the state what we want it to be. And finally, we'll use the assert keyword to check for invariants within the function execution. Asserts help mitigate unwanted side effects of your code. The contract modifiers, default, audit, and axiom determine the enforcement status of the contract. The default modifier should be used for those contracts where the cost of runtime checking of the contract is small. You don't pay a very high price. If you expect the cost of runtime checking of the contract to be very large, you should specify the contract using the audit modifier. And finally, with the axiom modifier, the predicate is not checked at runtime. The ensures keyword that allows you to check for post conditions on function exit is able to access the return value from the function. So the identifier here allows you to refer to the return value. Here is an example of some C++ code which follows design by contract. This is from the technical specification. This may not be how the feature looks when it's released. So the actual method that we are executing is a push operation onto a stack. This takes the stack as well as the value that we want to push onto the stack as input arguments. Now we expect that the stack is not full when we perform the push operation. This is our precondition check. We then ensure that at the end of the push operation, the stack is not empty. This will allow us to confirm that the value has been pushed onto the stack and there is at least one value in the stack. Ensures and expects are before the function definition. The implementation of the function is within these curly brackets highlighted here. Now, within the function, you can have multiple assert statements to ensure that invariants are met. The structure of the contract attribute in C++ should have made it clear that preconditions and postconditions are part of the function interface. These cannot access the local variables of a function and the private and protected members of a class. So they can only access input arguments and return values. Assertions are part of the function's implementation, and assertions should be able to access local members and private and protected members of a class. So, when will contracts be validated and how are violations handled? If you build your C++ code with the level of no contracts in your C++ code will be checked. If you use the build level default, which is the default specification, only contracts that have been marked with the default modifier will be checked. If you use the build level audit, default contracts as well as audit contracts will be checked. Remember, axiom contracts will never be checked. The latest release of C++ at the time of this recording is C++20. C++20 is a very powerful language with many new features. Let's quickly discuss the path that C++ took to get here. The C++20 version is the latest version in modern C++. Modern C++ has no precise definition. It's a colloquial term used to refer to the current style of C++ programming, where we use light, precise components that use the type system of the language and its new features in a gainful manner. Modern C++ embraces new features and new standards with every new C++ release. It's a different philosophy and a new way of thinking of C++ programming. Now, C++ as it existed before the introduction and adaptation of C++11 is often referred to as classical or legacy C++. C++11 released in 2011 completely changed the way programmers worked with C++. So all versions of C++ after 11 are referred to together as modern C++. Early versions of C++ did not follow a set standard. C++ 98 was based on the Annotated C++ Reference Manual or ARM published in the late 80s. This annotated C++ reference manual defined the functionality of C++, and you can say it laid the foundation of the first C++ standard. C++ 98 was quite powerful. It included templates, the standard template library, containers, algorithms, strings, and input-output streams. C++ then got a major makeover in the year 2011. C++ 11 fundamentally changed the way we program in C++. It included the components of Technical Report 1, often referred to as TR1, which contained 13 libraries, which were then specified to become part of the C++ standard. C++ 11 was a huge release. Some of the features that it included were regular expressions, smart pointers, hash tables, the random number library, move semantics, a new memory model, and a threading API. Since C++11, C++ has not looked back. There is a new release every 3 years. C++14 was a small standard that brought in reader-writer locks, generalized lambda functions, and const expression functions. C++17, released as you might expect in the year 2017, was a slightly larger standard. The main features were a parallel standard template library and the standardized file system. Since the game changing release of C++11, C++20 has been the biggest release so far. It includes changes as fundamental to the language as the changes that were brought in because of C++11. There are four huge features included as a part of the C++20 standard: ranges, coroutines, concepts, and modules. The ranges library makes it very easy for developers to work with collections in the standard library. It's very much more intuitive to use the functions provided by ranges when you're working with STL containers. In a demo that follows, you'll see how you can work with the ranges library in C++20. Ranges have lazy algorithms that work directly on the container itself rather than with iterators of the containers. Iterators tend to be unsafe because they can move past the end of a container. The ranges library also includes the pipe function that allows you to compose and chain together transformations on your data. Coroutines were introduced in C++20 to make asynchronous programming more mainstream, easier to perform, and more intuitive. Coroutines form the foundation for cooperative tasks, event loops, infinite data streams, and pipelines. The basic foundations of coroutines include the use of functions that can suspend their state and keep their state around. These functions, once re entered, can pick up from where they left off. Such functionality has been available in other high level programming languages such as Python, and now C has it as well. The concepts module makes programming using templates much more powerful by allowing you to specify semantic categories for valid template arguments. This allows you to express your intent for the kind of template that is accepted by a class or a function. Templates that satisfy certain parameters. That's what you can specify. Concepts allow you to specify constraints on the type of the system or the type that is accepted by the system, which means you can get an error message when you use the wrong type with the system. And the last big feature introduced in C++20 is modules, which is a modern solution for the componentization of C++ libraries and programs. Modules work along with namespaces. They don't replace namespaces, and they eliminate many issues that you have with header files, and they reduce the compile times of your projects. C++20 is the brand new version of C++ released in the year, you guessed it, 2020. At the time of this recording, C++20 is still very new, and the features and functionality that it offers haven't been implemented by all of the C++ compilers. Some compilers have gone further ahead in their implementation than others. For example, the Clang++ compiler that we've been using lacks in support for C++20 features. Here on this page on en.cppreference.com/w/cpp/compiler support, you can see the current state of C++ compiler support for the various versions of C++. You can see for C++23, GCC has some support. All of the features are not fleshed out yet. You can see for the C++23 library, there is some support. The features are not fleshed out yet. For the core language features of C++20, you can see that GCC has the most support. Clang++ has less support. You can see those reds there indicating less support for all features are not available. So GCC is the right compiler to use for C++20 at the time of this recording. And the same is true for the C++20 library features. GCC has the most support, other compilers have less support. For older versions of C++, you'll see that these grids are almost all completely green, indicating that all of the compilers have support for these features. Now, of course, when you are observing this page, you might find more green than red because it depends on when you're observing this page. So for C++ 11, 14, and 17, all compilers have almost complete support. But for C++ 20, at the time of this recording, only few compilers have support for a few features. So if you want to run C++ 20 and your compiler does not support C++ 20, just head over to warnbox.org. If you're just looking to try out features from a new version of C++, Warnbox is a great resource. You can see all of the compilers that it supports. It also supports multiple languages, not just C++. Let's say you want to compile your code using a different C++ compiler. Use this drop down to select the compiler that you want to choose. You can use C++ 2003, 11, 14, 17, 20. You might even be able to try out features from upcoming releases. Now, I'm going to write some code in C++ 20 and use warnbox to compile my code. The ranges library is an important new component in C++ 20. We'll explore some of its functionality. On line 5, you see a hash include for ranges. Ranges offers us multiple different ways to access the elements of standard collections, and it's much more intuitive to use than any previous library. You can see on line 9, I have a vector of names: Ursula, Phoebe, Rachel, Monica, and Janice. Before the ranges library existed, if you wanted to sort these names in the ascending order, you'll use the sort algorithm from the algorithm library. So on line 11, I have the standard sort. I pass in two iterators, names.begin and names.end, and then I'll get the names in sorted order. I have a ranged for loop on lines 13, 14, and 15 to print out the names in sorted order. Let's compile and run this code, and you'll see that this is how sorting was performed before the ranges library was introduced. Once you hit run, you'll find the output here at the bottom. Here you can see the names in the ascending order or the alphabetical order or the lexicographical order. Let's use the ranges library for the exact same purpose, and you'll find that ranges makes things easier. You simply specify the collection name. You do not need to specify the begin and end iterator. Simply invoke, as I do on line 11, std ranges sort and pass in the collection. And here we are. All of the names sorted in the ascending order. Ranges makes things easy. After having performed the sort, let's say you want to iterate over the names in the reverse order. Well, ranges makes this easy as well. On line 13, you can see I invoke std ranges reverse view. Anything that is a view will not change my original data. It will give me a view into my vector data, which has been sorted, but I'll now be able to access the names in the reverse lexicographical order, and that's what will be printed out. Let's run this code, and if you scroll down to the bottom, you should see the output, and you can see that we have the reverse lexicographical order of names starting with Ursula and ending with Janice. The ranges library works with all collections in the standard library. You can use this reverse view with maps as well. You can see I have a names map instantiated on line 9. I've added key value pairs to the map on lines 11 through 14. For Ursula, Alice, Janice, and Monica, you can imagine that the values are scores. And I have a range-based for loop on line 16 where I use the reverse view and pass in the names map. Maps are sorted by default on the key field. The reverse view will allow us to access key value pairs in the reverse order of the keys. Here it will be in the reverse lexicographical order. I'm going to go ahead and hit run. And here at the bottom, I should get the result. Ursula is first, Alice is at the very end. The ranges library also makes data transformations very, very simple by allowing you to use the pipe operator. The pipe operator basically pipes the output of some data into the next transformation, the output of that transformation into a third transformation, and so on. The pipe operator allows you to chain your transformations together one after the other till you get the final result. I have a vector of numbers defined on line 9, 1 all the way through to 10. On line 11, I have a number of transformations that I want to perform on the numbers. I pass in numbers to a filter operation which gives me all of the even numbers. only those numbers where n% 2 is equal to 0. You can see this on line 11. Now, the even numbers are then piped in to a transform operation which returns the square of the even numbers. Notice the return n multiplied by n on line 12. We start with the original numbers, perform a filter operation, then a transform, which gives us the square of even numbers. That will be the final result. And that's what we'll print out using our for with ranges on lines 14, 15, and 16. Time for us to run this code and see the power of the pipe operator. Click on run and scroll down to the bottom, and here we see it. 4 is the square of 2, 16 is the square of 4, 100 is the square of 10. So we have the squares of all of the even numbers in our original vector. There is a time and place for defensive programming, but sometimes playing defense may not be the right thing to do. You might need to employ offensive techniques instead. Let's understand what offensive programming is all about and when you would choose to use offensive techniques instead of defensive. Defensive programming and defensive techniques are extremely important when your code interacts with external third party libraries. These external components could be hardware, third party libraries or applications, user input, or third party communication stacks. If anything from the outside world is going to enter your system, it should only come through after passing through your defensive programming barrier. Internal software need not defend itself against other internal components. So here are use cases for defensive programming. So defensive programming is useful when interacting with hardware, external libraries, and external inputs. Defensive programming is meant to defend against hardware glitches, bug-riddled libraries, and essentially anything from the outside world. If you've not generated this input yourself, you need to defend yourself against it. However, if your program is overly defensive, if you abuse defensive programming, well, that's not a good thing either. Excessive use of defensive techniques may obscure bugs that exist in your code. And your objective of finding bugs early and failing fast, well, you won't be able to meet that. Now, in those use cases where defensive techniques are not the right ones to use, offensive techniques are. So, when you're defending yourself against external code and external inputs, that's when you'll employ defensive techniques. When you're working only with internal components and internal code, you need to get on the offensive. You need to fail fast and complain about the internal code. Offensive programming is all about complaining and squealing loudly when errors occur. So developers come in and fix those errors. Even though in English, offensive is the opposite of defensive, offensive programming is not the opposite of defensive programming. Offensive programming takes the same basic principles and ideas behind defensive programming and expands on them. Defensive programming only checks for the validity of inputs. Offensive programming will complain and fail when invalid situations occur. Offensive programming is all about failing quickly and obviously when errors occur. Offensive techniques don't really make sense in client facing code. With client facing situations, you need your code to be robust and handle failures gracefully. Offensive programming is all about handling failures by squealing loudly. So, offensive programming makes sense when the code that you're working with is almost entirely within your organization. You're working with just internal components. If your software is only interacting with internal components, you know that all of the bugs that you find, whether it's in your software or in the components that you're interacting with, they're all the responsibility of the developers in your organization. If everything is internal, what you really want is to be able to find and surface bugs that exist quickly. This means wherever you find something has been received in error and input is wrong, you need to fail and fail fast. And this is why offensive programming involves using assertions liberally and creatively against developer errors and system behavior. So sprinkle assertions throughout your code to find and catch bugs quickly. Offensive programming can help you in many scenarios. Let's say you're trying to track down performance issues, time all of your operations, and assert and fail when they exceed the limits that you've set for them. This will help you track down when exactly your operations are slow. Let's say you're dealing with memory issues, constantly profile the memory that your code uses. If memory is over allocated or excessively fragmented, your system itself should fail. Make sure you capture enough detail to allow for debugging. Offensive programming can also be used to track thread deadlock issues. If such a deadlock occurs, that should fail the system. Again, make sure you capture enough detail for debugging. Let's quickly summarize and see why offensive programming can be useful. The main benefit is bugs that exist within your system will be caught and found early, leading to faster fixes. Offensive programming also allows you to validate the assumption of your software. You'll also get a chance to see whether these assumptions are being met or the assumptions themselves are plain wrong. Offensive programming will help you aggressively track and measure the types and number of bugs in your code. And finally, offensive programming helps ensure your system is always in a sane and correct state, because if it's not, you're going to fail fast and fail quickly. In summary, you should use the defensive techniques that we've studied while working with external libraries, user input, and hardware failures. In other situations, when you're dealing mostly with internal software and internal libraries, use offensive programming. We've now come to the very end of this course, Design by Contract and Features in C++20. We started this course off with a discussion about what design by contract is all about. We saw that it involves two parties, a client and a supplier, collaborating with each other based on mutual obligations and mutual benefits. We saw that design by contract involves three main components: the use of preconditions to check inputs to methods, the use of invariants to check for properties that should not change during method execution, and finally, the use of post conditions to check for updates that should be made once a method has completed execution. Design by contract was an important feature slated to be part of C++20, but will now be released in C++23. We then moved on to explore the most important feature releases in C++20, which included the ranges library, coroutines, concepts, and modules. We briefly explored how the ranges library makes working with container collections in the standard library much easier since it operates on the collection directly rather than on iterators. We rounded this course off with a discussion of when using defensive techniques may not be the right approach, and instead we should be using offensive programming techniques. We saw that when our code only interacts with components internal to our organization, offensive techniques help us fail fast and find bugs and fix them early. At the end of this learning path, you now have the skills, tools, and the ability to write robust, defensive, and high quality C++ code, and are ready to venture on to other learning paths on building complex C++ projects.